my honor to welcome you to this symposium to celebrate the work of Day-Weiss. Thank you all for being here. And many of you traveled from far away, and despite the snow, you made it. Thank you. And many people from the local communities are gathering today. It's really great. I knew that I would prepare something to say, and then I would see at all of you. It's like, it doesn't matter what I say. It's great. It's really an honor to have you here. So we will hear a lot of stories, memories, told by many different people. Some work with Ray for many decades. Some maybe just met him in their journey, and they were somehow touched by him. Will cry. I already started sooner, so probably every 10 minutes I will be crying. Please, no judgment here. But I hope we all take something from it. Celebrate the work of Day-Weiss is not easy. How you celebrate his work. And with Peter, I'll be thinking about how we do this in the right way. I kept telling him, can you imagine what Ray would say? And this is my attempt. Let me understand. You are going to have a room full of smart people, and you're going to talk about me? Are you out of your mind? You haven't learned anything. This would be the polite version. And so, but then, as we started involving more people, and Kip Thorne said in one of the early meetings we have, he said something, which was very revealing to me. He said, yes, event is to celebrate the work of Ray, but it's really for us. It's for us to come together as a community and kind of process his loss and understand what it means for our field. And so with that, I want to thank the physics department and the Kavli Institute for Astrophysics and Space Research here at MIT to make this event possible. I want to thank all of you again for being here, and let's make this event what we want to be, without worrying if it's right or not. It will be whatever we want it to be. And with that, Peter, please, we'll start with we'll see with what? With an overview of Peter's take on Ray.
Great, yeah. Hello, everyone. Good morning, yes. So anyway, for those who don't know me, Peter Fritschel. I was a graduate student with Ray in the late 1980s, early 1990s, working on gravitational wave stuff at that time. Went off and worked on the similar thing in the Virgo project in Europe for a couple years, and then I guess Ray convinced me to come back. I thought I'd come back to Ray's group for a few years, and well, here we are after a few years, right? So what I wanted to do, we're going to hear about throughout the day, the work that people did with Ray in gravitational waves, cosmic microwave background, and other things, and how he inspired them, and so on. And what I want to do is kind of set the stage for that, like who inspired Ray, how did he actually, what got him on the road of working on both gravitational waves and the cosmic microwave background. So kind of to try to set the stage for the rest of the day. It was sort of my goal here. And what I'll point out, there's a wonderful, very long interview that Ray did in, I think, 2020. It's part of the AIP Oral History series. And of course, I'd heard many of these stories over the years too, but really I got a lot of the details out of that. So I highly recommend, checking that out. It's a really, really fun read. So Ray would say his intellectual fathers are these two guys. So here at MIT, Gerald Zacharias, with whom he was his graduate advisor, but he also worked with him as an undergraduate. And you probably all heard them. I'm not going to repeat the long kind of story about Ray's undergrad and failing out and coming back in, but it's worth reading about if you haven't heard it. So he was really his very long time mentor and super important in Ray's trajectory. And then the other one would be Bob Dickey at Princeton, which is where Ray spent 2 years as a postdoc after MIT. And I'll just go back. So if you've been in Ray's office, right, he had this photo of Gerald Zacharias in his office for all the time that I knew Ray in the course of his, I guess, 2 offices. So the Zacharias lab at MIT was building atomic clocks. And in fact, I think they built the first cesium clock. But when Ray joined the group, he wanted to improve the frequency precision of the clock. And actually the goal was to build an atomic clock that could measure the redshift, gravitational redshift here on Earth by having a stable enough clock that you could move around to different places. And so it was actually Zacharias who had the idea of building an atomic fountain clock, right? Which is where you take, hopefully, slow enough atoms, you shoot them up, rather than having an atomic, beam that sort of travels horizontally, you have a slow enough beam that you can shoot it up vertically and then wait for it to come back down, and thereby just really increase the interaction time you have, and so as to reduce the uncertainty in energy or in frequency. So Ray worked on that a lot, but it didn't work. And that was a failed experiment. And the reason was he never got slow enough atoms out of what he was working on. He was working with like a thermal source of atoms, and he just wasn't able to get ones that are slow enough that he could actually go up and then have them come back down again. Of course, now it's a solved problem. It's a technology people use, but it had to wait sort of for the advent of laser cooling to work. It was about 30 years later that it did work, but that was a Zacharias idea and something that Ray spent a lot of time on. Another thing that he likes to talk about in those years, at least if you look at this interview, is he built in the quest to use different kinds of atoms and molecules in the clocks, an ionizer that you could use to make a collimated ion beam, which I found was very interesting because about 50 years later, when LIGO was having problems with electrostatic charge in our instruments, we needed a way to neutralize them. Ray was the one who built this kind of cool ionizer that we still use in instruments. I think you'll hear more about that later today. Another thing he worked on as a graduate student was an experiment to test. Sort of there was this idea at the time that the Hubble redshift might be explained by sort of a photon-photon interaction that would take energy from photons. So rather than being a redshift from the expansion, it could be to the sort of tired light hypothesis. So we did a test on that, on gamma rays, and of course got a no result for that. And then I guess I got to the point where I actually didn't know until very recently what Ray's PhD thesis was on. So I had to dig into that. And because he never really mentioned it, and it's just kind of mentioned in passing in this oral history, as something that kind of got to the time where the money for his graduate student career was running out, and he needed to do some thesis and get out. So he did what he called a boring thesis on the Stark effect and hyperfine structure of hydrogen fluoride. So then he went off, like I say, to Princeton, 2 years in the Bob Dickey group. The big thing he did there, in fact, really just this one experiment he built a quartz gravimeter. And the idea there was to look for excitations, a 20-minute period excitation, a spherically symmetric mode of the Earth, as might be produced by a scalar gravitational field, which is part of this Brans-Dicke theory of gravity. It failed again in the sense that he built this all quartz gravimeter, but it didn't actually measure Earth motion. It was spoiled by temperature changes and tilt fluctuations. So in that sense, he called it another kind of failed experiment. But he learned a lot about it, and he said that the Princeton time was really formative for him. It used a null-seeking servo, so you operate the device, you sense at some null point, and use a feedback to keep it there, and then your feedback signal is your signal. Your feedback signal is where you take your signal from. And that's really the basis for LIGO's operation. We hold the interferometer at a particular place and use the feedback signal from that to extract our gravitational wave signal. So Ray really describes those 2 years at Princeton had a big impact on his scientific development. The group at the time was involved in lots of very different, very interesting experiments, the gravitational equivalence principle measurement, gravitational redshift of the sun measurement, precise measurement of G and the oblateness of the sun. So he said, he learned from Dickey really how do you design an experiment to get to its fundamental limits, which I think anybody who's worked with Ray and gone through Ray's group that's a key part of what you pick up. So what do you do? He's now got kind of these 2 failed experiments under his belt with the gravimeter and then the atomic fountain. So what do you do at that point? Well, I guess at that time anyway, you go back to MIT and become an assistant professor. Really, that was due to Gerald Zacharias in this case, brought him back, and he started the gravitation and cosmology group. And he began this really long-range program to see if Newton's constant G changes with time. And his idea was to make absolute gravimeters, which we would put around the Earth, and they would be referenced to the Stark effect in a molecular beam to get the absolute calibration. And then also monitor the Earth shape with a kind of kilometer scale laser strain meters. I hadn't actually realized this until recently. And he began that whole thing with frequency stabilization of an argon laser. And that's also what began his kind of long relationship with Shaul Ezekiel, who was in the group at that time and working on the laser frequency stabilization. He also, in kind of his early professorship career, made another measurement of that redshift hypothesis, but now with a laser interferometer. So we're kind of getting closer to LIGO. And that they achieved, the phase sensitivity of that was shot noise limited up at 10 kilohertz. He said, the paper said it's sort of able to discern like 10 to the minus eighth of a fringe, which is about maybe closer to really 3 orders of magnitude from what LIGO would eventually need. And this is the setup for that. If you haven't located it yet, the beam splitter. So that was the first few years. And then he had this kind of transformative assignment where he was, I guess, asked, but really kind of told to teach a graduate course in general relativity. And at that time, so I think 1966, so the students in the class had heard about Joe Weber's bars at this point, and they asked Ray, how do they work? And Ray didn't really understand well enough or have a good explanation of how the bar detectors work, so instead he came back to them with a Gedanken experiment of using a laser and a very good clock to measure the light travel time between two inertial masses. And he asked them, to solve this problem, which they did. I guess it was fairly straightforward. But of course, there was no good enough clock, right, to actually perform the experiment that way. There still isn't one. So then the course moved on to cosmology, and they started talking about, it'd just been a couple of years since the microwave background had been discovered, and by Penzias and Wilson, of course, it was Dickey who interpreted it to be of cosmic origin, so they started talking about that. And it seemed like there was a lot of interest in the class about that. But at that time, it hadn't really been shown to be thermal or isotropic. It was just kind of a single frequency band measurement. And then there started to be some tenure pressure, which I don't think actually was on Ray so much, but others in the department were a little bit worried about him getting tenure. He wasn't publishing that much, and the gravity experiments weren't, going to yield anything for a while. So it was actually Bernie Burke who suggested him that he pursue this microwave background, which he seemed to be interested in with this class that he had given. And he involved graduate student Dirk Muldner, who was another one in that class, who was very interested in this, and he had some experience with far infrared. So that's 66, 67, he began the balloon program. So his, the idea there was to, send radiometers up to get above the atmosphere, and we're going to hear, a bunch about that. But basically, just kind of summarize here, between 67 and 82, his group, they flew about 20 balloon flights. First, to try to look at the spectrum, is it really a thermal spectrum? And then to look at the, how isotropic is it? I think in particular this pulled out this few lines from one of the 1973 paper. The spectral peak of 2.7 Kelvin black body lies at approximately 6 inverse centimeters. This is a miserable region of the electromagnetic spectrum in which to carry out experiments. You can hear him saying that or see him writing that. I love that one. So I'm just going to then kind of summarize quickly, because we're going to hear about this later today, the rest of his CMB research into the 1980s and 1990s. He hands over the MIT balloon work to Stephen Meyer, kind of in the mid-1980s, early to mid-1980s. Of course, he joins up with John Mather on COBE, and becomes chair of the COBE Science Working Group, which of course makes the first measurement of the anisotropy of the CMB. So returning to gravitational waves. So Weber announced in 1969 that he claimed he had measured gravitational waves, but of course other groups around the world are now at that point also starting to make bar detectors, and by 71, really none of the other groups were seeing anything, so there's a lot of skepticism about it. So Ray kind of returns to his Gedanken experiment from the class in 1966, but now he makes it differential. In other words, measuring one arm against another. And he spent the summer of 1971, apparently, really analyzing the Michelson interferometer configuration and calculating all the noises that would affect it. And people probably know eventually that he published it just in a quarterly progress report of the RLE Research Laboratory of Electronics, which his group was in at the time. in the following, I guess, spring, in April of 1972. In this, so it appears in that quarterly progress report as section part B from his group, electromagnetically coupled broadband gravitational wave antenna. So there's about 22 pages of text and formulas, calculations, one figure, which is the one we seen here, with the concept for the interferometer that, in many ways is what we're still using, but, in several ways is not what we're using as well. But I think the thing that we all look to that for is really the first analysis. It wasn't the first time the idea of using a Michelson interferometer for gravitational waves came up, but it was the first time really the analysis of its sensitivity and the noises that would affect it came up. And this is the list of everything that he included at the time. And really most of those are things that we deal with, that we have to ended up being very important. Maybe with the exception of this one, the thermal gradient noise is not really something that we come up against. But looking back at it, actually, I also thought it was interesting because, this is part B. Part A, the contribution from his group was actually an even longer report, 35-page report on balloon flights. So he was still very active in that. And it's interesting because if you look at other quarterly reports around that time, it's typically like maybe a page or two of the things, but this was like a big issue for him. So that kicked off the gravitational wave project, and he got some money to start that. The group at this point, by now, kind of the early 70s, I don't know exactly when it was, but had moved into Building 20, and in the F wing of Building 20. So this was the lab space. Ray had a really kind of sweet deal because this is his convertible Rabbit right here, so he would drive right up, go right into this entrance of Building 20, and I think his office is right up here. So very kind of sweet commuting deal. And then in the 70s to 80s, they built the prototype interferometer, which 1.5 meters. Prototype interferometers are usually characterized by their arm length, so it's the 1.5 meter prototype. And it was using delay lines at the time, right? Not the Fabry-Pro cavities that we use now. And green laser light makes for turns out to be a really bad idea to use the delay lines, but it makes for really nice pictures. So some milestones on the path then to LIGO. I think, big one is when Ray met Kip Thorne at a committee meeting in Washington, D.C. in 1975, and that catalyzed the formation of the Caltech group, which eventually catalyzed the collaboration between the two groups and LIGO itself. So some of the key steps, I think, to the multi-kilometer interferometer, there was the first kind of engineering study in something called the 1983 Blue Book, because of the color of its cover. That was the first real kind of study where they involved some engineering firms and put that out, and this is the artist concept of what it would look like at the time. Note that in that 1983, they were looking at 5 kilometers arm length. And then the next one was the joint proposal to NSF between MIT and Caltech to the NSF for R&D to develop the technology. And the next one, of course, the actual construction proposal, which was put in 1989. Now they've got color for the artist conception, which is a big step up, I think. On the other hand, you see the arm length is now down to 4 kilometers, so I don't know if that was a good trade in the end. It took a few years, of course, for that to actually get funded, but of course, on and on it did. So the rest of LIGO you're going to hear about later today. So I'm just going to kind of end my last kind of 5 minutes talking about a little bit, my work with Ray and kind of a story there. So as I mentioned, in the mid 80s, they had the 1.5 meter prototype had been sort of decommissioned, and they're planning a new 5 meter prototype in Building 20 with a new vacuum system in the 20F high bay. There's lots of ambitions to improve over the 1.5 meter, which actually we never actually got a 5 meter interferometer going. But one of the big ambitions was to shift from these argon lasers that had been used to YAG lasers and move from the green to infrared. The YAG lasers were really noisy, super inefficient, and Ray saw that these YAG lasers was kind of their development was advancing, and that looked just like more promising. So that's what I started working on, and we worked on building our own YAG lasers. In fact, for a couple of years, Ray was able to get from General Electric a laser head, it's a slab laser head, which is called a zigzag laser. You can't tell from this, but there's a big YAG crystal in there, and the beam zigzags back and forth with total internal reflection in order to average out thermal distortions. So we worked with that for a while. We also got one of the very first light wave N-Pro lasers. It was called the Miser at the time, put out all of 5 milliwatts. But we actually made the first measurement of the frequency noise spectrum of an N-Pro laser. And we were able to do that because also in building 20, right over here, there was an anechoic chamber. I don't know why, but we were able to use that to move the whole experiment in to make it more immune from acoustic noise. So that was a lot of fun. But then there was a sort of a period, the LIGO project needed to be kind of consolidated, and it was decided that there wasn't enough time to develop YAG lasers, so the whole YAG development program was terminated. But Ray kind of wanted to find a way to keep it going on the side. So he found a NASA program that he thought might support some work on absolute frequency stabilization of a YAG laser. And this is really one of the few times I just, really working with Ray one-on-one together in the lab. And so we found, sort of reaching back to his atomic molecular days, we found a transition in the CO2 molecule that looked quite promising. And so we spent a couple really intense weeks building the apparatus, just an absorption cell, and making the measurement. We submitted it kind of just in time, like the due date was the day that he finished crafting the proposal, and he actually sent me down to Washington, D.C. on a plane to submit it in person. But it wasn't funded, unfortunately, and the group continued to suffer with noisy argon lasers for several years. But then eventually, about 10 years later, or 5 years later, we changed course and adopted the YAG laser, so confirming his kind of foresight 10 years earlier. So that's my story that I wanted to share with everybody. So I want to thank Ray for bringing us along in this journey. I found this very interesting. People he loved to use these green engineering pads. This example is actually an unusually legible version, if you've ever seen his stuff. But I think it's a really nice image. He's got, the interferometer all there laid out. So yeah, I think the other thing I just wanted to point out or say is that when Ray was asked about, how was it working, on this project over decades before it came to fruition, he would often say is, well, it really didn't think about it that way. Every day, there's always interesting problems to work on, and one thing, and there's always enjoyable people to work on them with. And so I'm looking forward to the rest of the day to hear about a lot of interesting problems with a lot of people that I really enjoy working with. So you get to hear the rest of the day. Thank you.
I'm a filmmaker, and in 1985, I was a grad student, and I knocked on Ray's door. This is how it works with Ray. Can I make a film in your lab? He says, sure, and walks off. And he ignored me for the entire time. What you'll be seeing today is a few clips from a feature film that I made. So it starts out a third of the film. The whole film is a third. You'll see a little bit here today, back in 1985 in the infamous Building 20. But the whole movie covers 40 years, minus 3 decades in the middle. And you'll see Lyman. Ray ignored me. There's a tiny, tiny moment in the clip that you'll see that I treasure, because it's the first time he asked me to lunch. And so it's in the movie, but it's like 3 frames long, so you might not notice it. So I'm telling you now to look for it. But then I made the movie. Ray watched it, and he laughed, and he said, you're okay. And after that, he let me into his world. I am a nobody, or certainly a science nobody. And Ray had all the time in the world for me. And he answered every science question I ever had, but then said, what about your son? Is he building boats? What about Elena, Lisa's daughter? What about the children? What about music education? Have you been practicing your Schubert, Opus 119? 4 measures. I've got 4 measures down. Ray, come on, give me a break. I realized this man is special in a way, and I'm not heroizing, or whatever that word is, because he's gone. I knew this from the beginning. His obsession with science is there, but it's only there because of his much greater obsession with humanity, with people. and who we are as a species. And he, therefore, in my mind, is one of the most rare people I've ever met. He's my science dad. And that's all I'll say. Thank you. 14 minutes for those who fall asleep. It's 14 minutes long.
Oh, I just should have screwed up my program.
Very crazy arrangement. Pretty dumb.
Yeah. We want to move the tube towards the mink, I think.
This is Ray. He's the boss of the lab. Ray built an antenna to detect gravity waves.
Array looks at, for example, supernova explosions in some galaxies, or heavy double stars that rotate around each other, you know. And
this is a famous theoretical physicist, Dr. Victor Weisskopf.
Gravity waves, and this is what Ray is looking for.
This is Dan. He also built the gravity wave antenna. Dan would like very much to graduate.
No. The time, because VI is a power. Yeah, right. And KT is an energy. Do you understand squeeze states?
Oh, wait, this is the quantum non-demolition? No.
One of us has to stand on the table, huh? Or you stand on ladders?
Well, 2 ladders, actually.
2 ladders. Wonderful. Heroics. You might as well go to become Lehmann brothers.
Yeah.
This whole idea started with Einstein. It's just taking a long time to find gravity waves because they're so small and hard to detect. Right now, the antenna is just a prototype.
Hughes got him.
And here's how it works. You start with a laser beam, which is a single coherent wavelength of light.
Here. And the light comes out and it goes screaming through a whole bunch of stuff. And the first thing is Ray's phase modulating crystals. And we use this to get rid of a lot of our noise sources. It's kind of specialized, but the laser beam comes out, goes through the crystals.
And the beam is sent through a bunch of monitoring devices before it gets to the antenna itself.
And then once it gets inside the instrument, right here in the central mass, it gets split into 2 beams, which now have the same phase. And those 2 beams get sent down to the far masses, get reflected back, hit a mirror here, and bounce back and forth 56 times.
Then the split beams are recombined. If a gravity wave came by while the beams were separated, then one of the path lengths will be stretched a little bit, and now will be out of phase with the other beam.
So finally coming out of here is a beam of light, which we put on a photodetector, and that lets us measure the difference in path length between the 2 arms, and that's our signal. That's the thing we want to see gravity waves in.
And they translate that out of phaseness into brightness and darkness of a spot on a photodetector. That's the trick.
A tensor wave is
Gravity waves are also called tensor waves.
travels like this and expands like this as it's going through space. So you get synchronous. So that's why the signature in this in the antenna downstairs is you look for one arm shortening and one arm lengthening. Just even the fact that no one's ever... Here's one of the 4... Yeah, come in. What are you guys talking about?
Oh, why it's neat to measure gravity waves.
Hysteresis curves?
No.
In magnetic systems?
That's right. That's really interesting.
Yeah.
The engineering part of experimental physics.
Right. Yeah, well, I wouldn't mind knowing why it's interesting to measure gravity waves. You probably wonder why it's interesting to plot a bifurcation diagram.
No, I think that's pretty neat, too.
Yeah.
Ooh, yes. Now, where's that little stupid thing? I'll tell you one of the things you store stuff that's busted.
Ray just found out the whole lab is going to be torn down and renovated in a few months, and the antenna will be out of commission for good. It's just one more pressure to work the bugs out of the system quickly.
16 minutes left, and we gotta get this straight.
The theory of general relativity as it stands is very tight and very beautiful. It's geometrical. The theorems are aesthetically pleasing, and the whole thing hangs together very nicely. I would like to pursue it as a hobby, perhaps, but that's a different thing than the experimental sort of work that these guys are doing. There's a lot of, anytime you get into the experimental stuff, it's really just long hours in laboratory screwing around with circuits and stuff.
Peter, do you need a hand hooking things up there?
There's only one thing left to do, and that is to alter the suspension system, which has been introducing all kinds of noise into the antenna. They'll replace the solid rods, which held the masses, with very fine wires.
Great.
Sort of a tricky thing to do.
It's nice when things work.
Yeah, no.
Oh, but everybody's told me in the lab that you're gonna pass me.
That's right. We'll see. Never can tell.
One day, a couple years ago, Ray heard tapping on the lab's window. It was Lyman. He wanted to come in, join the lab. They talked. Ray said yes. Somehow Ray knew that Lyman was special.
That's a picture. That's a picture of Einstein and Planck, I think. Yeah. No, here, these are supposed to be for us to change if we want, okay? I had a conversation with Kip about this a night ago or something like that. And I have some worries, which I'm curious how you think about them.
Ray has to report to the National Science Foundation about what he thinks the prototype can do.
Sure.
He can't overestimate the antenna's sensitivity, but he has to be encouraging at the same time. The fate of the large $78 million antenna depends on the progress of the prototype.
This is too good, this is too lousy, and that's much too good. In other words, what I'm telling David, I don't want to get caught. That's the statement right there. Okay?
Yep.
And I want to get that to him. I think Kip agrees with that. And I think Ron is not being asked. Okay?
That's the most sensible thing.
Yeah. Okay. All right. Let me get it. Yeah, this. If you approve of that, I will send it to to Dreamer.
Today, Lyman and Andy are taking their general exams. The exams last for 5 hours.
Oh, yeah. When's it gonna get warm?
Hey, let's get some beer.
Hey, you wanna do that?
I don't know yet.
I think you're psyched, eh?
You
getting psyched?
Yeah.
Are you actually working effectively, or are you just sort of fucking around?
Andy just found out he passed the exam.
No, I made it.
Lyman still doesn't know yet.
Record Lyman when he comes in, just so you can get the expression on his face and stuff, that raw. Jeez, I wonder, eh?
All right, there it is. Did you do it or not? No. Oh, Lyman.
I know.
Let me just trying on each other's shoulders here.
Here, have a beer.
I need some beer.
Have a beer.
Oh,
I flunked twice, okay?
Lyman! Part 2?
I flunked everything. I mean, me personally.
Music
Yeah,
one.
I know what we're talking about.
Yeah, right, okay.
I can see it in your eyes.
It makes me feel great. If I could only have flunked part 1.
The hardest part of the experiment to solve is to get rid of noise and vibrations.
And I told the most likely time it was quiet here was on Saturday nights. We're going to close the street down. To get the cops to close the street down. The guys got to come with an authorized sawhorse, put it down on the ground, and stand there all night with paper.
Rent a costume. Rent a cop costume.
Rent a cop, that's right.
This is the last meeting before the first run of the experiment.
I mean, it's millions of dollars from NSF is one thing, but Two cops staying out all night.
Looks like it's bad, and then we might even ask them to close down Main Street. I mean, I have enough balls to do that. That costs a lot more money.
How do you figure a bigger experiment?
I mean, it's big enough to have the roadblock.
Psychological?
Pardon me?
Psychological?
No, for the vibrations
Oh, vibration. Environmental.
from the trucks.
Yeah, environmental. Oh, I see. Oh, all right. That's understandable.
Labs in Germany and California are on the air right now also. Everybody is running their data according to an atomic clock for perfect synchronicity.
How long are you gonna run?
Until we drop.
Oh, like
Maybe it's later.
hundreds of tapes worth.
Hundreds of tapes, yeah.
Hundreds?
We only have 70. It might be.
You have really 70?
Yeah. We get 25 tonight, that'll be. Yeah. We can take probably about 3 an hour.
Really?
Well, it's now
Tops. That's when she's warped right out.
I'm just freaking out and having.
Right?
No, actually, it's long term. I've just been kind of on and off with science and my life and what am I doing and why did I get a job and why am I doing research. And I just have to stop and
Do you
take
need
a
something like
rest.
data? Like results? Would that help?
No, like a degree and a working MG and a drive out west or something. That's what I need. No, short term I need data.
What's the big game here? What's the object? I don't know. Making people happy maybe is important. It would be nice to think that. But then the whole problem, I think, just commutes itself. It gets projected onto a new space. And what is making people happy? What's that mean? I mean, you want to know the bottom line. How do I win this game? It's all the same questions.
The early data already looks promising.
Is that real?
I don't know.
Huh?
I don't know. I just sort of looked through them real quick.
Now look at this. Almost a factor of 10 lower than all the others. You don't believe that?
Certainly, it's enough to convince funders to build a new lab after this one is destroyed. Scientists don't expect much from gravity wave science these days. Particle physics is all the rage. Still, Ray wants to preserve his antenna. Just in case.
I may have a little bit of trouble getting it off. It's coming, it's coming, it's coming. Oh my, look at that. Ah, there we go. Yeah, well, that's had a pump on it. Now, you want to talk about that thing? Sure. Should I pull it over? Sure. Let's pull it over, yeah. Now, what was this? Whoa, all right. We didn't know how long to make LIGO to begin with. It was made 4 kilometers because of
Well, there was 40 meters. The 4 was because Caltech liked 4.
This time, they're going to make the antenna 40 kilometers long.
No, that's just a little bit of a joke. And we know now that we should have made it longer.
So what do you think of this field? Like in 15 years from now,
you know it as well as I do, but it would be absolutely fascinating to find out how we got these pairs of black holes. That's a challenge that we have now discovered. And that to me is it's cosmology on near terms. It's not the cosmology of the cosmic background, but it's cosmology that is, how did the universe make progress?
Yeah, because...
And we are 10 to the minus 6 and 18.
Yeah.
Okay? They think that that's 50 years away, but it's going to be done.
You think?
Oh, it's got to be done. It's one of the most interesting experiments in the world.
Thank you, MJ. This is, I don't know, every time I see it, it's always better. Thank you.
Oh, my goodness. I want to tell you a little bit about cosmic background studies that we did with Ray. And so it's mostly pictures of people, because from my experience of Ray, that was the most important part. He cared so much about people all the time that you could feel it. So I just want to start with a few step back in time. What was physics like? This was what I got into the cosmic background business in 1970. Ray was already in it but I was a graduate student. I just found a thesis project to work on. So in those days, we didn't have lock-in amplifiers in boxes. You built them yourself. The fast Fourier transform had just been invented, although it turned out that Georges Lemaitre had invented it years before and nobody noticed. And that's actually documented. You could find it. There was no pocket calculator, no such thing. The advanced laboratory computer was a PDP-11 that ran on a paper tape. And if you were really lucky, you could get it going. And our detectors were made mechanically with a soldering iron and little bits of solder and tiny wires. So stepping back in time, it's hard to imagine what we have accomplished since then. Ray would have told you all the people that came before. So I have a few pictures of people who came before us. Friedman solved Einstein's equations and said, the universe could be expanding. Lemaitre said the same thing. And Einstein said, well, that's wrong. A lot of people know that story. George Gamow was working on the Big Bang story too, and after the World War, and neutron physics was now beginning to be well appreciated, unfortunately. And he was working with Herman and Alfred there in the picture, and they had written work on predicting the cosmic microwave background radiation, 1948. And just to give you a sense of old times, Alfred's thesis defense said, I think George Washington U had 300 people came to watch the presentation in the big auditorium. But did anybody go measure? Nope. Actually, Joe Weber was told it was impossible, so he called up to complain to me later that he was deprived of another Nobel Prize because of that. Rashid Sunyaev had many predictions, and Jim Peebles was one of the people already working about the statistics and calculations of the expanding universe. So when we wanted to get started on the COBE satellite, of course, we called him. How did we get started? This is a sketch of our first idea of the Cosmic Background Explorer satellite. I think it might have been my sketch. Anyway, it embodied the ideas of Ray and Dirk Muehlner. Pat Thaddeus was part of our team in the very beginning. He was at Goddard Institute in New York at the time, where I was. So it had the basic ideas that we eventually flew, and a baffle to protect all the instruments, a helium cryostat, a microwave radiometer surrounding the cryostat, and a spectrometer down inside, which is very much similar to what we flew in the end after many changes, including designing it to go up on the space shuttle and then redesigning it not to go up on the space shuttle. But 1974, we had all the basic ideas. And we said, we're really smart, we know how to do this, which was false. We did not know how to do it, but we could do it, and that was sort of the aim of our plan. We said, we're really smart young people, we could do this. And we did not have any idea how hard it was going to be, but only 15 years later, it flew. So here are the people. There's Pat. He was my postdoc advisor in New York at Goddard Institute for Space Studies. I don't have a picture in here of Paul Richards, who was my thesis advisor. The way this all got started for me was he started a program to measure the cosmic background radiation working with Charles Towns and Mike Werner, and I got a chance to work with them, so I said yes. Then that thesis project actually didn't function quite right, so I got to write a thesis about a non-functioning apparatus that was, however, significantly influenced in its design by Ray's experience already. So anyway, this is the team of 6 scientists that were, well, not, I guess we had that's 7, isn't it? This was the team that was chosen by NASA headquarters from the results of 3 separate proposals that were sent into NASA in 1974. So anyway, okay, well, we're going to go ahead, and we figured out what to do. So what did we, well, first, I want to show you the pictures of the other people that joined us. This is the whole science team coming up. And I count altogether 6, at least, of the team members are there because they were directly influenced by Ray himself, and at least 5 of the rest of us. So you'll see them here: Ed Cheng, Steve, Rick. What happened to Chuck Bennett? Didn't I? There he is. Chuck was recruited into our project too by Ray. Who knew? So. Anyways, because of that, we have very strong East Coast orientation and a very powerful team of people who knew from people building stuff in the laboratory. So what did we fly? This is what we flew. It looks a lot like that picture that I showed you at first, except it has bigger solar panels, and instruments in the center protected by a sunshade, and in the same orbit that we had in mind in 1974. So it operated for about 5 years, and this is the thing that Ray and we all conceived and built up. It's a differential instrument, double differential, and that's what gave it its power. Number 1, it's differential comparing 2 inputs that should match, and number 2, it's got a movable black calibrator, which is a radiator that is supposed to radiate exactly the same way as the sky would if the Big Bang story is correct. And so it's a polarizing Michelson interferometer, which was brought to us. Actually, it's an invention of British guys, Puplett and Martin and Puplett. And Paul Richards came back from a sabbatical with that idea. So that was what we flew. It was pretty tricky to make it work, but anyway, it did. So what did we find? We got our famous spectrum. I showed this exactly 8 weeks after launch to the Astronomical Society, and people who were there then were impressed that everybody stood up to cheer. I thought, well, doesn't everybody know that's the right answer? Because I could not possibly imagine how the universe could have done anything different. That's my amateur theorist. I talked to Martin Rees, and he said, actually, there were a lot of things that it could have done that it didn't do. So that he was really surprised by that perfection. So the error bars, there are 1%, and we didn't actually know what they were because we hadn't finished calibration, but at least we knew their error bars were small. So anyway, that's our big contribution to the perfection of the expanding universe story. And we have the temperature down to less than 1 millikelvin due to Dale Fixon, who's here. He can tell you more about how we did that, but it's least squares fitting on steroids. So that's our major result. Here's our other instrument that made the news. This is a differential microwave radiometer, and it's got 2 antennas and a ferrite switch that switches back and forth between them at 100 hertz. And we spin this apparatus around on the satellite, so we measure all possible combinations of 2 points 60 degrees apart on the sky, and another least squares fitting on steroids. Hundreds of millions of data points are compressed into a map. And we got these maps, which made physics today. So after that, we all got to go to Stockholm. And one remarkable story about that one is Ray went, of course, too, but he didn't want to get a white tie and tails outfit. So he did not get to have the banquet with the king. He went and had his banquet with the spouses. And I think maybe he had more fun. Anyway, that's the short story of what we did. And Mark can tell you another one because other things happened also. Mark participated here at MIT and then went on to UBC. Mark.
How does this work? Great. Yeah, hi. So I guess I was Ray's last CMB grad student, is that right? Or maybe Andrew Jeffries was. I started, he had this idea that in heavy atoms, an electron spends a bunch of time in the nucleus and there should be a parity violating interaction. And so my first experience with Ray was combing through spectroscopy tables trying to find a match between noble gas transitions and heavy atom transitions to look for, because he had this beautiful clean laser system in the back room, which was an instant thesis. So that completely didn't work, and I switched to working on the cosmic microwave background. So there's a stack of measurements that started by Dirk Milner and Ray Weiss, and then I joined that to try to measure anisotropy of the cosmic microwave background I'll tell you a bit about. A striking thing here, certainly at the start, is like Ray's work on the spectrum, where he's trying to see, is this a power law or not? And there was no discussion of what would give rise to a chemical potential or Comptonization of the spectrum. It was kind of model-free. What can we measure here? We didn't have a working model of what we were trying to find in the anisotropy. There was a dipole moment, which could be from our motion. So we were looking for higher order moments of that couldn't be from our motion and would be about the universe. And we did not, at the start, there wasn't a working model of what to do. And that's part of why these horns have a 20-degree field of view, which is poorly tuned to what you might like to measure. But so the instrument is this, and here's Ray tuning up a bubble level so that when you hang it and spin it, the two horns are at the same elevation angle. And the system is this. It's a bunch of bolometers in a cryostat coupled with a chopper, and it's a differential instrument, and it spins, so it's like WMAP was later, like the DMR were later, like WMAP is a differential instrument spinning to scan the sky. In '76, so it started out with these indium and timonite bolometers, which were a solid state thing immersed. We started building modern style detectors with tweezers. Ray and I built them tweezers and a microscope and gluing things about the size of a chunk of, a few hundred micron cube. And then Pat Downey made these detectors, which were order of magnitude better, and that really was sort of transformative. Here, we didn't measure higher order moments successfully. We did measure a dipole moment with enough precision. Here's the dipole moment measurements plotted as antenna temperature. So at high frequencies where we took the data, the power drops off because the thermal curve is running out of power. But if you ask what underlying thermal curve are those dipole moments consistent with, you get that it's, 2.8 or 3 Kelvin. The striking thing here is just almost precise enough to be interesting. If you have a spectrum which is rising, there's a term in how bright the dipole should be, which goes like the slope of that spectrum. So I've shown as a dashed line there the rocket distortion. Herb Gush had flown a measurement getting a distorted spectrum. The gang at Berkeley had flown a thing with a distorted spectrum. And it's 2 sigma discrepant with our dipole moment measurements. Not enough to say it was flat out wrong, but we were kind of, anyway, we needed this extra factor of 1,000 or more that John has pointed to that came after. The other discovery here is that the galaxy was just really bright. So this is, I'm calling this the polar antenna temperature. We just fit secant, so the free parameter is what's the brightness perpendicular to the plane. You notice the dates on the data on here. So these are the MIT balloon measurements of the brightness. But when Dirk and Ray started, IRAS hadn't flown. We just didn't know that the galaxy was so crazy bright that you couldn't perform anisotropy measurements without measuring the whole sky and measuring it at a bunch of wavelengths, and measuring it with the angular resolution you need to take out, to model and take out the galaxy. So what we learned really is that you needed to build COBE to make progress, which sadly we didn't know at the time. Can I delay a minute? Yeah, I'm gonna. Can I tell a funny story about how? What? I have two stories. One is the last slide, and one is I want to tell in front of it. Anytime you do a measurement with Ray, the first thing is to calculate what the noise is going to be. So I'm sitting in his office working out. I wanted to measure the spectral response of our radiometers, and the phone rings, and Ray says, yes, yes. So what did you decide? Well, I'll be goddamned. And he hung up the phone. And so this is how he found out, that COBE was funded. The story goes like this. He reports to me that the guy said, we've been deliberating. And Ray said, yes. And he said, and we've made a decision. And Ray said, yes. And Ray said, what did you decide? And the guy said, I can't tell you. I need to notify the rejected parties. And hung up. So one thing I remember really strikingly, which for me has a bunch to do with who Ray is. The name for a candy bar in the lab was a Zork. And it's not just a candy bar, it's, you need a break. You're gonna walk down the hall to the vending machine, you're gonna buy the best of whatever meager choice there is, you're gonna walk back and still be thinking about what isn't working. So that's a Zork. And it comes from this gang, Zacharias, Oppenheimer, Robbie, and Charlie Lauritsen, and these horrible McCarthy times. And it took me forever, actually, to realize that Zacharias was Ray's supervisor and my dad's thesis supervisor. But it was a wonderful thing for me, part of learning how to be a physicist, that to have as heroes people who stood up against McCarthyism. And that was the sort of lab culture and lab hero. I'm a little afraid we'll all get this chance again. But reaching back to people, part of being a physicist is having the courage to know what you know and know what you don't know and say it out loud. And that was part of Ray for me. Thanks.
Good morning, everyone. My name is David Kaiser. I teach here at MIT. I teach physics and also the history of science, and I'm really very honored and delighted that Peter and Lisa invited me to help put this together. Enormous share of the work was done indeed by Lisa and Peter, but I'm glad to be able to help out a bit. So I'm going to share our next session, which is on big questions in astrophysics. We'll answer all those questions in just 1 hour. It's really amazing. We're going to do that. We might have a few questions left at the end. I'm going to invite 5 speakers up one at a time. They'll present from right here, so I'll introduce them before each of their talks, and hopefully we'll have time for some at least brief questions for each of the speakers after they've spoken. So I'll jump right in. The first speaker is a very dear friend and colleague of mine, Scott Hughes. Scott is a professor of physics here at MIT. He's also serving as interim associate department head, which is why he always has a smile on his face this semester. Scott received his PhD in physics at Caltech, working closely with Kip Thorne. Following postdoctoral appointments at the University of Illinois, at Caltech, and at the Calvi Institute for Theoretical Physics, he joined the MIT faculty in 2003. He also has served as the head of the MIT Astrophysics Division for several years, between 2019 and 2023. Many, many, many awards for his research and scholarship, and I'll say at the beginning, if I read everyone's set of awards, that would fill much more than the 1 hour. So I'll just take my word for it. Scott has done extraordinary work, recognized as such by the community. What you might not know, though you'll see why in a moment, he's also received many, many of MIT's highest awards for teaching. One of my favorite bits on the entire internet, and I've read the whole internet, is a short video of a student exclaiming, literally bent over and out of breath, that Scott Hughes is the GOAT, and that's when I learned that stood for greatest of all time. that empirical observation has not yet been disfavored, and I think you'll see why. His research focuses on general relativity, including applications to gravitational wave physics, black holes, and strong field gravity. His talk for us today has the compelling title, General Relativity Just Works. Scott.
All right, so I am going to tell you today about the way in which the LIGO discoveries have basically convinced us that general relativity is just, that's where you got to start from. It just works. It really gives us the most compelling framework for understanding strong gravity and all these events that we are measuring. Prior to these discoveries, people were thinking about a lot of things, and basically, as far as I'm concerned, along with the ether, they're gone now. When Ray decided to tell me about this, he had an ulterior message, though. And I think the real point of my talk is going to be that ulterior message. So let's go back. Prior to 2015, we had a lot of data about gravity at that point. We knew about general relativity, but really the most precise stuff was in the weak field, places where the sort of Newtonian field strength was much less than, significantly smaller than the speed of light squared. We also knew about it on cosmological scales. There was information that we had about strong field gravity, areas where GM over R is a significant fraction of the speed of light, but it tended to be a lot less precise and a lot less direct. And as a graduate student studying general relativity, this was something that really interested me. Could we do better than this? Can we really dig into this? And I would go to Kip to talk about this, and he'd say, well, of course it's right, Scott. You don't need to worry about this. And so I went to Sturl Finney and said, do you have any other anything you can contribute to this discussion? And he actually gave me what he considered to be his top 7 list of why black hole candidates were in fact the black holes of general relativity. This is where I learned the difference between black holes, those things that I look up in chapter 33 of MTW, and black hole candidates, the things that astronomers were looking at up in the sky. And so you go through this, and here are 7 things that all pointed to the fact that we had to be, these objects were the black holes of general relativity. They were very luminous and they were rapidly variable. That pointed to a process that converted matter to energy with an efficiency better than 1%. Hard to do that by any nuclear process. It had to be some kind of gravitational process. They had short lifetimes that implied mass was falling onto an object that was very strongly gravitating. There were jets that were formed that all implied a relative potential well. There were line features that suggested orbits of very relativistic matter. There was variability that told us that these things had to be confined to a size that wasn't much bigger than GR's prediction of an event horizon size. There was a thermal spectrum that told us that these things must involve matter that's crammed, again, down to a really small region like that. And in many cases, it looked like there was no surface. No surface says probably it's got to be an event horizon, though of course that's evidence of an absence rather than absence of an evidence. And so you could argue on there. This was interesting. I kind of thought, okay, GR's probably right. And Sturl said, wait, there's a rebuttal. If you had one good reason, you wouldn't need 7. And so that kind of made me realize it would be really, okay, now I see why we're doing this. We need to move forward and look at these kind of things. And indeed, that led me to get really excited about binary black holes. And all the way back to 1994, where a certain member of this audience at least had a good cartoon of these things that we could think about, people like me and Kip and many other relativity friends in the audience here, we loved binary black holes. And I think fundamentally, we would give you all these reasons about the beauty of the field equations and the importance of having a pure mathematically constrained theory, but to be blunt, a lot of it is just because we're kind of lazy and we don't want to deal with fields and matter. It's just nothing but space-time. It's nothing but gravity. It's a beautifully clean problem. And we kind of knew, as I say here with this, if we now compare this to what numeric relativity can tell us, Kip's cartoon from 1994 is grossly correct. Some details are not quite right, but we sort of knew that we had this in-spiral merger ring-down shape of things for a very long time. And we knew that if we were able to determine this and precisely map what we are measuring here to what the Einstein field equation tells us, we were going to be able to learn a lot about these events, test the nature of gravity, and use it as a tool for astronomy. But what if GR wasn't actually giving us a good description of strong field gravity? When I was a late graduate student, a postdoc, and I would talk about these things, this was a rejoinder that many people would say to me. They say, well, you're kind of extrapolating beyond where we know things. Are you really that confident about it? If general relativity doesn't give you gravity deep in the strong field, are you even going to really have black holes? And I'd give them Stirl's top 7 list, and they'd say, yeah, that's 7 okay reasons. Really wish you had one good one. Would the in-spiral be any different? Would the system even produce gravitational waves? Well, at the very least, we knew of one very strong empirical constraint. Thanks to binary pulsars, we at least knew that whatever was going on, gravitational wave back reaction, as described by general relativity, worked pretty well. So that gave us a lot of confidence we were heading in the right direction. But even when presented with something like this, people were saying, yeah, but you're really kind of pushing beyond what we know. And in fact, when I was a postdoc in Santa Barbara, I had an unnamed person tell me LIGO would measure nothing, because they were quite confident that what was going to happen is that the gravitational waves, they back react on, they're generated just like GR, they back react just like GR, but after propagating some distance, and this person was very sketchy about what that distance would be, they would propagate off brane, and they would never be measured by any of our detectors. And I what do you do with that? So I said, okay, fine. And then of course, I occasionally would talk to people like Ray, and they'd say, oh, just build the damn experiment and measure it. Come on, that'll shut all these people up. And sure enough, that's what happened. So this immediately validated general relativity as our theory of gravity. Okay, it was not just strong field, but it was dynamical. It covered every scale outside of the event horizon. As we move forward, if I think about this from a GR point of view, at this point, we're really not saying, are we testing general relativity? General relativity has been tested, it works. But we're able to look ever more finely at details and structures and make it more precise. I love this idea of chasing after these sort of details here, even though it's almost fundamentally become a null experiment, because so much other science comes along with that null experiment. As we discovered just over the past year, this near twin event to the first discovery really looks a lot like it, but we can measure it so much better now. We see a lot more structure in the spectrum of the late gravitational waves. You see the in-spiral so much better. This is the kind of thing where this beautiful science is coming from. So now, my Ray story. As many people here know, I am not a part of LIGO or the LVK, but I have been LIGO adjacent since I started my PhD in 1993. So what this meant was that following this discovery, as we all know, there were a lot of rumors that were circulating. And people would say, Scott, what's going on with this? And I could very truthfully say, I don't know. And so while all that was going on, of course I was curious, but I knew what the stakes were, and so I was very happy to keep my mouth shut. In fall of 2015, probably around late October or so, Ray decided I needed to know a little bit more. And he came over to my office, and he said, Scott, the door needs to be closed for this. And he sat down on a couch in my office and started telling me about what was going on and what people had learned. He was getting quite worked up. And I tried to interrupt him because someone else, who shall remain nameless, had already given me a briefing. And so I said to him, Ray, before you get too into this, I think you should know. And he said, Scott, this is very difficult for me. Please, just let me say what I've got to say. So I said, all right. And he started going, and I could really tell where he was going. So I tried once more. I began to interrupt. And he finally said, damn it, Scott, I've told you this is really hard for me. Please, let me get this out. So finally I said, fine. And I sat back, and I'll describe why he was getting so worked up in just a moment. He kept talking, and he talked for maybe a minute and a half. And then he finally, the whole time he's doing this, he's looking at a table in my office. And he looks up, and he sees the look on my face. And he must have seen I had a little grin. Because he stopped, and he said, you son of a gun, you already know, don't you? And if you know Ray, you know he didn't actually say son of a gun, but we'll leave it there. Why was he getting so upset? Well, the thing which he was trying to say was that he knew there was something amazing going on. And he also knew that a lot of people had a lot riding on that, what amazing stuff that was going on. And he wanted me to understand why everything was in such lockdown, why I and a few other people were kind of being kept out of the loop, and he didn't want us to be hurt by this. And what he really wanted to tell me was all of my friendships with everyone were more important than the discovery. That was the thing that really was making it difficult for him to get this out. So my message is he deserves every accolade for what, he Ray really pushed the boundaries of what we can measure, what science makes possible now. But what I'm going to cherish and what I will carry is that what mattered to him more than anything was this deep concern that the friendships, the love we all have, is the thing that we carry forward. Thank you.
Scott, thank you so much. I'm getting the signal we should move on to our next speaker. We'll have time for chat. Okay, why don't we take one or two quick questions, and we won't bother passing mics. We'll just ask maybe Scott to repeat the question for folks who might hear it. So are there one or two quick questions for Scott Hughes? If not, we will have a coffee break and plenty of chances, of course, to chat more. Yeah, please go ahead, David.
Yeah.
Especially at the end of it. I want to ask you a science question. At what point, if ever, do you think gravitational waves will start to create cracks in the evidence?
So the question, sorry about that. So Dave Rice is asking me, whenever do I think gravitational waves will show cracks in the edifice of general relativity? My former postdoc, Nico Yunus, is now a director of an institute at the University of Illinois that is, one of the questions they want to know is, what can we look at as the foundations? What kind of observations might lead to the answer to your question? And I was asked to be the gadfly in a discussion we had looking at this question. I'll give you the answer that I gave then. I said that I would bet a month of my salary against a month of the salary of a graduate student who asked this question, that we will not have observational evidence of this in the lifetimes, or the career lifetimes of everyone in that room at that moment. And that included graduate students who were at that point. And I would love to be wrong about that, but I suspect that the kind of features that you're looking for are not necessarily going to be ones that astrophysical sources are the right ones to test for that. Certainly not with gravitational wave observations. Maybe something different will happen. We could have an entire conference on this topic, but that's my quick gadfly answer.
Thank you, Scott. Let's thank Scott again. Terrific. Our next speaker this morning is Vicky Kalogera. Vicky Kalogera is the Daniel Linzer Distinguished University Professor at Northwestern University, where she also serves as director of the Center for Interdisciplinary Exploration and Research in Astrophysics and director of the NSF Simons AI Institute for the Sky. She's also, of course, a leading astrophysicist in the LIGO scientific collaboration. Vicky completed her PhD at the University of Illinois at Urbana-Champaign and then held postdoctoral appointments at the Harvard-Smithsonian Center for Astrophysics before joining the faculty at Northwestern in 2001. Her research focuses on the astrophysics of compact objects, gravitational wave and time domain transient astrophysics, and advanced data analysis and inference methods. And her talk today is entitled Listening Carefully, What I Learned from Ray Weiss. Vicky, thank you.
Okay. I uploaded 2 more versions of my talk while Scott was talking, so hopefully we're going to get the final version here. It's really an honor. This is what I use, right? An honor to be here. Looking back, I met, I had heard of Ray Weiss years before I actually met him, but I met Ray in 1999. And I could never have imagined at that time, even for years later, that my path would cross all these steps, all these phases, and intersect with Ray so much. I owe him quite a bit of gratitude, and his mentorship has been extremely important, as I will try to give you a glimpse here and there at what moments Ray was really instrumental. So let's get started. So yeah, I guess as an astrophysicist, I got to pay attention and listen to the universe. But really, what a lot of my years, I was listening carefully to what Ray was telling me, either directly or indirectly. But loud, always loud. So I'll try to give a mix of a bit of my three times in these, I guess, more than 25 years that his voice was quite loud in my head. I first met Ray back in '99 when there was a coincidence of things from X-ray binaries to Ramesh Narayan and David Spergel and Joe Taylor asking me to work on something I had no idea about, but they thought I had an idea about, so I said yes for a committee of theirs. And then that brought me at a seminar at MIT, a lunch seminar, and that took me to a radio pulsar workshop in Aspen, and that took me to a gravitational wave a conference in the French Alps where Bruce Allen was there, and Bruce jumped and said, "You should join the LIGO scientific collaboration." And I said, "What? You guys are all particle physicists. I'm an astronomer. I'm not a gravitational physicist." So then Dipto Chakrabarti, who was a close friend of mine and a postdoc at the time, and I don't know if Dipto is in the room, but if you are Dipto, raise your hand. There he is. He said, "You should go and talk to Ray Weiss." And of course, I laughed again, as I did often at the time at Dipto. And I said, no, I shouldn't, but he insisted. So then I wrote an email to Ray, and Ray responded. So then I found myself going to building 20 in his office that Peter already pointed out, and shaking, I entered his room, and there was a table. That's how I remember it. I don't know if it's true, actually. Memory is very deceiving and misleading, but I remember entering, and there was a table to the left, and Ray sat at the table, not at his desk, and made me sad. It felt exactly like this. He said, "Sit here." You know, was I a dog or a postdoc? Not clear. And so he asked me a lot of questions, and it was going in the direction of, yes, you should join, like an order. But at the end, he asked me a question that I'll never forget. The question was, you should join. He was caring and encouraging, but really at the end, he smacked his arm on the table and he said, "But you should know something, Vicky. Before you join, you need to think about something. It's not what the collaboration is going to do for you, it's what you as an astrophysicist is going to do for the collaboration." And by that time, I had kind of said yes, and then that sentence was like, I think I want to say no. But I felt trapped, so I got up, thanked him, and left the office. And so that was the beginning of my relationship with Ray. Then I joined the first collaboration meeting, which in hindsight, I realized it was in Florida, I think. And it was the beginning of the LIGO scientific collaboration, or at least that's how I remember it. And I found this document yesterday that basically Ray was the spokesperson, and this structure was laid out. So there was charter and R&D and scientific operations and governance, and some membership was being spelled out, and then different groups were being spelled out, data analysis group, and my first thought was, I'm not a data analyst. I don't know what I'm doing here. And then astrophysics, ACES, for those who remember. So I thought, okay, astrophysics is mentioned. That's what I'm going to join. And I had more discussions with Ray at that meeting. There were criteria about detection, so that made us all very optimistic back in 1999. And I had another discussion with Ray. And Ray said, "Look, Vicky, I'm the boss." Not me, him. I'm the boss, and the reason I want you in the collaboration is because you can bring astrophysics guidance to us. So we don't need you to do data analysis. We just need you to think about the sources and give us guidance and make predictions. So I thought, I can do that. That's fun. I might as well do it in connection to people who are doing the real searching. Then later, Dave Reitze was the spokesperson, and he changed the story on me. He told me, you're in the collaboration, Vicky, you need to be doing data analysis. In any case, I also found this letter that's part of the same document where Ray signed. You can see the dates, and you can read the plan, the criteria. I would like to consider a strategy, et cetera, et cetera. So, based on his advice, what are you gonna do, Vicky? So my first years were, I was having fun. Predictions, merger rates, source properties, etc. But then data analysis entered my life, and it was great. Thank you, Dave. I decided, searches it's going to happen. The signal will be there. We're going to find it, but I want the astrophysics. So with a few other collaborators, especially Alberto Vecchio, we started building up the Bayesian, and an E is missing there, Bayesian parameter estimation. And then eventually, who knew? I even got into detector characterization, but eventually, of course, astrophysics is my passion. And that's where I continue working on. So it's been quite a ride. And then we reached the detection. And the thrill of what observers feel coming still, I still feel like a theorist, and feeling that thrill of discovery. If you're a theorist, and I mean, most of you are in the collaboration. Scott, you are not in the collaboration. Deep Tone, not in the collaboration, but you're an observer. You have that feeling. That feel of a discovery, the thrill is unique, no matter what theory you're doing. So I really feel privileged to have been at that time in the collaboration. And going back to Ray, I can't believe, Nergis may remember, but I can't believe that at a critical time early on, before anything was public, I directly accused Ray in front of other people that he knew it was an injection and he wasn't telling me. And I remember I said publicly to a few 10 people of all at MIT, I said, if you did this and it's an injection, I will kill you. I regret certain moments in my life. So it was a thrill to be in the conference room with Ray performing. And then the fact that I would ever see Ray in a tuxedo, that's another shocking moment. Okay, I may transition into just hitting a couple of where are we now from the astrophysics perspective, what do we know for sure, and come back to one more important moment in terms of Ray's teachings. One source, hundreds of sources. Who would have imagined on the kind of time scale? So now, of course, it's my paradise. That's why I joined back in '99. So lots of study. Still, we cannot figure out how these things are formed, but that's why theorists are happy. Plenty to do, plenty to hypothesize and imagine, but we have data. And now we have data not as individual sources, but now we're doing population studies, which is where I started from, and most people made fun of. So we need population studies to figure this out, and my group, my collaborators, many other groups at MIT and elsewhere, we're studying the population characteristics directly from the data or a priori from simulations. What are the 1 minute, haha. So, punchline. The data give us clear features, okay? I'm not gonna go into the details, but we know we have peaks and bumps and something else that we can't even name, and maybe something else at higher masses. And this is just the masses. Are these features real or not? Some of them are really real. We always talked about a low mass gap. Well, gravitational waves have made it clear now against electromagnetic astrophysics. There is no low mass gap, okay? Why? It will take me more than a minute to explain. In addition to that, we are having from the data some really concrete information about the formation channels. The lower end population of black holes have characteristics in the mass ratio and the spins that I'm skipping that are very consistent with isolated binary evolution, while this peak at 30 or 45 solar masses has characteristics in mass ratio that is inconsistent with isolated binary evolution and consistent with dynamical processes. Again, not much time to go into the details, but some extra evidence here in comparison with theoretical models. And the theoretical models is the red curve here, which is clusters, inconsistent with low masses, consistent with higher masses. Isolated binary evolution models, clear peak at exactly where the data is showing it. Okay. A little bit about the future. In 2022, I had an exchange with Ray on his birthday. And I gave him my wishes, and I hope you're doing something fun, etc. And lots of thank you. And he writes back, and I said, thank you. He always called me a card-carrying astronomer. Many of you heard this. At the first meeting, he would introduce me, holding me by my clothes. I don't know if any of you remember, but I know he brought me in front of UKIP and said, meet Vicky, card-carrying astrophysicist. Pay attention. And then he said, I heard the rumor, you might be leading an MPS group, third generation. I wouldn't have said yes if it were not for Ray. He kind of made it clear that you better say yes, Vicky. I don't care how much work it's gonna be for you. You're gonna say yes. It was a lot of fun. But what was nice about Ray is at that time, 2022, he was as passionate about the next generation detectors as he was 25 years later about the first detection that was always around the corner. It was hard when you saw that enthusiasm in someone so much more senior than you to sit back like a kid and say, well, I'm not sure, this is too far away in the future. So that was very inspiring for me always. He also took me years before this, after the discovery, he would always drag me at every presentation he needed to make to important, he had an expression, not very positive expression about certain people, to convince them that they have to pay attention. And he would say, you have to come and you talk about the astrophysics. And I would say, but Ray, they're only paying attention to you. No, you need to be there because I cannot talk about this, the astro stuff. So we did a lot of trips together. And in some of these trips, he would get very upset. And he would get very agitated in private, and he would swear like a sailor. And that always reminded me of my father. And that was another connection. My father was not educated, he was not a scientist, he was a high school graduate, but there was something in Ray that reminded me of my father. His intensity, his jittery motion when he was really worked up, and how much he swore with no limitation and no hesitation. And in those moments, it was like, oh my God, hello, Dad. So that was always quite something that put me in like, I was a child again. All right, so we did the report. We talked about piano a lot. I didn't play piano. My whole family plays the piano. And I always told him, I just listen, Ray, I just listen. He kept insisting that I should take on the piano. So around 2022, after his birthday, he said, there is a grand piano in your future, Vicky. I still disappoint. Here he is in our home with our children playing the piano while I was gearing up to think about the next generation, Cosmic Explorer. And while the committee was working, thank you to the committee, I couldn't have done without them, he kept sending me ideas in detail. JWST observations, here's why, this idea is from Stephen, but I have been thinking about it. You should talk about this with the committee. And after I presented and it was all final, he did give me the pat on the back, and I felt, oh, I made my dad proud. And then he did say, furthermore, you answered the only possibly hostile member of that committee masterfully. Thank you, Ray.
Thank you, Vicky. I think we'll move on only in the interest of time, but that was really absolutely marvelous, and we'll have a long coffee break, several throughout the day. Thank you, Vicky. Let me go right on to our next speaker, Professor Bernhard Schutz. Bernhard Schutz is one of the founding directors of the Max Planck Institute for Gravitational Physics in Potsdam. He completed his PhD at Caltech, working with Kip Thorne. It seems to be a pattern. Following positions at Cardiff, he became director of the Division on Astrophysical Relativity at the Max Planck Institute in 1995. He's helped to lead the field, as of course we all know in this room, of gravitational wave physics for both ground-based and space-based observatories, as well as nurturing the pursuit of numerical relativity. He founded the renowned open access journal series Living Reviews, including, of course, Living Reviews in Relativity, and among many, many, many other publications, the author of the leading textbook known to all of us, A First Course in General Relativity. His talk today is entitled An Abundance of Binaries. Let's make sure we exploit them. Thank you.
Thanks very much. I've made a talk with just pictures, and so I put notes down here. So if I look at my notes, it's because I don't want to miss things that I really wanted to say about Ray. When I remember Ray, I remember him as a human with so many different sides to his personality, and I think that's coming out already in these other talks. He was certainly a driven scientist, but science for him was not an ego trip. He was pretty much just as happy to crawl around in a vacuum pipe looking for leaks as he was to go to Stockholm and receive a Nobel Prize. Almost as happy, maybe. But the science was there, but it wasn't his trip. And of course, people mattered. That's the guy that started out. That's around in the early part of his lab work. I didn't meet him that often because I was in Europe, and we were on different continents. But every time I met him, he wanted to know what was going on in my life. Although he didn't wear a badge about it, he was a refugee from the Holocaust. It was fortunate for him that he got out well before, and he was able to come to the US. But he was born in Berlin, and I think it was pretty natural for him afterwards to identify Berlin as a city which was some version of hell. So when I moved to Berlin in 1995 to help set up the Albert Einstein Institute, he had some trouble digesting that. He told me he wasn't very happy about that link in our work to Berlin. But 5 years later, in 2000, he actually turned the tables, and he made what I think was his first trip back to Berlin in order to speak at the third Lisa Symposium, which I was organizing then at the AEI. He also loved music. And we've heard that already. He played the piano. He's very proud of his daughter-in-law, the singer Carla Crisfield. When he learned that my daughter Rachel was a budding singer, he wanted to hear her sing. And he traveled down to Stony Brook to hear her give a recital. And later, after hearing her perform here in Boston with the Boston Pops in 2006, he described himself, and he continued to describe himself, as her biggest fan. He traveled to New York at least 3 times to hear recitals, meaning trips going overnight and so on. And to bring home to me how important it was that I should be supporting her to do her music. For a while, he said he was going to introduce me, and he would bring me into Building 20 and people that I hadn't met before, as Rachel's father. And he did, and he sent me this email, which has the subject, Father of Rachel. That was me. And I didn't take that, and he didn't mean it as a way of diminishing me as a scientist or anything, but just to put things into perspective. Science was great, was important, but then there was music, and I think that was the priority. Okay, but here we are. We're assembled here to talk about Ray as a scientist, not as the musician. And he was omnivorous about physics, and we'll hear all sorts of things that he did. He got the Nobel Prize for LIGO, but we're going to hear at this meeting about his work on Kobe and lots of other things. For gravitational waves, Ray was the person who basically got us to switch from bars to interferometers. And the ultimate outcome of that is we found this universe, as Vicky has been saying, that's just full of compact binary coalescence signals. The bars, remember, would never have seen them. They were just too narrow band. But these interferometers that we've built have just become binary detection machines. We're looking for lots of other things, continuous waves, which I've worked on, stochastic backgrounds, unexpected bursts, and the bursts from, remember, bursts from supernovae were the first things that motivated the detection program. But nature decides, and nature has given us this incredible population of heavy binaries, unexpectedly heavy, incredibly well matched to the detection capabilities of our interferometers. And as we go into the future, we need to make sure we exploit this resources as this natural resource as best we can. So the history of our understanding of these compact binary coalescence detection also has Ray's fingerprints all over it. Ray, of course, is remembered for his work in the lab, but he played a very important role in the development of our understanding that these were the sources that we should be looking for. And that's because his group introduced the concept of match filtering, as far as I know, and introduced the concept of match filtering to our community about data. So in the 1970s, even when these interferometers were starting, the target was bursts from supernovae. We knew by the end of the 70s about binary neutron stars and the possibility they radiate gravitational waves, but realistically, the amplitudes were much too small. This thesis by Dan Dewey, supervised by Ray, contains the beginning of the abstract. Just read that second sentence. This represents a first attempt at integrating the astrophysical features of expected waveforms with a data analysis science for their detection. So that's what we do with match filtering. We use the predicted waveform. And even though this was still aimed at supernovae, the idea was, let's look at supernova waveforms and so on. That idea, and the thesis is from 1986, but that idea was coming out in Dan's work in the early 80s. That idea leaked out, and it wasn't long before we began to understand that we could apply that to the neutron star binaries and lift their very weak amplitudes up into the observable regime. So they became. That was transition, that they became a source that in the end was very important for the science case of the instruments and so on, and now is our most plentiful source. But that started here in Ray's group in this sense. When I learned about the difference that match filtering could make back in the mid-'80s, it stimulated me to look very carefully at the data, at what science we were going to be able to extract from these detections. And it didn't take me long to find out that what they are, what we now call standard sirens, that we can measure their distance, that they convey the information to us about how far away they are. And this distance is the bedrock of our observations. One of the things that, of course, that we're trying to do with it is to measure the Hubble constant, but even things like the mass spectrum that Vicky showed, to separate the redshift effects on the observed masses from the rest frame masses. To understand that, you have to have the distances. So that all came about in the mid-'80s. But of course, it was important then that the only way we were going to get the distances wasn't from a single detector or even from a pair of detectors. You had to have a network of detectors in order to be able to extract this information. So in 1986, I organized a meeting in Cardiff, and it was a meeting for interferometers. All the interferometry groups attended, many of the bar groups attended, and it was themed about, data cooperation, data exchange, cooperation on data. The idea of building at least the mental attitudes about working as a network of detectors internationally instead of just different detector projects. Ray was the chairman of the afternoon session, as you can see in the program, and there are lots of people there. But Ray is off there on the left in the picture. So I was optimistic at that point that we could put together some sort of data sharing agreement, some document. Well, I was over optimistic. We didn't get that for another 10 or more years. But Ray was in there right away, willing to try to persuade people. The binaries that we're seeing, that Vicky was showing us, they're telling us, as she said, that we don't understand binary formation. We particularly the big binary black holes. We have all these different populations. We're trying to assemble a database for measuring the Hubble constant, but we're still just at the start of all of this. And given, I think, Ray's fundamental contribution to so much of what we've done, I think, and it's my theme here in this talk, is we want to make sure we exploit the new detectors that we're building in order to get that kind of information out. And so I'd like to look toward the future, toward 3G. Again, Ray's fingerprints are all over this, the MIT group and Cosmic Explorer. And in parallel, in Europe, there's the Einstein Telescope, ET. When we build these, we'll have sensitivity out to redshifts of 2 or something for binary neutron stars, and to the very beginnings of star formation for more massive black holes that we're seeing. And so how will these detectors help us to get the most out of the CBC population that we're going to be overwhelmed with? So as we're seeing with the current detectors, just having sensitivity isn't quite enough. We need good positions on the sky. We need the network to give us that positions if we're going to extract the information that nature is offering us. That's what I'm concerned, because because at the moment we see 2 different projects. We see the possibilities on both continents of 2 detectors instead of just 1. We see a lot of emphasis on low frequency, going down to the lowest frequencies in order to scoop up the heaviest binaries. But the position information will be up at the higher frequencies, where you can resolve distance between detectors, and that needs to be a priority as well. And the other thing that I'm concerned about is that we don't have a single global project. We still have we still have 2 magnificent planned instruments, and with lots of political problems, lots of difficulties getting money getting approval in both areas. But I just worry that we're not coordinating enough on the global scale. And I think that's one of the reasons why we have not, with the current detectors, we have not been able to extract as much information as we had hoped, or as our sensitivity would make possible. And I just hope that we can solve that problem globally going into the future. And I think that's the right way to honor the memory of Ray Weiss. And so I'll stop there.
Okay, our next speaker in the session is Bruce Allen. Bruce is director of the Max Planck Institute for Gravitational Physics in Hanover, not in Potsdam, and head of the department there on observational relativity and cosmology. He studied physics here at MIT as an undergraduate before completing his PhD at the University of Cambridge, where he worked closely with Stephen Hawking. Following postdoctoral appointments at the University of California, Santa Barbara, Tufts University, and the Paris Observatory, Bruce joined the faculty at the University of Wisconsin-Milwaukee before taking on the directorship role at the Max Planck Institute in Hanover in 2007. His research focuses on early universe cosmology, quantum field theory and curved spacetime, gravitational wave detection and data analysis, as well as large-scale cluster computing, and his talk today is simply entitled Pulsar Timing Arrays. Bruce.
Okay. I'm going to talk about pulsar timing arrays. These are detectors of low-frequency nanohertz gravitational waves. The most plausible source for these is a stochastic background coming from inspiraling binary systems. Now, these two topics, gravitational waves and cosmological backgrounds, are things that I became interested in through Ray, and so I want to talk a bit about how that came about and then finish with a little bit about pulsar timing arrays and the current status. I met Ray on the 14th of September, 1976. He was my professor, my teacher in my first physics class at MIT, 8012, which is a Newtonian physics course. And one of the things that this makes rather clear is Ray's passion for physics. I mean, this is a course on Newtonian physics, but Ray felt bad about teaching us something that wasn't actually right. And so you notice that there's some evening lectures here on special relativity just to tell us what was wrong about Newtonian physics. I wanted to point out also something curious here. The final exam was on the 14th of December. That was a Tuesday between 10 and 11:30 in the morning. That'll turn out to be important. Now, I talked to Ray after this class. We ended up walking back to Building 20, and when Ray discovered that I was teaching myself relativity, and that I had originally come to MIT to be an electrical engineer, and that I liked building electronics, he hired me to work in his lab. So I started working for Ray literally on day one. This is what Ray looked like at the time. I think you've seen some of these pictures before. This is Ray with his PhD advisor, Jerry Zacharias, who saved his ass, as he would have said. Now, I was working on a microwave background radiation experiment. This picture was taken in 1976. This is a few years later. I'm building a 10 gigahertz microwave horn antenna here, X-band. And one of the first things I needed to do was to measure the side lobes of this to see how much of the ground was going to leak in. And that was done using a klystron. I think it was a reflex klystron. And one of my first really clear memories was Ray helping me turn on this klystron. It was a microwave source. It had come from the radiation lab. It was some dusty piece of 1950s equipment. And the thing that struck me that I really appreciated was there was no instruction manual for this thing. So Ray was turning the knobs on this high voltage power supply and explaining to me how the thing worked. He says, okay, we start with the repeller voltage really high, and now we're going to turn it down. See the bunches of electrons that are coming out here. When we get them to go far enough into this interaction chamber, they're going to start off. He had a picture in his head, a mental picture of what was going on. And Ray was the first person to teach me how to think like a physicist, how to make numbers and how to build this mental image. Now, he had a lot of other important influences on me. I think it's fair to say that Ray influenced my career and my interests more than any other person alive. And sometime in November, that first year, he said, Bruce, there's something that you should go to see, because I know that you're studying relativity and you're interested in this. There's going to be a talk at the Texas meeting in the Copley Plaza Hotel on the 14th of December by a guy named Stephen Hawking. You should go and listen to that. And he said, you can come to my office and take the final exam in the course. I'll keep an eye on you while you do that. And that way, even though this overlaps with the exam, you can go. So that was the first time I saw Stephen Hawking, who eventually became my PhD advisor. I want to tell a story about Ray. In the last year of my time at MIT, my undergraduate thesis experiment, I built a liquid helium-cooled front end for this microwave background radiation experiment I was working on. There's a nitrogen outer jacket and then a helium inner core here. And there was a problem with this. There was a heat leak somewhere up here at the top. So when I filled it with helium, the helium would just boil away in an hour. I mean, it was supposed to stay cold for a few days, but the heat leak would just boil away all the helium. And I worked for months trying to figure this out. I couldn't figure it out. And then finally one day, a guy in the lab, Andrew Jeffries, Andrew's not here, he was supposed to be here. He said, yeah, there was a similar problem. We saw at Princeton a few years ago. It turned out to be convection around the heat baffles. This is the lowest of 7 heat baffles. And he said it was fixed by putting some expanding foam, the kind of stuff that you use in home insulation, in between the baffles. That stopped the convection. Maybe you should try that. And I was desperate at this point. And so I went out and I got some expanding foam and I put it between the heat baffles and I put the door back together. And I remember it was a Friday afternoon and I filled it with helium. And as soon as I did that, I knew something had gotten better. Because before you could just hear the helium hissing out, and now there was just this slow trickle, this vapor stream coming out. And so I started measuring the levels of helium with a dipstick. And that was Friday night. Anyway, when Ray came back into the lab on Monday morning to walk around, he found me there. I'd been making a plot over the weekend of the helium levels going down. And I was really excited about this because I think it was 60 hours was the lifetime. Then I could do my thesis experiment. And I remember Ray telling me, he said, Bruce, I'm really happy to see you so excited about this. It's a good sign for your future as a physicist because he said the satisfaction that you get from science, it's not the prizes, it's not the awards. He said that's all bullshit. What you get is the satisfaction of solving a problem that's really been bugging you for a long time. That's why you do science. And in fact, that's something which has stayed very close to me my whole life. Now, I'm from this area, and whenever I would come back here to visit family, I would always come by the lab to have a chat with Ray, go out to lunch at the F&T diner, and I would stay in touch with Ray. And in 1984, I'd come back from Cambridge. I was a postdoc now in Santa Barbara, and I had bought an MG Midget, 1965 MG Midget as a graduate student. It was a bucket of junk, but I fixed it, and I brought it to California with me. You notice that the steering wheel's on the wrong side. So anyway, so I was a postdoc now in Santa Barbara, and Ray was there, and I went to have a chat with him, and he said, I want to see your car. And so we went for a drive. And as we were going for a drive in this car, we were talking about this and that, and Ray said, I know you've been working on inflationary models. And by the way, I was interested in inflation because since I'd thought a lot about the microwave background, the horizon problem, why the temperature this direction and that direction on the sky are very similar. That's very tough. And inflation offers a solution for that. So he says, I know you've been working on inflation. Listen, can you try and calculate the gravitational wave background that inflation would create? Maybe that's an interesting source for LIGO. And that scientific problem turned out to be hard. I worked on different aspects of this, like, for example, what's the correct definition of the vacuum state for the quantum fluctuations which create this background and so on. A whole series of papers came out of that with the final answer being this spectrum. By the way, normally what you plot is omega. So you divide this you multiply this by a factor of 1 over f. And then here's the steep low frequency part. Those are perturbations that re-enter the horizon after the universe becomes matter dominated. And then here's the flat part and so on. I think this is actually the first published sort of full spectrum. Anyway, so Ray's interactions with me were really an inspiration. So this turns me now to the last thing. This is a topic that Ray and I were talking about during the last years before he died, which is pulsar timing arrays. These are low-frequency detectors of gravitational waves. They're made from a set of pulsars. These act as precision clocks, and the pulses, when they arrive at the Earth, are recorded and timed. And if a gravitational wave goes by this, it advances or retards the arrival times of these pulses very slightly. And I've marked this diagram as not to scale, not just because, of course, the Earth is too big, but for another important reason, which is that these pulsars are perhaps 1,000 years away from us. The light takes 1,000, or the pulses take 1,000 years to reach us, whereas the gravitational waves to which these things are sensitive have periods of about 10 years. So you should really see about 100 cycles of this green background along one of these paths, not just one sort of slow thing. And the sources here would be located in Harvard Square or something to this scale. They're very far away. So unfortunately, the gravitational waves in pulsar timing arrays don't produce perturbations at the Earth which are large enough to individually measure the noise in the pulsar's rotation, interstellar weather, advancing and retarding the arrivals of the pulses. These things play a more important effect. And so the way that you detect gravitational waves with the pulsar timing array is by observing the pattern of correlations that the gravitational waves produce between the arrival times in different pulsars. And those form a pattern that was predicted by Hellings and Downs about 40 years ago, where two pulsars that are close together on the sky are correlated. Two pulsars that are about 90 degrees apart on the sky are on the average anti-correlated. And you go back to a pattern of correlation again for pulsars that are in opposite directions on the sky. And observing this pattern of correlation, that's like seeing the chirp signal for LIGO. That's the sign that you've seen gravitational waves. And the status of this is a bit of a mess, to be frank. If you look at the 6 different pulsar timing array collaborations, here's their attempts at reconstructing this Helling and Downs curve from their data. And you can see these are from papers 2.5 years ago that, for example, the Parkes pulsar timing array said there's no support for or against the background. The European pulsar timing array said there's marginal evidence, or if they select their data a bit differently, there's evidence. The North American Nanohertz Observatory, Nanograv, published a paper saying there's compelling evidence. That range of 3.6 to 4.2 sigmas have been now revised down to 3.2 sigma. So anyway, the interesting scientific question here, something I was talking with Ray about, is what happens if you combine all of these data sets together? Because, of course, that roughly doubles the number of pulsars. Many PTAs observe the same pulsars, but that increases the number of correlations by a factor of 4. So you should see stronger evidence. And the question was that actually, what would that show? And I just wanted to say that this is something which I've been working on with a couple of people, Wang-Wei Yu and Rutger van Hasteren, and we've actually completed such an analysis. We took all of the public data from 5 of these PTAs. The Chinese pulsar timing array data is not public. And we combined it using effectively a simple method that lets you just put the data sets together. And we searched for a background which has a power law spectrum. So there's a characteristic amplitude A and a characteristic slope gamma. We combined the data, and indeed, if you do this, you do find evidence for a gravitational wave background. You can see here posteriors on the amplitude and on the slope. If you fix the amplitude, the slope to the value that you'd expect from binary in-spiral sources, you get a rather sharper constraint here on what the amplitude is. It's peaked away from 0. And in fact, you can also reconstruct the Hellings and Downs correlation curve. This is actually not an optimal reconstruction, I'm afraid to say, but it's a standard one. This is actually a good fit. Chi-squared is 0.84. But the punchline here, and this is the thing I'm sorry that I was not able to show to Ray, is that even when you combine all of this data together, you get a statistical significance if you measure it using what's called the optimal statistic. This is a null hypothesis significance test. It's around a 4 sigma observation. You can also do this using Bayes factors. It's about then 4.1 sigma. So it's still not a detection. And I think Ray would have been disappointed by that. But thank you very much.
Okay, our last speaker for this morning's session is Professor Lyman Page, Jr. Lyman is the James S. McConnell Distinguished University Professor of Physics at Princeton. He completed his PhD here at MIT, working with Ray, having previously served as a research technician at McMurdo Station in Antarctica and other interesting things in between. He joined the Princeton faculty in 1991, soon after completing a brief postdoctoral appointment here. His research focuses on measurements of the cosmic microwave background from ground-based, balloon-borne, and satellite platforms. He was one of the original co-investigators of the WMAP satellite project, the founding director of the Atacama Cosmology Telescope, or ACT, in Chile, and a founding member of the Simons Observatory, also on the Atacama Desert in northern Chile. So Lyman's talk today is entitled QCD Axions as Dark Matter Are Within Experimental Reach. Lyman, please.
Great, thank you. It's a pleasure and honor to be here just talking with all of you. And remembering Ray, Bruce said so many of the things that I would have said. I can be a little more brief than I plan to be, and so I don't. So I can keep it together later. Let me just go to the punchline here. So I was mid-20s, and I'll tell you how I got here. And then, but I was wandering around, and I was looking for a job. I didn't have a job. I didn't have any connections to MIT. I didn't have any, academic lineage. I went to college as a physics major and all that. Nothing like that. And Ray he welcomed me. I came to him for a job. He welcomed me into the lab and just made me feel great, comfortable, taught me things, taught me how to think, taught me how to do physics, mentored me in a way that carries me on still. I'm on the path that he set me on. And it was just a huge figure in my life. So it's really, as you can see why I started this way. Okay, so so this is actually a slide from Ray because he reminded me exactly what happened, and you've seen this before. So I'd been sailing for 2.5 years and working on my boat. And I decided I wanted to come to graduate school, and I wanted to go to MIT. So I walked in, and I knocked on the admissions door. No one was there. Herb Bridge, who was the director of the CSR, said, "Look, let me help you." And I said, "Well, first I want to get a job," because it wasn't quite admissions time. And he said, "Let me give you some names." And one of them was Ray. And so I went around and talked to people, and everyone was more interested in sailing than science. And so, but I came here to Building 20, in that back door, and knocked on it or rang the bell, and no one answered. And I'd forgotten this part, but Ray reminded me. So I walked around the other side. I think you saw a picture of that other side in Vicky's slides. And there was I could see some people through the windows. There was a chain link fence with barbed wire on the top. So I climbed over that, and I knocked on the window, and they came and let me in, and that was my introduction to Ray. And he said I could. He said I could. Told them the brief story. He said I could work in the lab, but he couldn't pay me. But that was it. So I got a job as a carpenter in JP, and I would come into the labs at nights, afternoons I had off, and on weekends. And had many, like others, lunches on Saturday at the F&T, some with Ziggy, who we saw a picture of earlier. And that started me, and I was trying to absorb all the physics that I could, because I knew nothing. Even though I'd been a physics major, I just felt I knew nothing when I started, and slowly just was infected by the whole enterprise. And of course, as I said, still it carries me to this day. Okay, so let me tell you about axions. I think Lisa asked us, why would Ray like to do this? And I should say I still work on the CMB. But, so why would Ray like it? And I think because of it's fundamental, and you can measure it, and we can get there by measurement. It's not going to happen tomorrow, but the path is pretty clear for a lot of them. They're not easy measurements, but you can really do it. And you saw from that list of other things that Ray worked on that Peter showed. So I think he'd really like it. And I love these quotes. This is what we put in all of our proposals. These have MIT all over them.Maybe the most important experiment in fundamental physics coming up is the search for axions. We love it. Okay, yes. And then from Ben Safdie, who was a postdoc here, Thaler and worked with Yanni Kahn, why axions could be the next big discovery in physics. So why? Of course, they're a great candidate for the dark matter, but they can also solve this, if found, they can solve this outstanding problem of the strong CP, right? Why is there no CP violation in the strong sector? And that's, of course, ultimately linked to why is there more matter why is the universe predominantly matter versus antimatter? So here's the group, and again, going back to some of the things from Ray, it is about the people. And so Saptarshi Chowdhury is the new faculty member who leads us, and Roman and Frank and Joe and Nathan and Nate and Joelle. So this is the group at Princeton working on this. A magnet's a key part of this, and that's with John Dye and Yu Huzai at PPPL. And our traveling wave parametric amplifiers are from Peter Day's group at Caltech. So this is the group that's gotten together. Very briefly, here's where we are. The pioneering experiment, the concepts for which were laid out by Pierre Sakivi is ADMX. It's been brilliant, and they have set. So let me tell you what the plot is. Here's the axion mass down here. And actually, I just want to say one more thing about going back. I know Ray thinks the dark matter is primordial black holes. He told me every time we talked about this. So we're well aware of that. But anyway, we talked about this as well. So anyway, here's ADMX. Here's this experiment that we're working on. It sort of nestles in right below ADMX, looking in the mass range of 0.8 to 2 micro eV. So it's about 200 to 500 megahertz region. This is, and these are all, that's real from the CAP experiment. And this line here is the limit, theoretical calculation from the DSFZ group for where we should see the axion, photon coupling, if the dark matter is at the axion, okay? Is this line down here. 10 to the minus 9 is the gut scale, okay? So what's cool, and then these are projections. Lindley Winslow here is the spokesperson for this experiment and the DM radio experiment. So there's a lot of collaboration because Saptarshi came from the version of this group at Stanford. So we're all working on figuring out new methods to search for axions in this region. And then there are other experiments up here, but I don't have, there are a lot of other experiments I don't have time to talk about. But there's a vision now for how we can get from below ADMX all the way down to the gut scale. So it's really, it's exciting. It's really fun. Let me just show you a couple of elements here for wrapping up. So this is actually, so what does it take to measure an axion? So what's the signature that we're all looking for? Is that if you have a large magnetic field, let's just put it in the z direction, what an axion does, right, and we're swimming in them, right, we're in the sea of axions, they couple to the field and they make an axion current along the field, right? Just the opposite of all that stuff you learned, in your E&M class, right? So the axion current is along the field. And then that axion current generates, I should say the frequency of the axion current is proportional to its mass, just h nu is mc squared. So the frequency is proportional to its mass, that's the 200 to 500 megahertz. But then it generates a magnetic field like you would think in E&M, perpendicular to it. So you have a DC field here, an oscillating axion current here, and then an oscillating magnetic field around the DC field. So that's what you look for experimentally. And the way we do it here is so this is a big magnet, that's why PPPL is involved, huge magnet, and then this is a cavity of 40 millikelvin, and it's just a garbage can. It's just a big garbage can, and with an antenna in it, and you read out at the quantum noise limit, or try to, right? There's all this interference you have to worry about, all these systematic effects, all this background noise you have to get around, and you're just looking for that oscillating magnetic field in your garbage can. Okay, and this is all, and then the whole thing, has to be cooled by a dilution refrigerator, and some 5 Tesla magnet, and it's conduction cooled. And here's where we are. This is actually now in the lab. The prototype for a cavity is in the lab. We have our manufacturing review in 2 weeks for our magnet, and my awe at people who work on building magnets just increases daily. They're really tricky to make at this scale. And the dilution refrigerators in the lab. So all this stuff is being built, and it's just a blast. And my slide for all the people who have supported us. So we're off and running. We hope to have something within a couple of years. And while we hope, maybe the dark matter is both primordial black holes and axions. Wouldn't that be wonderful? But it's anyway. Again, it's just I think of Ray often and doing this, and I think I'm still infected by his enthusiasm for science. So anyway, let me stop there and thank you all. It's me again. So we're going to talk about the microwave background, which I've been working on since starting with Ray. And what we're going to do is I'm going to give a brief introduction, digging in a little more to what Ray did. And then we're going to have a panel discussion. This is all going to fit in by 12:10. Then we're going to have a panel discussion here. And it's really, we have this, this is an amazing opportunity because Ned Wright is here from Kobe. And of course, there are other Kobe people, but also John. And then Mark Halpern, who was working separately on an absolute temperature measurement. And so we'll talk for a while about that and common links to Ray. And then we're going to end up right at noon with Sam Day-Weiss giving a 10 or so minute talk. Okay, so here, why do I have this up here? So this is this spectrum from Kobe. And this is, and I'll show a couple of versions of it, and I'll not focus so much on this one because, unless you're in the business, you probably don't work in ICMs, which are inverse centimeters. Okay, but we'll get the peak here is at 2 millimeters. That's the key here. Okay, and what I'm going to tell you comes from this essay that Ray wrote. Okay, here's roughly, Ray was a pioneer in CMB measurements. And you saw the quote from Peter, the technology as we know it today just did not exist. And Ray had a crucial step in developing the technology and making some really crucial measurements. So he returned to MIT in 1964, working on measuring G. And then Bernie Burke here, who had made some measurements of the CMB at low frequencies, suggested Ray try to measure the CMB near the peak. And we'll get to that, why that's important. First balloon flight, we heard about 20 of them. First balloon flight was in '69. Dirk Mueller did his PhD, was integrally part of all this. His PhD was 70. The first meeting of Kobe was with Mather, Thaddeus, Weiss, Miller, Wilkinson, Hauser, Binzak, and they met in New York. And that was 1974 to talk about what would become Kobe. So maybe a pre-Kobe meeting. And then just to layer this in 1975, Ray gets his first award from the NSF for 53K to work on interferometric-based gravitational wave detectors. So these things were going on in parallel. And then David Owens did his PhD on a sky survey. Pat Downey, with Ray, invented this thing called the monolithic silicon bolometer, which is, I'll talk about a little bit. Steve Meyer joins the group as a postdoc. I started hanging out, I rapped on that window in sometime in '82 and was hanging out off and on for the year, and then basically Ray got me into grad school and I started in '83. Andrew Jeffries and Mark Halpern, we don't have quite the right dates, but then they finished up their PhDs in '83. And then Steve took over the group. I was his first grad student, and I'll tell you briefly because you'll just hear Ray in this. So I was Ray's student for 2.5 years, something like that, working on the microwave background. And then one day we were in one of the MIT buildings, sitting on the stairs, And he was smoking his pipe then, and he just says, "What do you want to work on?" And he's smoking his pipe, and I would have worked on anything. And he pulls out, "Work with Meyer." And that was it. It was either gravitational waves or CMB. And Steve Meyer was my advisor, and fantastic. So my last whatever, 3.5, 4 years was Steve Meyer. So blah, 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 Dave Cotting, and Kobe launches in '89, and then Ray's, I think, last big thing on the CMB was coordinating this task force on the future, which still guides us of what we can do with the CMB. In red here are all the people from Dave Wilkinson's group who had come up. So there was a very tight connection between the Princeton group and the group here, so much so that Building 20 was often called the Jadwin Hall Annex. Okay, here, Jadwin Hall is the physics department of Princeton. Okay, here's the status of the measurement. This is from Jim Peebles. So now, here's wavelength on the x-axis and energy on the y-axis. And this is a 2.7 Kelvin black body, right? So you'd expect that black body curve. Here are the measurements, okay? So you can see their upper limits and some measurements up here above the peak. And so the question is, did this turn down, okay? And why is this important to know, right? If the microwave background, if that had a cosmological origin, if it was from the Big Bang, it should have a thermal spectrum, should have a Planck spectrum. So this was crucial to know. And that's what Ray worked on. You've seen this picture before. The first, and here is the instrument. So all this was new, how to read it out. Everything here was floating in liquid helium. How to do the optics, none of it was clear. There was I think this had a filter that looked in 3 different filters, and you look at the ratio of the power between them. And in their first flight, Miller and Weiss, 1970, they reported an excess over the peak. And this was a theme that would stay with the field until Kobe and Cobra, right? That this measurement was this excess over the peak. Okay, so they did this. They reported an excess, and it was due to emission from the rim of the cryostat. And I should say, I got a bunch of these pictures from Steve Meyer, who wishes he could be here, but just couldn't be, and Dirk Mueller, who will be here tomorrow. So that was that. And so they said they saw an excess, but not as large as others, and have this comment in this paper from 1970, spectrum may not be thermal. Second flight, the letdown reel, which they wanted to say, maybe we're seeing the balloon. Let's let down the reel, let's let down the payload 1,000 or which is a couple thousand feet. Broke, okay? Their package went to the ground, destroyed, completely destroyed, but that was a godsend because they rebuilt it without that rim. And then they had 5 more flights. They knew after 3 that the results were consistent with the CMB, but there were questions because they had to make corrections for the atmosphere. And so they then had 2 more flights to figure out the atmosphere. Here's a picture. Here's the letdown reel that broke, that then Ray redesigned later with the balloon team, with the balloon base. And there's Ray on recovering the payload early on. And I want to include this, I love this. The results of these flights were published in PRD rather than PRL, and this was a mistake. PRL offers rapid response, but not much space, and we were not experienced enough to write our results in a convincing and short manner. And he says it's because it just didn't get enough play, right? They were clear to us, the results of the initial flight were wrong, there is no excess near the peak. Second set of measurements showed the curve turning over at higher frequencies. Okay, and then, years later, and this, I'm sorry for the lousy reproduction here, this is now the temperature on the x-axis, and this is a chi-squared on the y-axis. And I think Alan Guth, for his book, said, did you guys really do this, or something like that? And then Ray went back and looked at the data. And so this is now, okay, you can see clearly how the minimum chi-squared, right near 2.8 Kelvin, and then as you go to higher and higher possible temperatures, this is fitting the Planck black body to their data. Clearly, this is singled out. So they really did measure the right spectrum, the spectrum as we now know it, and it's a fantastic measurement. Okay, Then they went on with Owens starting to measure. This is actually Dirk Muehlner again, Day-Weiss in the field. And here's Pat Downey. And this was an enormous development in detectors, because everyone had been making them by hand beforehand, right, with tweezers and things like that. And this was a completely modern setup, right, with using E-beam evaporation and implantation and making implanted leads and all that stuff. And I used these for my thesis. They were the most sensitive detectors around for a long time. Here they are. And they're big things. They had this huge étendue, so you could dump a ton of power on them, and really low 1/f noise. Okay, some quick pictures so we can get to these guys. Here's Ned Wright and David Shoemaker on the prototype for the FIRAS instrument. Ed Chang and Steve Myers, so this was in late 80s. I don't know all the people here. Here's Dick Benford. I'm not sure if that's Nergis or not. There's Peter. Nelson, a lab can be a cruel place. Nelson, his nickname was Fuse Blower. Boris Golubovich there was an undergraduate. Steve Meyer, Dave Cottingham, who was working on another CMB experiment, me, and then Ray. And actually, just a thing on Nelson, you heard about Dan Dewey's introduction. Nelson was working on Bayesian analyses of background of lots of things, but he actually contacted a bunch of us in the CMB community and brought the whole Bayesian framework into the CMB community, and it's all we use now.
That was the annual lab night.
Yeah. Yeah. Is it? Yeah. Good. Okay. So here you've seen this picture. Is this? I don't know if is that Ben? That's Ben. All right. That's Ben. There we go. All right. Okay. And Ray and again Dick Benford, Steve, Bill Barnes, Virginie, and Ray. This is not Mike Burka's wife, okay? Everyone had that wrong, and Mike told me a little while ago. Here is Peter and Pam's oldest, and just Ray. I just love this picture. I know they're communing, right? And there's Ray with his gate walking down Building 20. Okay. I want to introduce Ned. This is Ned Wright, who worked with Ray for many years. Worked on Kobe, was actually the first person who found the anisotropy. Who actually found the anisotropy in the DMR data, and then went on to lead the WISE experiment, the WISE satellite, which has just given us beautiful results on so many fronts that we could talk for another half hour about it. I don't know, you haven't had a chance to talk. Why don't you give some impressions of Ray?
Well, I was looking at some of the slides that were projected, and that's where I first met Ray down in Palestine, Texas at the balloon base. And so I have my own slides I took on my camera of that MIT package, actually 3 different MIT packages, because one thing about balloons is they never work right the first time. And so you're always going back. And the nice thing about balloons is that you can turn it around in a couple of months and for pocket change compared to a satellite. So that is the essential advantage of doing things in ballooning. And that was perfect for Ray's style of, he was the hardware version of, fail fast and refly. So that's what I have to say.
There were 2 measurements of the spectrum. One of that Ray worked on, determining the turnover of. So there was the one that came first from Kobe, FIRAS, and then there was the other one, and these results came out within months of each other. And I don't know, why don't you guys should talk about it, because it's an incredible story of decades of work.
Within weeks of each other.
Yeah, so Right, we built a rocket instrument. The CMB, it's just honking bright. So if you get up out of the atmosphere and open your window, the signal noise ratio on the spectrum is huge, and the whole game is not having your instrument be brighter and so forth. So we built a sounding rocket designed for a few-minute flight. Looked a lot like the picture John showed. It's a Martin Public interferometer polarizing internal reference that we move up and down around 2.7 Kelvin, and we look at the sky and we see null fringes during the flight. So, you know, Herb and I shook hands while the thing's still in the air saying it's a thermal spectrum. You just can see it flat out in the data. When we shook hands was 2 days before John gave his AAS talk. So it's in this 8-week window between, between when you guys flew and when you told everyone you had the answer, although you knew it, probably like us, when the window opens. Yeah, it was a treat and fun to come close like that. I gotta say, it's a 10-minute flight, so we're stuck at the 1% error bars level forever with those data. The advantage, balloons are quick, but they're very expensive per hour. And if you want a year's data and you want to move things around carefully and so forth, there's no question that very careful measurements happen in the satellite.
Yeah, well, you know, one of the lessons that was driven home when I was working on the CMB and working with Ray is that the best experiment is one that measures nothing. And so by that I mean you always have to have a null experiment. And so both the Gush rocket experiment and FIRAS were designed with a calibration blackbody, and they were designed that the output signal was the difference between what came down the Skyhorn and what came from the calibration blackbody. And so when properly tuned up, you're measuring nothing because the sky is very close to a blackbody.
LIGO gang knows this, right? An interferometer, a Michelson interferometer, is a differential instrument, right? And so both of these spectrometers are LIGO-like in that sense, that they're from the start differential, yeah, and they're going to show zero.
Anyway, so FIRAS is a misnomer. I mean, the absolute spectrophotometer is strictly, differential.
Quite true. Definitely not an absolute spectrometer, although with great effort you can calibrate it to be one. But honestly, we did not determine whether Planck's formula is correct. It's not. We didn't measure that. Dale did a really good job of doing as well as you can with the data, but it was not the original purpose.
And maybe just to add a remark, the approach we took is we built 2 or 3 different lab calibrators that we put in the place of the sky. Actually, our instrument was symmetric enough that we could put it in either side and put the internal calibrator on either side. And our figure of merit was we make 6 different ways of making a thing that we think is a black body. It's very unlikely they're all going to fail in exactly the same way. So we kind of thought we had a thing whose emissivity was 0. But just again, always from differences. And the Planck law could have been wrong by a factor of 10 and we wouldn't have known.
And I should add that what we did is not the limit. You can do at least 1,000 times better. There's a mission we were working on called Pixie, which would be a grown-up version with much better calibration of the FIRAS instrument, and it could also measure the polarization of the CMB. So we didn't fly it yet, but we could.
I've actually been surprised that for most of the spatial, I think from the spatial experiments doing the maps on the ground have obviously not tried to make things fully differential and null. And I've been surprised at that because I think that the next generation somehow didn't absorb the true beauty of the FIRAS. I mean, it's a very interesting thing.
I should say that as Harvey Mosley, also part of COBE, and Dale Fixon is right there, who did the analysis behind the spectrum I put on my first slide. I don't know if there are any other COBE members here, but yeah, Bruce.
So one of the things that really endeared Ray to me, which I learned from him, was his attitude about mistakes. You know, in normal society, when people make mistakes, they often try to cover them up. And Ray had exactly the opposite attitude. He'd say, oh, that's a really interesting mistake. Mistakes were something to be elevated, to be studied from all directions, to learn from. He actually celebrated mistakes as something interesting to discuss and learn from. Now, the two of you have 200 years of experience with Ray, collectively, and we heard about, you know, how during his PhD thesis and afterwards, there was a lot of mistakes. So I'm just curious, does any of you remember a mistake, one of these things that Ray thought was very interesting, and you learned something from it?
I'm not sure about Ray alone, but our whole science team for Kobe was attentive to mistakes. We were so concerned. There's been such a rash of terrible science in the public, polywater and cold fusion, that we are not going to do any of that in public. We are going to hunt and hunt and hunt for mistakes that we could have made. And so even after Ned showed us the first maps of the CMB hot and cold spots, we said, well, we can't publish yet. It's probably right, but we can't do that. We have to keep hunting for mistakes. Even after you found all the mistakes, you still have to keep hunting.
One part to celebrate is the little microscopic mistakes. The thing I learned from Ray is if you have electronics and they don't work, don't touch them. Figure out why it is they don't work. Don't just fiddle and see if it works later, because then you won't know what happened. So if you have a thing and it isn't working, that's a gold mine. And you understand it before you do a thing. So I mean, one example, when we were trying to figure out how to make these absorbing films on the detectors, we had no real idea. I had no real idea. And I just got wildly different results run to run. And then we understood that I wasn't paying any attention to I was thinking of them as filters. And I wasn't paying any attention to whether I put this few microns of sapphire in with the bismuth on the top or the bottom. And the dielectric constant of the sapphire made a factor of 2 or 3 in the absorption. And then we realized that that's a gift, because you could tune the metal film and the sapphire so that it looked like an infinitely thick block of sapphire.
So understanding the mistake there led to, a step forward. Yep.
I was just saying, well, you've worked in the lab, right? At least for me, it's just a constant step of mistakes, right? Nothing, and you just be brutal with yourself every mistake you make, and that's how you make progress. Because we need to wrap up. I just want to point out one other, it's maybe too obvious to say, but just so Ray was, of course, crucial in Kobe, one of its originators, and Mark's thesis advisor. And both of these experiments had enormous challenges outside of recovering from mistakes, right? Kobe was, the Challenger disaster made you rethink it. Mark's experiment was shaken to pieces before they launched it. So it could well have happened before Kobe. So these experiments went on for decades, and then both have roots with Ray. And they finally worked within now weeks, I've forgotten the exact number, weeks of each other. So it's just this amazing story of how science works over the years and how progress is made.
And it was a great relief that the 2 spectrum experiments got the same number.
Exactly, yeah.
Just luck. What if they didn't?
Just luck, right. Yeah, it would have been interesting. Okay, let's thank these guys again. We're going to end up with Sam Day-Weiss talking about modern anisotropy experiment. And so Sam, I have the honor of being Sam's PhD advisor. And so this is what I'm working on when I'm not working on axions. Good. Welcome, Sam.
Thank you, everybody. My name is Sam Day-Weiss. Like Lyman mentioned, I'm a graduate. I've been working with Lyman in his lab for about 6 years now. I'm a graduate student. I have the great fortune of giving the last talk before lunch. So I'm unfortunately keeping you all from it, but hopefully you forget about your hunger. I'm going to tell you about a really exciting new experiment, measurements of the CMB. The other thing that some of you in the room know but may not know is that I'm also Ray's grandson. So it's an extreme, thank you. It's a real honor to be able to talk to you about my dissertation work here. The CMB field is a very active field still. There's a lot of, the frontier is really, as Lyman mentioned, on measuring the anisotropies of the CMB. And I think the newest experiment that has detectors on the sky right now is called the Symes Observatory, which is what my work is in. So I'm going to talk to you about that today. So as an overview, I'll talk a little bit about the observatory itself, what it consists of. There's a variety of different telescopes that it consists of. My work has been in a subset of the telescopes called the small aperture telescopes, which I'll call the SATs from here on out, a little jargon. They are fundamentally a search for gravitational waves from the Big Bang, so B modes is sort of the jargon from the field. I'll talk a little bit about what that means, how the instrument design is working towards that goal. I'll show some slides from the lab about the journey of the instrument from Princeton, New Jersey to the Atacama Desert where it observes. And then I'll show some initial observations and results, which we're very excited about. So this is a drone footage of a mountaintop in Chile. It's called Cerro Toco on the Parque Astronómico de Atacama in Chile. It is where the Symes Observatory is. It is also where a bunch of CMB experiments have been, also led by Lyman. Over on the left-hand corner is where the Atacama Cosmology Telescope used to be, where that SAT-6 is labeled. So that this is a great spot for observing. The hardware that's currently part of the Symes Observatory is called SO nominal, which is in this middle part of the diagram. It consists of one large aperture telescope, which is a 6-meter primary mirror reflecting telescope, and then 3 small aperture telescopes. The LAT has been observing for about a year now, and the SATs have been on the sky for about 2 years. So very new results. But the observatory is growing, and there's plans to actually add 3 more small aperture telescopes, which are pictured there on the left. So I've boxed that one small aperture telescope in red because that's the one that I've primarily been working on for my thesis. And I should say that this is a multi-frequency measurement experiment. Each of the small aperture telescopes are dedicated to a different frequency range. So we're looking at the anisotropies in frequency bands at 30 and 40 gigahertz, 90 and 150 gigahertz, which is the instrument that I cover, and then also 220 and 280. So like I said before, the SATs are primarily a search for primordial gravitational waves. But how do we look for primordial gravitational waves in the CMB? It turns out you do that from looking at the polarization of the primary anisotropies. So it's been well established, as we just heard since the Kobe DMR experiment, that there are small temperature fluctuations around the mean 3 Kelvin black body. And those perturbations are scalar perturbations, which basically trace the density of dark matter in the early universe. And the RMS of those fluctuations is at about 110 microkelvin. So that's, again, relative to the 3 Kelvin background. Now, it took increasingly sensitive measurements of the anisotropy to discover that it was actually linearly polarized at about the 5% level. And what is so fantastic about and interesting about the polarization of the anisotropies is that just by tracking distinct patterns of that polarization across the sky, you can actually distinguish different physical mechanisms that generated that polarization on the surface of glass scattering. One of those contributions, which has been well measured already, is from those scalar perturbations. So those same perturbations that make the temperature anisotropy also make what's called E-mode polarization. And I should have said these are little snippets of maps of the temperature anisotropy and the E-mode polarization from the Atacama Cosmology Telescope, a very recent data release from that collaboration, which is combined with Planck data. So you have that contribution from scalar perturbations, which has already been well characterized. But then there's also a theoretical contribution from metric perturbations in the early universe, which are really just gravitational waves. And there is currently an upper limit on that contribution of a 57 nanokelvin RMS, and this is what we call the primordial B-mode signal. So that limit was set by our colleagues in the BICEP-Keck collaboration, a paper in 2021. And this signal is really what the small aperture telescopes are aiming for, what we're looking to. I mean, ideally, we make a measurement, we discover the gravitational wave signature in the polarization, but at the very least, we want to improve that upper limit by about an order of magnitude. So just to sort of summarize, this is a ground-based observatory. We've already heard that there's balloon-borne experiments and satellite experiments. Those all, there's things to weigh with cost and sensitivity. This is a ground-based observatory, and so the primary measurement challenges come from that fact, the fact that we have to look through the atmosphere. So in summary, the challenges are really that we're trying to measure a less than 57 nanokelvin RMS signal through a 12 Kelvin fluctuating atmosphere. So it's an extremely difficult measurement to make. We also need to make a high signal to noise measurement over a large sky area because that primordial signal, B-mode signal, comes in at about the 2-degree scale. So we need to map a relatively large region of the sky in order to achieve that. So how are the small optical telescopes designed to sort of address these measurement challenges? There are 3 main things. We designed it with a wide field of view, so a 35-degree field of view, which is very large for these kinds of modern experiments. We packed the focal plane with a ton of really sensitive detectors. And the last thing, which I'll show on the next slide, is we also employ a half-wave plate, which modulates the incident polarization signal and helps us kind of decouple from the atmosphere. So on the left diagram here, we have a cross-section of the small aperture telescope. The light from the CMB sort of comes up from the top part of the figure here, and from the 35-degree field of view into the window of the telescope. The reason why it's important to have this wide field of view is because, well, sort of twofold. It helps us disentangle signal that's from the sky from signal that's correlated with our instrument, and it also helps us measure a reasonably large sky fraction all at once. So we're instantaneously measuring points in the sky that are 35 degrees separated from one another, and we can do this on a time scale that's faster than the fluctuations of the atmosphere. So the light comes in through the window, it goes through this half-wave plate, which is rotating at 2 hertz, that modulates the polarization, and then it goes through a 3-lens refracting optical system down to the focal plane, which is what I've boxed here in orange. Now it's a cryogenic system, so it's a vacuum cryostat, and the optics, the lenses are cooled to about 1 Kelvin, and the focal plane is cooled to about 60 millikelvin, so that this is for helping with get the detector sensitivity to be photon noise limited as opposed to dealing with thermal fluctuations. And all of that cooling is achieved by this dilution refrigerator, which is this object sticking off to the left. So if you were to look at the underside of the telescope, you would see the picture outlined on the right, which is sort of a blow up of what I've highlighted in orange there. That is a picture of the fully populated focal plane of the instrument looking skywards. And each of those gold hexagons has about 1,700 transition edge sensor bolometers in it. Just as a scale of reference, I think Lyman's thesis experiment flew 1 bolometer. Is that right? 4 bolometers, I'm sorry. We have 10,000 of these operating at the photon noise limit, regularly looking at the CMB. And in fact, it's looking at the CMB right now. So we've made a lot of progress in terms of, one of the hardest challenges is in multiplexing these detectors, but this is an incredible feat of engineering and science, and the sheer number of detectors really helps us get the sensitivity that we need to measure that, that really small signal. So the field of view gets us some way in terms of mitigating the atmosphere. We measure a pretty large fraction of the sky all at once. But the real problem is that to get our full survey area, the telescope needs to scan back and forth to actually do the measurement. And the problem is when you're doing that measurement, when you're doing that scanning, the atmosphere is fluctuating with its 12 Kelvin signal at the same time. And so you need a way to decouple from that atmosphere. And we take advantage of the fact that the atmosphere is actually not linearly polarized, but the CMB is. So we decouple from the atmosphere using a cryogenic rotating half-wave plate. The light from the CMB comes in, the half-wave plate modulates the polarization, and that pushes the signal band, away from the timescale of the fluctuating atmosphere. So in principle, this is, it's a very simple idea, but practically speaking, it's a really difficult engineering problem because the way, this is a 0.5 meter slab of sapphire. It's multiple sapphire plates stacked together. It all sits on a rotation mechanism, and all of that's cooled to 40 Kelvin. And then that rotation mechanism is spinning on a superconducting magnetic bearing all at 2 hertz. So this thing is a real beast to operate. During the lab testing and also in the field, it's the thing that we're most nervous about breaking all the time. But it's been working, and it's been modulating the polarization and allowing us to make some measurements. Here's just some slides. Just like everyone has emphasized, so much of this work in building these kinds of experiments is about solving really hard problems with your friends in the lab. This is just a few of the people who contributed to the experiment over time. But the small optical telescope that I worked on started lab testing in 2019. I joined the lab in 2020, and then it took until 2023 for us to decide that it was ready to go down to the field in Chile. My favorite picture in this, I think, is this one of Lyman. If you ever thought that he stopped being a graduate student when he left MIT, you'd be wrong. He's down in the lab with us all the time, and this is him holding a microwave source over the cryostat when we're trying to get a signal into our detectors. Once we decided the instrument was ready to go, we packed it into a shipping container and sent it down to the Atacama Desert, reconstructed it, and then put it onto the platform to observe. And this is the telescope with a cover on it, which we used during bad weather, but this is essentially what it looks like now, observing the CMB as we speak. So one of the first things that you do after you install the telescope is you need to just make sure that it's working. You want to make sure the detectors have the sensitivity that we think they should, the optics are working properly, and most importantly for us, that the half-wave plate is modulating the polarization in an expected way. And so the first thing that you really do is you look at point sources that are available to calibrate the instrument. The point source that we use mostly is Jupiter, but Jupiter is unpolarized. And so this instead is another source that is polarized that we look at is the Crab Nebula. And so this is a beam map of the Crab Nebula. It's showing flux. The color bar is flux in temperature units, so in Jansky. And the polarization of the nebula, of the emission from the nebula, is overlain on top of the beam map. It's a 28 arc-minute resolution beam, so 28 arc-minutes is the full width half max of the 90 gigahertz beam of the telescope. So what you're looking at isn't really the nebula. We don't really resolve the nebula because it's very small, but it's just showing you that we have a really nice optical response in the beam. This kind of measurement gave us a lot of an early confidence that the instrument was doing what we thought. It tells us about the absolute calibration, the fact that we are recovering the expected flux, the polarization direction of the nebula that we get, and then also that nice symmetric beamform. Of course, the real thing that we want to measure is the CMB, and so once we kind of tick off these check boxes to show that the instrument's working as we expect, we go ahead and measure the CMB. So this is now a combination of two small optical telescopes. It's both mid-frequency, so 90, 150 gigahertz instruments. We have just a small snippet of a map from several months of data. You have Stokes Q map on the left, a Stokes U map in the middle, and then the E-mode polarization on the right. If you're used to looking at these kinds of maps, you can see sort of a vertical alignment of the pattern in the Q map. That pattern is rotated by 45 degrees, just like the Stokes Q and U vectors in the middle. And then those are clear indicators that we're detecting E-modes in the CMB. And maybe the way that people are more used to looking at the E-modes is in the angular power spectrum. So now this is just only using data from one of the telescopes, the one that Lyman and I worked on actually, to show that the EE angular power spectrum. There's been an overall calibration factor applied from lambda CDM, so that the solid curve there is the expectation from the lambda CDM determined by the Planck satellite. And we haven't subtracted any dust from this plot. But what this is really giving confidence in is that we're detecting that 6.4 microkelvin signal. We have a lot more work to do to sort of push down. So the primordial B-mode signal is expected to peak at around a multipole of 80. And so we need to push our sensitivity and ability to recover those modes down below the multipole of 100 shown there. That's, of course, where all the instrument systematics live. And so we have a lot of work to do there. But there's a lot of new data, a lot of new analysis going on, and we're really excited about the results that are to come. So that is all I have, and I'll just flash my thank you slides. So thanks.
Okay, let's thank everyone again. Ned, Mark, John, Sam.
Welcome back, everyone. Just as in this morning, I'm David Kaiser, a teacher at MIT, Physics and the History of Science. I was not scheduled to chair this afternoon's session. I'm glad to do it, but I'm sad for the reason. Our very dear friend and colleague, Peter Fisher, who is the named chair for the session. We'll hear from Peter on a video in a moment. He's home recuperating and is very comfortable and is just very, very sad he can't be here with us today in person. So Peter recorded a video on his phone just before he went into surgery. I mentioned that. You'll see why when you see the video. But he wanted to make sure he could at least share some of what it had been like in the role that Ray had played in Peter's own career and life, and then the transition to this session, which is a shorter session, about something that several of us in the room got to enjoy for nearly 2 whole years. I was working with Ray every other week on a small working group on primordial black holes. So with that, I'm going to ask the folks in the booth if they could please show that film by Peter Fisher, and then we'll have 2 short talks from some of our colleagues after that. Thank you.
Hi, I'm Peter Fisher. I knew Ray for about 33 years. The first time I met him was when he was my first interview when I was coming to MIT, and he made quite an impression then. The interview actually happened while he was teaching junior lab, and we were talking about various things. We were actually having a very good conversation, but in the same space were a couple of students who were doing an experiment that involved lifting and lowering a big magnet up and down, and they never really waited long enough for their calibrations to run before opening and closing the magnet. So interspersed in our conversation was Ray kind of yelling at them like, you know, I told you not to open that goddamn magnet. Now you close it and you wait until it's done, or otherwise I'm going to come over there and kick your ass. And it kind of brings me to one of 2 words I want to think about when thinking about Ray, which was that he was very authentic. He really always said pretty much what he meant, not always sugar-coated, not always diplomatic, but really him. I've been alone a lot in the past few days because I dislocated my shoulder and spent a lot of time lying in a gurney in the ER at Mount Auburn for like 2 days, and then here at home. And knowing that I wanted to do this, I've been trying to think about, you know, what were the really important moments I had with Ray. And I'll talk about 2. One was the very last time I saw him. We met for lunch at the Pacific Cafe, as I'm sure many here did. I always found these lunches really kind of intimate. Going to a place that I very seldom went to, seeing someone that I cared about a lot, kind of on his home turf. And I got a lot out of these discussions. And the very last time I saw him, we talked about the primordial black hole work, and he was kind of redemptive in his encouragement of us to think about this. That really meant a lot, certainly to me, and I think to the others involved. But I asked him, I forgot exactly how it came up, but I asked him, when in the course of LIGO did he really believe that it would observe gravitational waves? And his answer was interesting. He said, well, I never thought that, they would just appear, that we'd get to some design sensitivity, there'd be some low significant effects, there'd be a lot of arguing, and then he said, what happened? Well, holy mackerel. And there was just a lot about scientific discovery, the way it works there, and LIGO, it just kind of burst onto the world stage. After that lunch, it was raining. I drove him down to Mount Auburn, where I'm going tomorrow, in fact, to see Rebecca, and dropped him off, and he walked in, and that was the last time I saw him. A really singular moment was when he made some remarks on the day that the Nobel Prize was announced. We had, this wonderfully chaotic time in the Pappalardo room, and Ray gave some pretty unplanned remarks about LIGO and his career and his time at MIT, and actually a recounting of how he had been kicked out, which I think we've all heard various versions of. And of course, Gerald Zacharias was the guy who recognized Ray's talents and got him readmitted to MIT. And they worked together through Ray's PhD. And in that morning, in those remarks, he said, every student at MIT should have someone who believes in them the way Gerald believed in me. And that really struck me. I was head of the physics department at the time, and I really understood what he was saying, that every one of our students should really have someone who's in their corner. I think we do pretty well, but not always. And I just mention it here as kind of a challenge to all of us, not just faculty or not just postdocs, but all of us to, find someone who we can believe in and help in the same way. It's kind of what we're all about. So anyway, I wish I were there with you. I just really am glad that this event is taking place, and I hope I'm sure you're remembering Ray the way he deserves to be remembered. Thank you.
Thank you to Peter. And so now, indeed, as Peter set us up, we're going to have two short talks on this topic that several of us here at MIT have had an enormous amount of fun working on and learning about, and much of that over the last 2 years in very, very close and regular working contact with Ray and this whole group that Peter and I have helped put together. So our first speaker is Alexandra Klipfel. Alexandra is a PhD student here at MIT in our Experimental Nuclear and Particle Physics division of the department. Alexandra completed her undergraduate degree at Caltech. She's worked among other projects on the alpha magnetic spectrometer in their group, and is now a central member of our own primordial black holes research group here at MIT. Her talk today is entitled Primordial Black Holes, Our Only Chance to Detect Hawking Radiation. Alexandra.
Hi, everyone. Thank you so much, Dave. As you heard earlier today, Ray was really excited about primordial black holes as dark matter. And in fact, there are a lot of people at MIT who are similarly interested in detecting, or maybe for Ben, disproving primordial black holes as dark matter. And so much that we've been really fortunate to form this brand new research group here, the MIT Primordial Black Hole Group. Ray was really instrumental in helping to sort of nucleate this group. He came to all of our meetings. He was actually the one organizing the meetings and sending the emails. He attended our workshops that we hosted. Here's Ray. This is our first workshop we hosted. He gave talks. He gave everybody feedback. And I'm just so grateful for his role in forming the group. So I wanted to show a little insight into our group here. So this is an email from Ray back in 2024 February. And we had our very first informal meeting with him. We heard down the pipeline, like, Ray's interested in PBHs, and everyone who worked on them kind of met up with him. And he sent this email afterward that said, "I suggest we meet again." And ever since then, we had these regular monthly and bi-weekly meetings. And then I wanted to just include this email he sent to me because it meant a lot. Peter said he could be very authentic and harsh, but he was also extremely kind, particularly to young researchers, and he really encouraged me to pursue the work I was doing. And then here is Ray's own handwritten notes that he sent around to the group at one point. about direct detection and multi-messenger detection of primordial black holes with LISA, which he wrote here, or gamma rays, which he wrote here. And then this is a memo that he sent around where he really emphasized multi-messenger detection. And he also was super interested in this idea, this kind of wacky idea that we have for building a purpose-built spacecraft to detect PBHs. He jumped onto that, and here he is teaching us how atomic clocks work because we need one on the spacecraft. So I'm gonna give a bit of background about PBHs and talk really briefly about a project that I've worked on. All right, so we have a lot of observational evidence of astrophysical black holes from really hard work people have put in at LIGO and with the EHT, but we need stars to form these black holes. And the first stars formed about 100 million years after the Big Bang. In contrast, primordial black holes as dark matter are theorized to form less than 1 second after the Big Bang. And they've been a topic of study for the past almost exactly 50 years, starting with Hawking and other colleagues in the early 70s. And we theorized that primordial black holes would form by the direct collapse of overdensities in the aftermath of inflation. And this means that the mass of the black holes is just related to the size of the universe at the time of formation, or the Hubble mass, and no longer connected to the solar mass regime. And this admits a very large range of allowable masses, from 10 to the minus 5 grams, which Hawking first came up with, up to on the order of 1 million solar masses if they want to constitute the dark matter. All right, so we're really interested in primordial black holes as dark matter, and they meet all the criteria for candidates. They're very massive, so they're non-relativistic. They could form before BBN and contribute to the non-baryonic matter fraction of the universe, and they would only interact gravitationally. And a lot of hard work has been put in to constrain PBH dark matter fraction, which is what's being plotted here. Fraction of 1 means all the dark matter in the universe is PBHs. And our group in particular is interested in detecting these asteroid mass primordial black holes, which really have this mass the size of an asteroid crammed down into a size of less than micron. And they can even be as small as like a hydrogen atom or a proton. So these things are really difficult to detect. They're very small, they have no accretion disks, and minimal Hawking emission. So it's part of my work and our group's work to try to come up with some novel detection strategies. So a little bit of background on Hawking radiation. Black holes radiate all standard models of particles according to modified blackbody spectra. And the Hawking temperature scales inversely with the mass of the black hole. Here's an example spectrum. You can see a very small black hole will pump out all of the standard model particles. And the point to take away is that lighter black holes are smaller and hotter. And as a result, astrophysical black holes of the solar mass and larger are colder than the CMB. And we would never be able to detect photon or neutrino Hawking emission from them. So PBH is our only chance to make an experimental detection of Hawking radiation. And this emission process is really a runaway kind of positive feedback loop where our black hole is a constant mass over effectively the entire age of the universe, and then it emits most of its mass in a very rapid, energetic explosion, which really happens over the course of about a day. And this is something I'm going to talk about perhaps trying to detect. So we expect primordial black holes to form with an initial mass distribution that has these generic sort of shape. A power law tail to arbitrarily small masses, then most of the PBHs are at some mass m bar, it's very sharply peaked, and then we have some exponential cutoff here. But this is just the distribution at time of formation. As these black holes evolve over cosmological timescales, we have to evolve this distribution numerically. And then our present day mass function would look something like this, a yellow curve here. So if we say, what if we assume all the dark matter in the Milky Way is comprised of asteroid mass PBHs? So we peak our mass function in the asteroid mass range. Most of them are heavy, they're not emitting, they're hard to see, but we're gonna admit some subpopulation down here that would be exploding today. And they would be generating ultra-high energy cosmic rays throughout the galaxy. So what would this signal look like? Have we observed any? And are multi-messenger detections possible, just like Ray was so interested in? All right, so this project I'm going to chat about really briefly was inspired by the KM3Net collaboration observing a 100 PeV neutrino. And our first thought when we heard that is, this could have come out of a PBH. So KM3net has observed one event, and then IceCube has observed 5 PeV scale neutrino events. And what we've been able to show is that you can account for the IceCube diffuse isotropic flux above a PeV with this subpopulation of exploding PBHs throughout the galaxy. So most of them are asteroid mass, this small subpopulation is exploding. And in fact, you can find realistic class of these number distribution functions that can make up all the dark matter and generate to within 2 sigma the observed IceCube flux. And then the last element of this was what would happen if one of these explosions happened much closer than average to our solar system? This would be a rare fluctuation governed by Poisson statistics, and the probability of a local explosion happening close enough to the Earth to generate a KM3net-like detection over the total collecting time scale of IceCube and KM3 is about 8%. And this scenario notably reduces the statistical tension between the IceCube and KM3net observations. So we really have this scenario where we can explain the IceCube flux, we have these mass functions that can comprise all the dark matter, and potentially you have a source for this unknown KM3net neutrino. So this scenario is not excluded experimentally or statistically quite yet, so we want to keep thinking about other ways to test this hypothesis and detect local PBH explosions. And just like Ray suggested, we want to look for photon signatures. So we ask, what would we see in the extremely high energy gamma ray band from such an explosion around 1800 AU from Earth? And though this other group has showed, through some careful work, that the source of the KM3net event neutrino was not within the field of view of LASSO, we can show that LASSO should be sensitive to an explosion at that distance. And this gives us the chance that if another similar event were to happen, we actually have the technology in hand to both detect the neutrinos and the photons that could come out. And the crucial thing here is these would be emitted at a very characteristic ratio that could distinguish such a burst as a PBH instead of, for example, a blazar or another like GRB source. So hopefully in the future we can keep working on this. And then lastly, just a brief comment on some other cool projects our group works on. Most of these were happening kind of while Ray was in our group and he was giving us feedback. So we are looking for Hawking radiation signatures from PBHs in the inner solar system. We're trying to design a spacecraft to actually orbit the sun potentially and detect PBH transits. We can think about even crazier scenarios like explosions in the early universe that could generate the baryon asymmetry. And then also things like black holes interacting and ionizing neutral media in the universe. So thank you so much. And thank you so much to Ray and for everybody in our group.
So again, only in the interest of time, I'm sure you'll have many, many comments and questions. We'll hopefully get to those in the next coffee break. So let me introduce our next speaker. Our final speaker for this short session is Benjamin Lehmann. Benjamin Lehmann has held the prestigious Pappalardo postdoctoral fellowship here in MIT's physics department. He completed his undergraduate studies at Stanford, where he worked closely with Riza Wexler, and then completed his PhD at the University of California, Santa Cruz, working with Stefano Profumo. His research focuses on dark matter broadly, using a combination of techniques from particle physics, astrophysics, cosmology, and black hole physics. At MIT, he works closely with our colleague Tracy Slatyer in our Center for Theoretical Physics, a Lineweber Institute, as well as being another, much like Alexandra, central core member of our research group on primordial black holes. And I want to just add one last thing. Ben was recently named a NASA Hubble Fellow, which I'm super delighted about, which will enable him to stay here in the Boston-Cambridge area for a couple more years. So Ben's talk today is entitled Close Encounters of the Primordial Kind, the Final Frontier for Black Holes as Dark Matter. Ben. So advance.
Thank you, Dave. Ray was so engaged with our PBH group at MIT. He was so happy to talk with some really errant theorists who were looking for interesting things to do. And I want to speak to a couple of the projects that we discussed heavily with him as we were working through them. And hopefully I'll show you a little bit of what Alex was pointing to with these wild ideas for putting spacecraft in orbit. So I come at primordial black holes actually from the dark matter side. I am mostly a dark matter person. And when I think about dark matter, I usually think about it in this plane of its mass and interactions. So we know that dark matter interacts at least gravitationally. We know that its mass is bounded, although albeit not very well. There's 40 orders of magnitude missing from this plot. And most of the effort on the particle physics side of dark matter focused for a very long time on one little lamppost around the electroweak scale. Now, we've had a very successful suite of experiments that have given us wonderful null results at that scale for a long time. And so now there's a sense in the community that we need to think more broadly about what dark matter could be and how do we rapidly explore a wide set of other possibilities. So for me, I like to break dark matter down into 3 broad categories. Most of what we're used to thinking about as dark matter is really the center of this plot, the middle masses. This is particle dark matter, ordinary particles, fundamental particles. If you go to lower masses, then dark matter has wave-like behaviors you can't ignore anymore. And if you go to higher masses, you really should think about dark matter not as being an elementary particle, but as being some kind of granular, composite, or compact object. And of course, this is what leads us to think about primordial black holes. And in particular, I've spent a lot of time thinking about direct detection, laboratory detection for particles in the middle of this range. So a natural question that we posed together as a group was, can we do something similar for these massive granular objects? Now, we're going to probe mostly the asteroid mass range that Alex pointed to. There are a couple of other islands of interest at low or at high masses, but if we want to account for all of the dark matter, we know that there's got to be a substantial component in this asteroid mass range from 10 to the 17 grams up to about 10 to the 22 grams, depending on whom you ask. And so if you want to attempt to do direct detection with particles that are that massive, here's the problem. They're very rare. They're very sparsely distributed. If you compute the average separation between 2 black holes at this mass, if they account for all the dark matter, you'll find that it comes to about 1 billion kilometers. So if you wanted to do the analog of laboratory direct detection, where we use, let's say, a meter scale detector, you would need a 1 billion kilometer scale detector. And the insight that we had as a group was that, in fact, we do have a 1 billion kilometer scale detector available to us, and it's the solar system. The solar system is about that scale, the inner solar system, and it's very precisely instrumented. The hero of the story are the solar ephemerides. I know it sounds like a Greek hero. It's actually these records of the motions of objects in the solar system. And we've been doing this for a very long time. We have very old records. And so it's reasonable to ask whether you could go back through this data and see evidence of an encounter with a black hole in the solar system. Now, we've gotten a little bit better at measuring these ephemerides since the ancient Greeks. So now, for example, we have lunar laser ranging. This actually is the moon, with apologies to Obi-Wan. But one of the other really powerful observables that we have available to us comes from orbiters around Mars. And these orbiters have been measuring the distance from Earth to Mars at a precision of order tens of centimeters for a timescale of order 20 years. So that's great data. Let's see if we could use it as a direct detection experiment. So let me show you a very quick estimate, back of the envelope, of what kind of detection rate we might expect. So let's say I have a black hole, it flies past Mars, it has some impact parameter, B. I can compute the amount of velocity imparted to Mars. That's going to set Mars drifting. It's going to eventually disagree from our prediction of where it should be. And if I want that distance to exceed the experimental precision on the distance to Mars, then I have to wait a certain amount of time, or I need a sufficiently impulsive encounter. And I can translate that to an impact parameter that I need, and translate that to a cross-section, to an event rate. So I can write down the answer. Turns out I should expect, if I have black holes in the middle of the asteroid mass range, I should get about 1 event every 25 years. Interesting number, given that we have 20 years of data. So what we did in the PBH group is we actually made this a little bit more sophisticated. We ran a set of simple simulations with a toy model of the solar system, and we convinced ourselves that, in fact, this toy calculation, which is the dashed lines here, actually does a really good job of predicting at the order of magnitude level the size of the perturbations that you expect. And so we can now translate this to an expected event rate as a function of black hole mass. So here, there are 3 different curves that correspond to 3 different assumed sensitivities. So here is where it became really helpful to chat with Ray. Here, the name of the game is being able to extract small signals from very, very high precision data. And in fact, it really is going to come down to being able to do very, very accurate simulations and to be able to do very, very careful statistical recovery. So the outermost curve here is actually assuming that we can do as well as LIGO does. And of course, that was a fascinating discussion to have with Ray. Now, what I want to point out here is that, in fact, what you want to do is get above this bar. That's where you have a high enough event rate that you really should see something in the data. And you can see that this is actually quite plausible. In fact, this is even a little pessimistic because this is only showing data that you would get from Mars. And as Ray was extremely fond of pointing out, you can do much better if you're more clever. So this is possible. The bottleneck is just that you need to do very careful simulations and very careful analysis. Now, this is possible to do. There is a whole industry of simulating the solar system at extraordinary precision. There are some reference models that incorporate millions of objects and lots of physics. It's a big project to actually do this and get a robust constraint in the asteroid mass range. But I want to point out that Ray had lots of ideas on how to do this well. And ultimately, whatever result we get, we are going to owe it in large part to Ray. So the last thing I want to do here is extend this direct detection analogy one step further and talk about using binaries as paleo detectors. So here the idea is that if you have some kind of very, very low event rate, maybe what you want to do is look for a system where events have been accumulating over a long time. And in the direct detection world, what you do is you dig up crystals and you look for damage tracks in these crystals that have been formed over billions of years. You can do something similar with black holes using, again, astrophysical systems as direct detectors. So here, what you want to look for is black holes ending up trapped in these systems. And the relevant process turns out to be dynamical exchange. So I have a binary that's sitting in space, it's stable, a black hole comes in, there's a 3-body scattering process, the black hole kicks out one of the objects and replaces it. So now you have a binary with a black hole and a star, let's say. And you can go and compute the event rate for this. You can convince yourself that it actually should happen every now and then in the Milky Way galaxy. And not only should it happen every now and then, it actually might explain an interesting astrophysical puzzle. We've detected by now a few binary systems with stars and black holes that look kind of strange, where the separation and masses of these components are incompatible with the observed chemistry of the star. And so that motivates thinking about exchange as a potential origin. And you can actually do the computation and convince yourself that with primordial black holes as dark matter, it is viable. You get the rate that you need in order to make these systems. So it's an interesting hint. Much as I like to disprove that primordial black holes are dark matter, I would accept the opposite conclusion. I'm going to wrap up by saying that I think that we are actually very close to being able to make a decisive test of this proposition. And I'm only sorry that Ray won't be here to see it. And I want to just to say that Ray was such a fun person to discuss any of these problems with, but not just to chat about physics with. It was especially fun to chat with Ray about crazy ideas. Ray was really willing to humor you, and we had some great discussions about some ideas that are sort of on the fringe, but that I think will actually play a big role ultimately in closing that asteroid mass window. And you can see he's in full glory here with his homemade hearing aids so that he could hear women especially. He was very attentive to making sure that he could hear everybody and be a full participant. The last thing I want to say is that Ray and I shared one more thing, which is a German-Jewish family background. Ray was born in Germany, and we're very lucky that he was able to come to the United States and to MIT. His family fled persecution by the Nazis. And we never talked about the extent to which that identity played a role in his life, but I do feel it's appropriate at this moment to offer a Jewish remembrance, that Zichrono Livracha, that his memory should be a blessing, and I'm sure that it will.
Thank you all, and we'll head now to the next session.
Dave, you're up. So this is going to be the longest session of the program. It's going to be perfectly on time because we only have 5 or 6 people speaking.
6.
6.
Plus an interlude, so.
Please, so Dave, take it from here.
Thank you. Thanks very much. Actually, that was a perfect introduction to this part of the celebration of Ray's life. For those of you who don't know me, I'm Dave Reitze. I'm the executive director of the LIGO Laboratory, based at Caltech. With Peter and Lisa, we've selected 6 very distinguished speakers that are going to really focus in on the gravitational wave part of Ray's career. We're going to start with Fred Dylla. Fred has a very distinguished career. He's an MIT graduate, I think both BS and PhD, had a long career in Princeton and also at Jefferson Laboratory. I think he was the chief technology officer there. Became the president of the American Institute of Physics, also did a stint as the president of the American Vacuum Society, which is very appropriate because I think you're going to be talking a little bit about that. So I'm going to turn it over to you. Thank you, Fred.
Thanks, David. It's wonderful to be here. As David mentioned, I was Ray's student both as an undergraduate and a graduate, along with his colleague, John King. They were 2 of the best experimentalists I have ever known in my life, as most of you will agree hearing what you did today about Ray. But I want to come back in a little part of his career when he was just finishing up with Zacharias and the molecular beam lab and starting his own lab in the famous Building 20, which we just had a marvelous film about. So the Plywood Palace, that was affectionately known by many who worked there. It was, as you could see from the film, a wonderful place to have a laboratory, because if you just needed a hole in the ceiling, you put in a hole in the ceiling. And you could build all sorts of apparatus without asking physical plant or permissions. And this picture has been shown before of Ray shuffling down a Building 20 corridor. I always remember Ray either sitting in front of a box of electronics, fixing it in a t-shirt, or wandering around asking you a good physics question in his blue Oxford shirt. His advisor, you've heard this morning, was also an amazing physicist, Gerald Zacharias. He was instrumental in the Manhattan Project, of course. He was the engineering manager out there, and also very important for the development of radar. And when he launched his career at MIT, he started the molecular beam lab. I remind you that many of the Nobel Prizes out of the 30s and 40s and 50s were molecular beam based because you could do measurements on small numbers of atoms. Zacharias is most famously known for his cesium clock, the first really good atomic clock. And here's a picture of Zach with John McLean, one of the able techs there, with a molecular beam. Now, a molecular beam tells you a lot about doing null experiments because from a famous book that Norman Ramsey wrote on molecular beams, the inside page says it's all a matter of intensity. And you're either trying to boost the atoms coming out of your source, you're trying to boost the sensitivity of the detector to detect an ion or a molecule. And it teaches you a lot about basic physics, a lot about instrumentation, and a lot about vacuum, the unsung hero of LIGO. This is probably something that most in the audience are unaware of. You heard about an ion source this morning that Ray built to discharge electrostatic problems in LIGO, but this was his first ion source. This was an ion source built for the front end of a mass spectrometer that would very efficiently ionize neutral atoms or molecules so you could detect them.
It, in fact, is still the world's most sensitive ionizer. It had a sensitivity of about 2.5%. He wrote it up in a 1961 article in Review of Scientific Instruments, one of the few publications that he didn't do in the 60s and 70s in the Quarterly Progress Report of the Research Lab of Electronics, a real article. That's still the world's record ion source. I, at the time, was just beginning to work in John King's molecular beam lab, shuttling between the Building 20 lab and the Building 26 lab, trying to put together a molecular beam apparatus. And I tried to find that apparatus, but it had evaporated. You also heard this morning that Ray had been thinking about doing experiments in gravity for quite a while. You saw one this morning. Here's one that he again described in the Quarterly Progress Reports, number 58 in 1960, where he proposed a gravimeter by looking at a Stark shift in a CO molecule. And you can see a relationship between delta G over G. It was translated into a frequency measurement at about 10⁻⁻10. And then the rest of the article delved into all the problems with this experiment, noise source by noise source, and why it was probably not a good idea. You've seen this picture before. We don't have enough pictures of Ray in the laboratory. I'm glad we have that movie. This is how I usually saw him wandering into the lab, asking him a question about something or wanting to borrow some equipment. And here he's on to his next regime of experiments on the cosmic microwave background that we heard about so well this morning. You saw this picture too. Another one of the gems of Building 20 was this anechoic chamber. And we learned there was probably a noise measurement for one of the laser systems done in this room. I grew up with Ray and John King learning the value of null experiments. You need stamina to do a null experiment because you always measure something. And you have to identify what that something is and get rid of it. It was good training for a young physicist. It was good training for eventually building LIGO. My null experiment was built upon an idea that John King had on, can we test how accurately the magnitude of the electron charge balances the proton charge? Now, modern theory says well, they're precisely equal, but there was an old supposition from Einstein in around 1916 said, suppose the charge balance weren't quite equal. What would you need to explain the known rate of expansion of the universe? And it was about 10⁻⁵. That's a daunting measurement to make, right? 10⁻⁵ of the charge of the electron. And I spent 3 years in getting a limit of 10⁻⁻21 that John and I published. That's a picture of me in a very, about the same time. You can see I was stuffed into a basement lab. I didn't have room in Building 20, except for doing the experiment in the anechoic chamber. I needed, just as Ray had to stop the traffic for an early LIGO prototype, I needed no street noise. And the best way to do that was to pull the experiment into the anechoic chamber. And for 2 months, I got third shift from 1 a.m. to 5 a.m. because Professor Bose had the first 2 shifts for his microphones and speakers. Now, let me jump forward to my MIT career. I went to a place on the right, Princeton Plasma Physics Lab, and helped build the 3 large tokamaks there. And then I went down to Jefferson Lab and helped build the superconducting LINAC there. And as Ray was designing with his colleagues LIGO, as you know, it's mostly vacuum system. It's got a very bright laser and very good optics, but it's the vacuum system that could ruin the experiment. And he knew that I had lots of experience with leaks on complicated vacuum systems. Certainly the one on the left, I had 2 kilometers of superconducting cavities with about 10 to the 5th seals. So if any one of them leaked superfluid helium, the LINAC was not useful. So I remember in the early days of LIGO, him calling me up and said, "Fred, let's talk about leaks. I know you could write a book called Pathogenic Leaks You Have Known, but you gotta help me with make sure the 16 kilometers of LIGO is leak-free." I continued to help him with what you're going to hear about in the next talk. We have run 3 workshops, starting with one at the LIGO Livingston site on how you would design a leak-free vacuum system for Cosmic Explorer and the Einstein telescope. And his favorite picture of mine and Ray and a good metallurgical engineer friend of mine, Dan Henkel, who discovered that the primary source of leaks in LIGO Livingston were little bugs that would eat through the stainless steel. That didn't happen in the Washington site. And I want to close with just reading one of the gems I found in the quarterly progress reports. And this was from 1974 when he was just burgeoning out into gravity work. This is the last paragraph of the quarterly progress report for January 1974. So we're about 2 years into LIGO prototypes. "Our objective is to carry out an experimental investigation of gravitational interaction which embraces terrestrial experiments and astrophysical observations. For several years, the work of this group has covered a broad range. Experiments have led to development of long-term stable gravimeters, laser strain, seismometers, and molecular beam frequency stabilized lasers. We have also measured fundamental phase noise and made preliminary designs of gravitational oscillators for spacecraft experiments. Astrophysical measurements have been carried out to measure the spectrum of the cosmic background. And we've studied atmospheric emission and far-infrared properties detectors. The inner logic or coherence of this research may not be immediately apparent. A listing of our projects demonstrates, however, that gravitational research, at least in its experimental aspects, is bound to have many facets and to spread out in various directions." So thank you very much.
I think in the interest of time, we're going to probably just move on through the next talks, but I will encourage you, if you are curious about the bugs and the vacuum system, to talk to both Fred and Mike, because the story is really quite interesting and it involves more things than just bugs and iron and things like that. So I'm very pleased to welcome Mike Zucker. Mike is a senior scientist in the LIGO laboratory. He's had a very distinguished career throughout LIGO. Some of the things that he has done include he was the site head for the Livingston Observatory during a very formative period. He led the recent A+ upgrade project, which is delivering the most sensitive detectors to date. Mike's got his PhD from Caltech, and I believe he probably has the honor of having the largest fraction of his life actually spent in gravitational wave detection. I think that's true, and that's squandered. Well, it was squandered until 2015. So now let me turn it over to Mike, who's going to talk a lot more about the vacuum system. Mike.
Thanks very much, Dave, and thank you, Fred, for the intro. That'll help a lot. Again, my name is Mike Zucker. I've been with LIGO since before it was LIGO. I actually know Ray not as a student or a postdoc of his. I came through an independent channel directly into gravitational waves. I worked in the gravity wave Weber bar group at University of Rochester with Warren Johnson and Dave Douglas in the late 70s, early 80s, and then went on. I was a technician, by the way, undistinguished academically, but the gravity wave connection was helpful. And I went on to grad school with Stan Whitcomb, who's here, and Ron Drever at Caltech in 1982 or 83, I think. I didn't interact directly with Ray because I was in the other camp. In fact, I think Ray was quite suspicious of me, partly because I was Ron Drever's student, but also partly because of the Weber bar connection in my past. But as we kind of launched toward a union of the Caltech and MIT group, what was often referred to as the shotgun wedding, I think. I think I saw Rich Isaacson here. Hi, Rich. And Bob's here too, right? Anyway, at that point, we began to merge. And at that point, Ray and I found ourselves working solidly together on a huge variety of topics. You know, everything from lasers and so on for the proposal, for the LIGO proposal, to things like how to speak to Ron Drever and work with him, things like that, that we helped each other. And through that, we forged a really solid relationship over the years, and we talked about many, many things, shared a lot of important things. We were both fascinated with technology. I think it helped that I was before the mast, as it were, and immersed in technology and maybe not so immersed in my studies, maybe a little bit like Ray at one point or Lyman, and that helped us find a connection. So what we did together was a huge variety of things. The things that Dave asked me to talk about are the vacuum system. And so I've told a little bit about how we got involved. And I'm going to tell you a little bit about why it was such a problem. It's not a glamorous problem. There are very few people who would kind of volunteer for this kind of work. But it had to be done, and both Ray and I found interesting and important things to learn about the world in general, about instrumentation, about how to do things in this quest. So the big thing is that NSF also agrees that vacuum is important. I just wanted to put this up, that that was on the front page at the announcement of our discovery. There was a snafu in the mailroom. You've all seen this picture of the quarterly report where Ray laid out the dimensions, the constraints for an interferometric gravitational wave interferometer. And you can see, circled in red, it is noted that it's a vacuum system, but you'll also note from Peter's talk this morning that that was not one of the noise sources calculated as a limit. And that's partly because it just sort of seems obvious. It has to be in a vacuum. You couldn't possibly imagine doing a precision interferometry experiment in the atmosphere. There would be all kinds of things that would interfere with that. There would be the viscosity of the air, which would damp the mirrors, that would influence them. There would be acoustics. There would be transmission of heat to the mirrors and so on and so forth. You can think of a lot of things. The thing that was the most important thing wasn't really appreciated right then, but it was appreciated soon thereafter. And that was the refractive index. You can think about the refractive index of the normal atmosphere, of course. It leads to a lengthening of the path length, the optical path length, the delay of the optical phase. And in this vacuum regime, you can also think about it as the impulsive change in the optical field as a molecule passes through the beam and scatters the field. And of course, you can calculate what the magnitude is by just basically taking the pressure up to atmosphere and equating it to the refractive index at nominal pressure. But this calculation was done after that quarterly report, and it appears in a rudimentary form in the Blue Book, which you've also heard about this morning, in which Ray and Peter Salson, who's here, and Stan, and a few other people laid out a kind of an engineering estimation for how you would proceed to build a multi-kilometer gravitational wave detector using interferometry. And in this Blue Book, you do see calculations for all the main noise effects and their direct impacts on the engineering constraints for a LIGO interferometer. And in one particular point, it gets a little bit weird. You can see here, equations 13 and 15 were this rudimentary calculation of the residual gas phase noise. And Ray kind of says, instead of evaluating the requirements for pressure, let's just see what kind of pressure is practical and work from there, because the answer was kind of scary. As you saw from Fred's talk and from some of the things that you've also seen earlier today, there's a nominal vacuum regime called high vacuum, which is something like a billionth of atmospheric pressure, which is typical of like vacuum tubes, television tubes, things like that, typical of most experiments, like molecular beam experiments that Ray had worked with clocks. And then there's a whole nother regime, ultra-high vacuum, which is a trillionth of an atmosphere. And Ray was sensible enough to realize that you could contemplate making a multi-kilometer machine using conventional technologies, things that are familiar from the vacuum tube industry or so on. But if you needed better than a high vacuum, it was very hard to contemplate how you would scale that up. Typically, if you wanted ultra-high vacuum, and this would be at that point in time typical only of things like particle accelerators or very specialized experiments, you needed to actually remove contaminants that are dissolved in your stainless steel, the primary one being hydrogen. And the way that that was done, and the way it still is done conventionally, is to bake steel very, very hot, 800 C or so, in a high vacuum to deplete the hydrogen from the raw material before you begin your experiment. And Ray was correctly horrified to think about trying to do a 800 C vacuum bake on 1 million pounds of stainless steel in a multi-kilometer structure. It just couldn't be done. So that's why this treatment and the LIGO proposal kind of said, well, let's do the best we can with our initial requirement, and then let's have a goal, which is actually what we think is good enough to detect gravitational waves, and think about that tomorrow. The problem is, by this point in LIGO, tomorrow was today. We really had to confront the fact that, and Fred will tell you, and anybody else who's done a vacuum experiment, you can't pump your way out of trouble. You have to construct the device out of a material that's compatible with ultra-high vacuum to have any hope of ever getting ultra-high vacuum. And here we're talking about making a multi-tens of millions of dollar investment, and it would have to be compatible with the ultimate goals that we had for the system. So we needed a better way. And that way came in the form of an idea had by, was I think LIGO's first actual vacuum engineer, Bowd Moore. Yeah. First I'll point out that another thing that was in the proposal was we were basing all of this planning on a theory for how the gas interacted with the beam. It wasn't until 1992 that Stan and I had an interferometer sensitive enough to actually test this. This is the 40 meter at Caltech. And I have to say, when we finally did this experiment in '92, Ray was immensely relieved because he said that was a real monkey off his back. If they got that calculation wrong, it was one of these many, many millions of dollars risks that we would have taken. So it was lucky that it was right. It was unlucky that it was right also, because it meant that this very stringent requirement was for real. In that proposal, though, we had at that point done some homework with an idea by our first vacuum engineer, Bowd Moore, who had a proposal to deplete the hydrogen in the steel during the milling process, basically at the steel mill. And we had actually tried that on a couple of small chambers. These were built up at Caltech. An engineer named Larry Jones, myself, Ray, and Bowd conducted some hydrogen tests on these small chambers and showed that, in fact, the hydrogen outgassing from standard stainless steel could be depressed by about 2 orders of magnitude with this relatively cheap process, baking the steel as coil stock right out of the mill in dry air. And Ray seized on this as the way to get what we needed for a huge production. This was only these samples were available at the time of the proposal, but we bet the farm on that. And of course, Ray insisted that we really needed to prove that this magical kind of freebie depletion would be preserved if you actually made an actual usable beam tube out of it, an actual LIGO prototype. And so at that point, we embarked on a mission to build some sample tubes using an industrial supplier in California, Pacific Roller Die, and built up some test tubes, which we called, I think, the beam tube demo in the synchrotron at Caltech. And unfortunately, I cannot find any pictures of the beam tube demo. It turns out I don't have to, because in '92, I recycled all those beam tubes into the 40 meter. The beam tubes in Rana's lab right now are, in fact, the first industrial production of low hydrogen steel for LIGO. Only 2 feet in diameter. We couldn't quite get the dies to build a full 4-foot tube, but they turned out to be great for building a prototype interferometer on campus. So these are the original beam tube demo tubes that proved the method for building low hydrogen beam tubes for LIGO. The other thing, which you've heard a lot about from Fred and from others, is the problem of detecting leaks. And here's another thing where we really had to think outside the box. Principally, Ray did. The traditional way of hunting leaks on a large system is to actually spray helium and look for helium inside the system coming in with a mass spectrometer. If you think about the logistics of doing this on kilometers of tube with time constants of half an hour to an hour, with the surface area of so many square meters, it was not practical. It would basically mean that the program, even if we could do it cheaply in terms of material, the standing army costs to accomplish this and the schedule delay to accomplish this to a satisfactory level, we had to be leak-free to about 10 to the minus 9 torr liters per second, would be prohibitive. But Ray devised a workaround, and this was to model the gas in the tube, measure it as accurately as possible with residual gas analyzers, and try and invert the magnitude of a putative air signature in this mess of gases in this newly evacuated tube, and put an upper limit on the amount of air that could possibly be leaking in. And you'll look at this. This is a very simplified flow chart. Ray had something like 29 pieces of code, all written in Fortran, thousands of lines of Fortran, that he himself wrote in order to intake the inputs from several hundred RGA channels, invert the cracking fractions for all the gases found, invert the sensitivities, the temperatures, because those affect the gas flow, and so on, and come up with a statistical upper limit, if you will, on the modeled putative air leak in a given tube. And we did this 2 kilometer section by 2 kilometer section for the entire 16 kilometers that went into LIGO. Ray also designed a very sensitive calibration system in order to make these RGAs produce reliable data that was calibrated in physical units. So all of this was done by Ray. Ray personally certified every beam tube. Now you think about it and you say, well, what if we had had a leak? What would we do then? And then the problem gets really tricky. You have to localize it. So in addition, Ray was ready with a system for modulating the pumping conditions at different points of the tube and looking for the spatial and temporal distribution of a putative leak to try and localize it, at least to some degree, so that then a normal helium leak checking procedure could find and pinpoint it and hopefully fix it. And so he developed this. Fortunately, all 16 kilometers of LIGO turned out to be leak-free to the required accuracy, and he never had to deploy this leak localization procedure, which was as elaborate as this was even more elaborate. He never had to apply it in anger until 2012, when microbes ate through the Louisiana tube. And then Ray did, in fact, reconstruct the locations of 2 leaks to something like 10-meter accuracy using this formalism. Another problem, of course, is water vapor. Removing water vapor in conventional systems is only a matter of baking them. But of course, here we're talking again about baking an enormous quantity of steel, an enormous volume, an enormous surface area. And we're trying to do that in a very short time and with a very limited budget. And so it's essential to understand the dynamics of the water that was absorbed to the surfaces and how to get rid of it in the most economical and reliable way. Here again, Bowd-Moore kind of put Ray onto the seed of an idea and exposed him to a concept that was called the isotherm binding energy model. And he in particular was favored a formalism called the Dubinin-Radoskevich isotherm models. And Ray ran with that hint and developed a complete formalism for how you determine the binding energy and the desorption energy of water vapor as a function of the surface population, the density of states on the surfaces, so that you could say how much baking is enough. And so that was another successful application, and that turned into, again, a mass production process for the LIGO beam tubes. Again, Ray supervised the baking of the LIGO beam tubes and the certification after baking for surface. I won't say much about this. I hope Stan can say something about it, but scattered light was another crucial thing, and here I'll just point out that here Ray worked with Kip Thorne, who's also in the audience here, to determine the correct formalism for understanding the interference of scattered light from the mirrors with the beam tube walls. The process that we were worried about was scattering from the mirror, which is, of course, one of the smoothest objects ever made, with the wall of the beam tube, which is one of the roughest objects you'd want to find, and then rescattering into the interferometer mode on another mirror surface. Kip and Anna Flanagan produced a very good formalism and even a recipe for how to serrate the edges of the baffles to break up any potential coherence. But it was left to Ray and a bunch of people, including me, to figure out how to make the surface black enough and non-reflective enough that it would be suitable for LIGO and also suitable for economical mass production. Many stories about this. At one point, Ray climbed in 1 kilometer into a beam tube through all these toothed obstructions to diagnose a problem. That's a story for another day. Again, we built the beam tubes, and you've all heard LIGO has been successful. These are just some snapshots from the field. Again, Ray was deeply involved in every stage. And that would be the end of it, but of course, nature abhors a vacuum. You heard about the leaks that happened in Louisiana. Here's another episode, not at LIGO, but in Virgo. Here's Ray working on an apparatus to characterize the implosion of viewports. There was a catastrophic viewport implosion at Virgo in 2008. And Ray led the effort to understand, first of all, what happened in Italy, and second of all, make sure that we weren't vulnerable to the same thing. And at the end, we collaboratively came up with an understanding of what had happened at Virgo and a completely new appreciation for what can happen if you break a viewport. And right now, people at the LIGO sites go through significant training to understand the risks associated with glass ports on an evacuated system. This is a picture of Ray's bomb. This is now in the possession of Albert Lazzarini, who is again blowing up viewports in Pasadena now. And he's enjoying it too. Peter already introduced this for you this morning. This again was born of the charge. This is Ray's lab book diagram of the circuit for this. This is a Widowmaker, a 3 kilovolt transformer, no switch, no fuse, wires hanging out all over the place. LIGO Engineering took it quite seriously and engineered a safety certified version, which is the one that's on the interferometers now. But this again was entirely hand built by Ray and tested in the MIT lab. And then Fred also mentioned that Ray was a key founder in this joint working group that we now have going with ET and Cosmic Explorer vacuum people. This is a group that we convened. I got a small grant from the NSF in 2019 to have a workshop on how to take the largest ultra-high vacuum system ever built and make one 10 times bigger. And this was a hugely successful thing. And as Fred mentioned, we've now had 3 of these workshops. Ray participated in the first 2. Sadly, he passed before the most recent workshop, which we completed in October. This was Ray's passion, and I'm showing on the right an idea which I considered crazy. It was actually my idea, and Ray loved it. He kept working on it long after I thought it was nuts. But this was an idea for a nested vacuum system that had an ultra-high vacuum liner that was very pure and clean, and a structural outer shell to act as a pressure boundary. He liked that idea quite a bit, and he did quite a bit of modeling and work on it in his later years. But Ray was very enthusiastic about Cosmic Explorer, and he participated in our bi-monthly calls with CERN and with the CE vacuum community pretty much right up until the end. So that's all I have. I just want to show this picture. It's actually, the original is on the table in the front room. And this is a photograph of Ray giving a lecture. I think this is at Big Pasco in Washington State. This is the factory where they were building the LIGO beam tubes, running them off of the mill. And Ray is giving a lecture about gravitational waves and everything else to all of the Boilermakers on site. And I want to point out a couple of things. First of all, as many people have said, Ray was very generous and very humble about his time to talk with anybody who could learn from him. But I also want to point out that this is a bidirectional interaction. Ray learned from everybody, And he spoke to these Boilermakers, and they spoke to him, and he learned about welding, about materials, about all kinds of things that he needed to know in order to come up with these brilliant inventions that he's given to the world. And I think it's important to realize that Ray took from everybody whatever they had, and he gave back everything he had without restriction and without prejudice. So I really want to thank Ray for all he's done for us.
Thanks, Mike. I think it's safe to say that we could basically spend this entire symposium talking about vacuums, but we've got much more to talk about. So I want to bring up Joe Giaime. Joe is a professor at Louisiana State University. He is the current head of the LIGO Livingston Observatory. He succeeded Mike, and he was a student of Ray's, so he's going to give you a slightly different perspective on Ray and Ray's career. Joe.
Thank you. Some of the things I have in my slides has been covered already, so we might be able to make up a bit of time. So I first heard about gravitational wave detectors and that one could have a career in physics at the same time. And when I was in 7th grade, I grew up in Yorktown, New York, where Darwin and Levine had just sort of shown in their laboratory that the Weber bar probably wasn't detecting gravitational waves. And this was conveyed to me by my 7th grade pal, James Levine's son, and I had no idea what he was talking about, and it kind of disappeared in my head. And I remembered 10 years later when I was looking for something to do after undergraduate, and I remembered reading about that Weiss was doing this at MIT. So I had no connection with him when I was an undergraduate there, and found him willing to hire me as a technician while I was trying to figure out how to apply to grad school, a technician in his lab when I was a technical instructor too. And one of the many people who washed up into Ray's good hands without really necessarily, I certainly didn't deserve it. I just sort of showed up. This is a photo I took of him having just gotten back from a wedding or something. I had a few frames left in my camera, and you can date this by looking at the little artifacts. There is a pipe visible in the lower left-hand corner, so this was before his heart attack, but it was in the newly renovated lab space, not the one shown in the cool movie we just saw. And he's having a lunch from Au Bon Pain, not from the F&T. So I know what's in that because he ordered the same thing every day. And that's a half brie sandwich with no mayonnaise and a very, very large coffee, at least for its day, large coffee. Anyway, so when I finally did apply to graduate school, he went to the committee meeting and put his foot on the scales, I think, and came back and that was he left that on my desk, saying that I probably was going to get in with that thumbs up. That was a little Post-it note. I lost it for many years, but found it again in my piles of crap, and so I scanned it in. All right. So all the actual content in this is on this slide. The rest are just pictures we can play with. So why did his lab work so well for his students? Specifically for his students. He was really, as you've heard over and over today, he was personally interested in each of his students' progress and everything else about them. He helped us with our problems. He carried around ether in his car to start it. He would start our cars with this ether when necessary. I don't think that works anymore. And when we had problems with the general exams, which sounds like it was most of us, we called it, the nickname we had, what was reform school. He had these sort of standard problems in quantum mechanics that he would make us go through that were kind of designed or maybe just had that effect of giving you lots of physical intuition at the same time and were useful later in life, mostly atomic physics anyway. He really respected everyone who worked at any level, leading us to all respect each other. Everybody helped each other in that lab. No one held back if they had something to help about. And that's not always true in workplaces. From time to time, most of us would find a sheaf of paper. You've seen many images of it on that green engineering sheet. Some of them were quite thick. The thickest ones came after he was away on vacation. He would come back and give us his thoughts on what we were working on, and it was just pure gold. Those sheafs of paper. The lab had a well-stocked mechanical, electrical shops and other things like that. Decades of slightly used instruments. We could build anything we needed in that lab if necessary. Instead of buying them, we made our own optical table dogs in the shop. First time I visited Caltech, I was amazed that people bought these things. Anyway, the last one's in gray. So I think that when we made the discovery, his worldview of what theorists are good for changed a little bit. He always had great respect for Kip and a handful of others, but I think now later in his life, he really did reform there. Okay, so again, I'm talking about the eras of students and not so much the details. I know I have left names out. I've realized this as I've been sitting here, so I apologize for that. There was the kind of gravitation and cosmology research group era where a bunch of things were going on. Kobe, the balloon work, infrared measurements of the CBR, Steve Meyer, Patrick Downey, those names. You've seen some of these pictures before, so I can go through them quickly. There's Steve and his wife, and you can see these are some detailed photos of the 1.5 meter when it was in operation. So after it got wrapped up for the movies, they did the renovation and they unwrapped it again, and we ran it, or the group ran it there briefly. And most notably, when I was there anyway, it was last really run after Supernova 1987A. So this was kind of cool, first supernova in a long time. So even though the thing couldn't have been possibly sensitive enough to see a supernova signal, ran it anyway. And so us kids, the people who had just arrived in the lab, thought that was really cool. All that running around with tapes and everything. And I still remember it quite vividly. Okay, so there's some pictures you've already seen. This is the photodiode suspension. So now the 1.5 meter prototype delay line detector, slides end. Okay, so meter scale LIGO R&D in the late 80s and 90s. Peter did a great job of describing these things and some of the pictures. Some of the pictures here I don't think were in Sloan before because I took them, but they were the same thing. These yearly hikes where Ray came along and there's Dick Benford, and there's Michelle. She's in the room here. Michelle Stevens, and Nelson up in the left-hand corner. Okay, there they are. So there's Michelle and Nelson and Peter Fritschel. Peter and Michelle and I arrived, and Joe Kowalik arrived around the same time. I wasn't a student yet. Nelson was a bit older. And so one of the things we did is we helped build this, what we called a 5 meter prototype. It never actually operated as a Michelson interferometer as far as I know, but we called it that. And it involved some serious kind of heavy work. There I am next to a seismic isolation prototype of a kind that you never see photographs anymore. So this kind of hits the theme that we talked about before. If you look on the table of artifacts outside, there's a prototype seismic isolation spring that was meant to have the same stiffness vertically and horizontally. And then there would be these round stages that the springs would be connected to on these little cantilevers that came out. So we didn't realize it at the time, but this basically makes every possible mistake that you can make when you design a seismic isolation system. You have the stages really wide and not stiff enough. You pre-mount your springs on cantilevers so that all those degrees of freedom in the stage are well coupled. And it turns out it does not matter if the springs have the same stiffness vertically and horizontally. It doesn't help at all. So we got it. So we by spending some time with this, it was decided that I needed to go and start doing some modeling, totally against my natural inclinations, right? So stop building things, stop cutting any metal, no more of this crap, right? And so that's why later it looks more like that. That was the prototype of the one that eventually, with some significant improvements, ended up in LIGO. And there's a picture from the time. This is scanned from a Scientific American article. I have the original somewhere, I just can't seem to find it, with Joe Kowalik in the upper left-hand corner, Yaron Hafetz, Nergis Mavalvala, Ray, and David Shoemaker. Okay, so there's Michelle with her project, one of her projects, which was a nested, I believe she will correct me if I'm wrong. She was working on a project that had a 2-stage suspension, test mass suspension, where the stages were nested, which was kind of a cool idea at the time. I don't think it's been followed up on since. And there's Joe with a a piece of fused silica. He was working with Peter Salson to measure the thermal noise in the silica by making an interferometer between two places on the front plate. So music was really important in Building 20, not just among our group. We had a Building 20 concert more or less every year, and there's kind of the bunch. I'm playing viola there in the lower right. In this picture, there was sort of fairly unusual things. Maureen Horgan played the trombone. A professional trombonist in those days, who happened to be a woman, was hard to find. Violists are always hard to find. And then Joe Cavallo had a natural, deep bass voice, and the person next to him, whose name escapes me right now, was a countertenor. And so we put these things together in various combinations. Okay, so when I left MIT after graduating, I went to work at Dylla in the University of Colorado. And one of the things I learned there was how to grantsmanship and sort of planning projects. Because despite the fact that all around me while I was at MIT, one of the biggest and most successful projects was being planned, I wasn't really part of that writing. Instead, I was exposed to things like this. The Blue Book, which estimated that the cost of construction for LIGO would be 17 million. And this was the schedule we were working out of when we renovated the lab. The whole thing was supposed to be done and having a working interferometer in, I think, 13 or 14 months. So I grew to be very skeptical of these. Jeff Livas and I used to joke around that he said that if you let too many people decide what the elements of the project are, you'll end up with a lot of things that never get done. And one of them, his poster child for that was the sink in the high bay never had hot water. But it was always on the list to get hot water in the high bay. So whenever people had time, well, let's work on the hot water in the high bay. All right. Okay, so I went through the theses from the group that have been sitting on my shelf all these years and excerpted some things that people had written about Ray in the acknowledgement page. A number of these, I'm not going to read them all because I honestly can't from here, but that one that sort of runs around in the middle toward the bottom, to Ray, who talked to me one Saturday morning and set me off in a new direction. And that was not uncommon for talking to Ray on a Saturday afternoon. Not all of these were his students, by the way, but all these people who were affected by them. And I think that, I got to read one of them. I can't do it from here. Sorry. I'm going to get in trouble. So the one in the middle towards it, I would like to thank my supervisor, Ray Weiss, whose relentless pursuit of scientific excellence has allowed me to investigate many different aspects of experimental physics. That was done, I think, during year 8 or maybe 9 of that year's studies. So anyway, I don't have to belabor this. All right. So on the other hand, there's Nelson Christensen. He was somewhat notorious because he got Ray angry at something in an epilogue. And he said somewhat negative things about his time in graduate school. And then in that second paragraph, he wrote, "The situation at MIT is not hopeless." Now, Ray got upset at that, but Ray forgot that after all those years, Nelson started talking like Ray. And when Nelson wrote, "The situation at MIT is not helpless," what he meant was the situation at MIT is going to lead to Nobel Prizes and so on. So I think it was just a simple misunderstanding. But after this, Ray insisted on reading the whole damn thesis before he would sign it for each of his students. Okay, so Joe and I, we had sort of the same damaged sense of humor. So these were our 2 ID cards when we showed up in 1986. Look at those guys, ready for action. And then MIT changed its system for IDs, and we all had to go. We were all forced to schlep over to the office, hand in our old IDs, and get new ones. We had to keep them. We had to show our IDs and get new ones. And these are the new ones after for some significant number of years in the coal mines. And so the same guys, but you can judge for yourself what happened to us. I mean, so I have to add, this is somewhat off topic, but in 2018. There was an event at LSU that Ray attended, and he was invited to give a commencement address. And I got a nice photograph of him speaking with Bill Hamilton, who was a bar antenna pioneer who built and operated probably the best gravitational wave bar at LSU for some decades. And the two of them are having a genuine drink together, which is, I think, what Ray always figured was the best way to spend time with your friends. Okay. So somebody, not me, while Building 20 was being demolished, set up a time-lapse movie from one of the roofs nearby. And they had this posted on the website back then, when I think 15 years ago when I stole it. So that's really all. Thank you.
Thanks very much, Joe. Good to know that the situation at MIT is not hopeless. That is very good to know. Our next speaker probably needs no introduction to most people here. This is Stan Whitcomb. Stan got his PhD at the University of Chicago as an infrared astronomer, promptly went to Caltech and got all excited about gravitational waves, has been with LIGO since before it was LIGO, has held, I think, most of the leadership roles in the LIGO laboratory, and I'm sure he's going to give us a very interesting perspective.
Thank you. It's a great honor to be here. I'd like to talk to you about the origins of LIGO, Ray's role in that, and in particular, I'm going to try to highlight the particular things that he contributed that I think are the most important. I'm going to do that in framing it using three key documents: Ray's RLE paper, the one he published, I guess, in 1972. 1973 seems to be a typo there. He was very proud that that grew out of that undergraduate seminar that he gave. The Blue Book, which you've heard about, and then the proposal. And I'll use those to highlight Ray's contributions. Of course, Einstein predicted gravitational waves in 1915, but the assessment at that time was that they weren't going to be detected ever, probably. And so they remained off the radar for about 50 years. And then in about the mid-60s, Joe Weber started to build his bar detectors, and in 1969 he announced that he was seeing evidence for gravitational waves. That triggered a sudden and intense interest in gravitational wave detection. Roughly a dozen groups around the world began to design and build bar detectors, many of them with improvements upon Joe Weber's original designs. But it also started a search for other detection techniques. And among those, I mean, there were all kinds of things. Direct detection, conversion from gravitons to photons in microwave cavities, sensing the Earth to the moon distance very accurately, Doppler tracking of spacecraft. Everything was talked about, anything that had a rough idea. Laser interferometry for gravitational waves must have been an obvious choice. That was suggested at least 4 independent times that I know of. Ray's RLE paper was one of those independent inventions. But that's not what's important about Ray's paper. What's important about Ray's paper was his detailed noise and sensitivity announcement. He went through and identified all the possible noise sources he could think of, and then not just identified them, he made a quantitative estimate for how that would contribute to the detector sensitivity. Every one of those has a detailed analysis. Ray's scientific style shows through in that paper. It's 24 pages, it has 72 equations and 1 figure. And for those of you who know Ray, that is his style. He wanted everything worked out deeply with full mathematical basis. So that paper started Ray's interest in gravitational waves, and indirectly or directly, it triggered a number of other groups around the world. Max Planck Institute in Munich, Glasgow, and eventually Caltech, all started building gravitational wave prototype interferometers. And so by a decade later, I'm going to go back. For those of you in the audience, you might say, well, of course you would do a detailed analysis of a noise source. That was not the case in 1972. I looked at some of the other papers from that period of time. People would make statements like, well, I tried several different seismic isolation systems, and this one worked, and so that just proves that it's an art and not a science. People were doing that kind of thing. Ray would never do that, and he really impacted the way all of us have approached gravitational wave detection. By a decade after that, Ray had turned in a slightly different direction. There were gravitational wave prototypes, interferometer prototypes being built around the world, several of them. Ray started this engineering study. It was a complete science and engineering feasibility study. If you look at the chapter titles for this, here it talked about sources, about the physics of detection, how the prototypes were performing, noise sources, how you would build the vacuum system, a site survey, the construction details, and a proposed design. You start to see in that paper designs for the cross-sections of the vacuum system that look an awful lot like what was finally built. Nobody else was doing this kind of engineering analysis. Ray really led the synthesis between science and engineering that eventually proved to be absolutely critical for LIGO. He was talking to the engineers and getting their inputs. This wasn't a perfect thing. We saw Joe's estimates for the costs that came out of this blue book. It's not perfect, but it's a big start, and it was an innovative thing to do. Nobody else in the world was even thinking about starting to talk to engineers about how you go about making a real LIGO. The real innovation there was that. And in fact, you start to see designs for how the vacuum systems would actually fit, how you would have enough headroom to be able to lift off parts of the vacuum system and assemble them. All of that, Ray was the first one to recognize that those things needed to be done, that there were engineering challenges that needed to be overcome. It was a lot less glamorous than the work on the prototypes. I will tell you, I was working at that time. I thought, boy, I sure am glad Ray's doing that engineering stuff, because it's much more fun to work on the 40-meter interferometer and try to make it more sensitive. But Ray actually recognized it and took that on. It's essential to the overall LIGO effort, and I think, in fact, ultimately, when you look at how LIGO was approved with the proposal, that engineering was actually more important than the prototype work that was going on. The blue book, in fact, looks an awful lot like a practice run for the full LIGO proposal, which was prepared 6 years later. That proposal in 1989, I wasn't involved with it. I had nothing to do with the writing of that proposal. So I can look at it from the outside and I can say, it is truly a masterful document. There were 2 volumes there. The first one was the science case, talked about sources, the detector physics, and noise analysis, work that was going on with the prototype. The second volume, the engineering, conceptual design, and the cost basis. When you look at how much things had evolved in 6 years from the blue book to this proposal, it is incredible. Okay? This proposal defined the scope and the sensitivity goals and the phased approach that would be successfully used by LIGO. You can see, again, Ray's influence, every noise source calculated, the parameters that went into those estimates, everything had to be right. Ray's role in the proposal. I mentioned again the proposal team, Robbie Vogt, Ron Drever, Ray Weiss, Fred Robb, Kip Thorne. You might guess that there are some strong personalities there, and it wasn't easy to write a coherent proposal. There are some parts of the proposal that you look at and you say, that's Ray's appendix, that's Kip's appendix, that's Ron's appendix. But overall, the scope when you get to read this proposal, and I encourage people to do it, is that there is a core that is coherent. It's pulled together. Ray recognized that LIGO would need that, and he, I think, more than anyone else, reached out to help build that core of the proposal, the coherence that was there. He worked with Bowd Moore, the vacuum engineer from Caltech. He worked with Larry Jones, the mechanical engineer from Caltech. He worked with Mike Zucker. He worked with his own students, Mike Burka. All of those people, Joe Giaime, all of those inputs went into this proposal in a coherent way. And when you begin to look at it, you see that Ray played an outside role in creating that proposal. His style of collaboration and mentoring led others to adopt a similar approach. And he drew people together in a way that was really crucial for the success of LIGO. He was trying to build and expand the team that would be dedicating their careers to this. And I think that's why there are so many of us here, is he drew us in, he led us to understand how our individual contributions would make this a successful project. He started the creation of what eventually became a vibrant, effective, gravitational wave community. And those are the three things that I think are his most important contributions. His insistence on a rigorous and quantitative understanding of the LIGO detectors. It wasn't good enough, as Joe talked about, to realize, oh, this design for the isolation system doesn't work. You actually had to understand why it didn't work so that you could build the next one better. His leadership in advocating for the synthesis of science and engineering on LIGO was crucial, and it was pioneering. And finally, he gets credit, in my mind, for the creation and mentoring of a community of gravitational wave scientists and engineers. Thank you.
Thank you, Stan. And so the speakers that you've just heard all have known Ray for quite a while through everything that you've just heard. My introduction to Ray came in 1996 when myself and David Tanner, my colleague at the when I was at the University of Florida, got involved in LIGO. We were invited to actually take on a subsystem of LIGO called the input optics, which is essentially everything between the laser and the interferometer. Lots of things in there. I'm going to tell two stories. One is a theme that you've heard before. The other is one that hasn't come up yet. So you've heard a lot about Ray's interactions with people and the way he interacted with people. One of the things I always remember about Ray is whenever I would first see him, he would always come up to me, sometimes put his arm on my shoulder. He'd go, "How you doing?" And he would ask, and some people ask how you doing, and that's just a way of starting a conversation, moving on. But he was usually quite generally interested in how we were doing, and we'd have conversations. And I learned, for example, that he was a piano player, and that he actually, when he came to Caltech, he had a secret place he would go. There was a piano on the Caltech campus that he would play, and I was like, this charming individual. So it turns out that after I became the director of LIGO in 2011, he would ask me that question a lot. All right, how you doing? How you doing? And I was like, oh, that's very nice of him. And so somebody told me, he goes, Dave, he's genuinely worried about you, okay? He this is his thing, and he wants to make sure that it's going okay. So if there's something wrong with you, that's an indicator that there's something wrong. So I found that amusing. My last interaction with Ray, unfortunately, was not an in-person interaction. It started when Ray left me a message in June of last year. So I think you're all aware that last year was a rather complicated and disturbing year for the U.S. scientific enterprise because of some of the budgets that were coming down. Gabriela Gonzalez, in her role, I think, as APS, sent around a message to everybody in the larger LIGO scientific collaboration based in the U.S. to basically write your congressman to try and get them engaged in understanding how important fundamental research is, not just LIGO, but just how, fundamental research in general. And so I took that message and I echoed it out in an email to the LIGO laboratory. So in June or July, I can't remember the exact time, Ray calls me up and leaves a 2-minute message on my answering machine saying, Dave, I've got some letters written. I really want to, get these letters out, to people. He had just moved with his wife Rebecca into the assisted living home that they were living in, and he goes, I've got the letters. They're all ready to go, but I don't know how to go buy stamps. They won't let me out of here. So he goes, can I send you? I'll email you the letters with my signatures on them. and you go buy stamps. And so I called him back, and unfortunately, I couldn't connect with him. So I sent him an email saying, by all means, Ray, please send me the letters. We will ensure you that they are written and sent. And they were quite elegant, and he sent them to the right people. And maybe through his efforts, maybe through the efforts of a lot of others, we're actually in a much better place than we are right now. So that's the interlude. Now I'll come back to the main program. The next speaker is Rana Adhikari. Rana got his PhD at MIT. He was a Ray student. Before he was at MIT, he was a student at the University of Florida working with David Tanner and myself on some aspects of the input optics. And Rana did a huge amount of work in the early days of initial LIGO getting the Livingston detector online. So, and then now he's a professor of physics at Caltech, having a long and distinguished career. So if Rana is around, there he is. Please welcome Rana Adhikari.
Hi, everybody. I know this is not in the stories section, but I don't have anything scientific to say. So I'm just talking about some stuff. Oh, let me go back. People who know me, I don't know what's the personality quirk I have, but I always like to poke the bear. And I always felt it was a successful year if I got Ray mad at me. And I think he sort of felt the same. He would often say, "It was a good day, I lost my temper, and I yelled at you." And so this is me trying to explain to him how interferometry works, just to get a reaction on it. As Dave said, I got started at the University of Florida, and this is a little transcript. And throughout this thing, I've tried to highlight in purple, which is my quotes, and then some of Ray's quotes are in yellow or white. You can read it, but this is about how it went, and it's in quotes, but memory is what it is. So this is my paraphrasing of what I think went on. Anyway, I think this is what went on with the admissions here at MIT around that time. I wondered, everyone else was getting their big envelopes in the mail, and I didn't get one. And then a few weeks later, I got one in the mail. And I think that's because I was waitlisted. And so when I arrived here, there was no more visiting going on. I didn't know what to do. I was just wandering around campus and knocking around. And anyway, I talked to Ray. He said, I'm pretty old. I'm just working on rubber and steel. You really don't want to work with me, but there's these younger guys here, Mike Zucker and Peter Fritschel, and you might get along with them and try it out. But go ahead and tell me what you're working on. And so we headed off to the Aubin Pan in Kendall Square. I got a big roast beef sandwich because I knew he was paying for it. And he was really impressed that it was such a big sandwich, and I downed it. And afterwards, he said, tell me about yourself. What have you done? And I said, I got these grades. He said, I don't care about that. Tell me about what you do outside of school. I said, I was like a little bit of a mechanic. And then he started to warm up and said, oh, this is a pretty exciting thing. And I remember he yelled for David. Said, David, get in here. This guy's done something useful. He's worked on cars. And then the rest of the conversation was about the clutch on his little rabbit that you saw earlier, and basically how much would I charge him, and what was he getting quoted on. So we got along after that. This is not the office that I encountered. I was in NW 17, so I was in between Building 20 and NW 22. But I just want you to imagine the scene of the reform school. So I've arrived from University of Florida, where I was not no matter what Dave says, I was not the best student academically. And then you can imagine the culture shock of landing at MIT. The first day's class was about Feynman path integrals in E&M 101. And I thought, I don't know what's going on. This is not the place for me. And I did accordingly well on the exams. And after the first one, there's this horrific thing where he and I walked together in the rain to the central campus. And we opened up these little blue books, and he looked through my exam and tried to figure out what was going on. And he said, "You're pretty good on quantum and stat mech, but you don't understand mechanics and E&M. Are you in the right business?" It's a good question, I guess. And so then began this reform school thing, which was, now I'm immensely grateful for it. But at the time, you show up at 9 a.m. on a Saturday, and you're standing in front of that board. And he had allegedly stopped smoking by this point, but the smell was on him. And so something was going on. And he would sit back there and say, you know, these typical problems, like do the classical electron, do the particle, and every time I'd do whatever it's not your fault, Dave, but every time I would do something, he'd say, oh, that's very interesting. I wonder why you do that. And it's because he liked to see what was going wrong up here. But that, like, those problems are now burned into my mind. And I think, you know, the shame of that experience going through that, I mean, there's a lot of, you know, blushing and sweating and that sort of thing while you're at the board, but on the positive side, I've never forgotten how to do those problems. And for myself now, you know, when it happens, you know, sometimes my students don't do so well on the Caltech qualifying exams. I give them the same treatment, but I like to think it's much less harsh because I do it in the afternoon and it's not on the weekends. But it's a thing that I pass along, and I think it's good. So I flunked once, I flunked twice. We got to part 2, which was, you know, Joe had told me horrors about being asked about anti-ferromagnetism on the exam, and I knew about it, and so I thought, I'm not gonna flunk that thing. So I went and I asked everybody, what are the questions on the exam, and I collated a list, and I still flunked. But then I passed the second time, and I thought, great. And then we got to this oral exam back then, and I said, I could do atomic physics, or I could do astrophysics. And I don't know if I should say this, I didn't realize this was gonna be recorded. But at the time, he said, you know, the atomic physics faculty here are kind of snakes. And the astro people are softies. So do astrophysics, you'll be fine. And I said, I don't really understand atomic physics or astrophysics, but I'll do it. And there used to be a process for it. So I would sit around and do these problems. And I realized I didn't know anything. So I was studying undergraduate astronomy books to try to pass. And see, I'm in the middle of this thing. And, you know, I'm from the South. And we moved down there, my family moved down there in the early 80s because of the space shuttle program, which, you know, again, like what a coincidence that Kobe was so troubled by the space shuttle, which was my whole reason for being there. And my experience, you know, when the Challenger blew up, I knew I just don't want to get into anything that has anything to do with space. You know, I should stay out of any astrophysics for sure in my life. And anyway, I'm sitting there, and he says, you know, I'm going down to Livingston. There's a problem down there. I'm going to go down there for a while and take over the commissioning from Peter Salson. I said, yeah, okay, thanks. And I kept on studying. He came back. He said, well, you know, have you made plans? I said, you know, I'm thinking, you know, I like your offer, Ray, but he said, I don't know what you're thinking about. You're going. Good, settled, decision settled. And we headed down there, and it was an amazing experience. You know, people asked me, Nelson Christensen, Jeff Livis, they would ask me questions, how often do you get to see Ray? I would say, what do you mean, how often do I get to see him? He's there every morning before I get to the lab. We're there, we go to dinner together, we go to lunch together. It's after midnight, he falls asleep while we're still working. You know, there's no getting out of it. And every night, it's constantly us, you know, working hand in hand, except there would be a break around 9 or 10 o'clock, and he would call up Rebecca. And we'd be sitting in the control room, and he'd be telling her stories like, oh, you know, Rana's working on the coil driver, and what kind of a call is this in the middle of the night? And say, well, we talk to each other every night. And anyway, these are just some quotes I have from him. I felt like the entire talk here, I could just give you a bunch of quotes from him, but that time in Livingston was a rough time. It was a very rough time for me anyway. It was 2001 when I started. And when I first arrived there, I was extremely unwelcome. I had been kind of snuck in there, and they really didn't want anybody coming in from outside. And anyway, it went okay because Ray was there to protect me, sort of 50% of the time. And when he was not, he could sort of detect it over the phone calls when things were getting rough. But at that time, you know, we had the new faculty at LSU. We had Gabby Gonzalez, one of my favorite lab partners of all time, and Joe Giaime was there. And then Peter would give me a call almost every afternoon and talk to me, and Mike. And all of you gave me a lot of help and support during that time, which made it a lot easier to get along. Then September came, and we were in the control room when we heard that the World Trade Center had been hit. And anyway, I didn't know what a World Trade Center was, so I just went back to the lab and went to work. And then all day I'm in the lab working on the mode cleaner and the PSL, and then no one shows up. And I didn't know what was going on. And I could tell then sort of toward the end of the day I came out, people were glued to TVs, and it was just a phase change. And, if you look like me, and you're in the deep South, that next 4 or 5 months was an unfriendly time in town, in Baton Rouge. But that sounds kind of negative, but on the plus side, if there's a plus side to that, it refocused me to work in the lab. And so, take away what you will. Anyway, we had a great time, except for some of these other encounters. There's that one, Rana, get your fat ass in here to help me with the coil driver. Joe came up to me and said, I don't know what's going on. Ray's always been kind to us. I'm sorry if that's changed. I said, no, that's just his way of saying, come on, let's go play. It's not a mean thing to say. And so I have to say, a lot of the work we did was, as you've heard, sitting in the electronics shop. And this is at MIT, but his electronics shop in Louisiana was similar. And I don't know if this is in bad taste, but he told me this is his favorite oscilloscope in the world, and he wants to be buried with it. And so I thought, I'm the only one maybe that he told that to, so I would show you here the particular model that he liked. So anyway, that was my sort of the tail end of grad school, but we had this intense few years of just working hand in hand. And I think, I didn't have much of anything going into it, but I just learned by imitation. And, my way of learning was to just sort of do whatever he was doing. And as you've heard, he learned how to, I don't know if he learned or if he was born that way, but the way that he would address everybody at the site, independent of, what their position was amazing. And his dedication that he would be there all the time. And I was worried, he was ancient at the time. He was over 65, if you can imagine. And I thought, what's going on? And then he retired. He became emeritus right when I started. I said, what's going to happen to me? He said, nothing's going to happen to you. It just means I don't have to go to these fucking committee meetings anymore. We're working in the lab all the time. Get back to work. And so we did. And it felt, it was a tough challenge at the time, but I wouldn't give it up for anything. I remember Mark Cole said to me, he said, I think your boss doesn't understand that not all of us are 100% dedicated to science 24/7. And I nodded along with him, and I said, I don't understand either that you're not all dedicated to science 24/7. I'm with him. I don't understand what you guys are talking about. Anyway, here's some more quotes from him. At some point in the last several years, I started to record him, because I realized, I'm not that young anymore either. And so he would tell us these stories, and I remembered it throughout my 20s and 30s, but, after, my memory is no longer as good as it used to be. So I started recording some of these things, and two of my favorites I have, if you want. There's a story of frequency counting and how Einstein wanted to find out about flip-flops in electronic circuits, which I have a recording of. And I think the more interesting one is this one about Dickey and the solar ablateness measurement, because you've all heard about this QPR and this masterful noise analysis of LIGO. And so in the interview, I asked him, how did you do that? That's a thing. Nobody does that. Everybody does the other thing, which is you go in the lab and you mess around, and then what happens, and then you try something else, and what else are you gonna do? And he said, yeah, I sort of got it from Dickey. But then anyway, if you listen to the recording, there's a lot of language I won't repeat here, but I tried to say something like, because of, your thing is sort of like Dickey's, and he just wouldn't have anything of it. He thought the way that Dickey designed the solar ablateness experiment was the most genius experimental design he's ever seen. And so I encourage you to find out more about it if you can. And then he gave me some advice in these next 20 years. He said, when you're doing science, you gotta make it sexy. It can't be dull, whatever it is, because people are not gonna care. He said, no matter what you do, you can invest your money and your time however you want, but the best investment is to put it into students, because that's always gonna pay off the best in the long run. And then he said this during the Ray Fest that we had at the end, for those of you who were there. He turned around to us after the musical performance and said, you should make sure to do something important. And then as he does, he would say, now it's up to you what you think is important, but you should really do something that you feel is important. And I think what he was saying to us is, it's fine to be physicists and do our science, but there's bigger things in society that we could focus our energies on. And so we have to think about how to balance that and not completely be dead focused on what we're doing. Although I agree with him that we should also be dead focused on everything that we're doing. But I think he was saying you got to think about where really to put your efforts these days in today's society. And also he thought I should have kids, and I said, I don't know, whatever. I'm not interested in kids. But then in 2022, I said, Ray, there's this girl I'm serious about, but there's a pandemic going on. I don't know how to get into Australia. She's in Australia. And he said, well, you're a fancy scientist. Maybe the Australians will want you. It was a good idea. So I called them up, and they made an exception and allowed me to get into Australia. And so I spent most of 2022 there on my sabbatical, as it were. By the end of the year, she was convinced and moved to the US in 2023. And I said to Ray, here we are in the US, we'd like to come to Boston, I'd like to introduce you. And he said, how about this? Why don't you come to Maine with me? And for years, those of you who've been in his group, you know, he would go off to Maine every year. And I'd always wonder, why are you going off to Maine? We've got science to do. What could you possibly be doing in Maine that's more important than this laser thing? And then eventually I learned. So we headed out there to Mount Desert Island in Maine. Here we are at Thurston's Lobster Pound, having Rebecca and Ray are having lobster rolls. And Ray was really impressed that I took down a whole lobster, but I had to wear a bib. We returned in 2024, and Peter and Sarah Salson joined us, and Ben and Carla were also there. And I got the chance to finally cook ribs for him that I've been wanting to do all my life. I used to be a barbecue cook. And I cooked it in the Louisiana style, and I also cooked fish for him, and he liked it, because he said I didn't put a lot of salt into it. So I just want to close and say, the thing that you know about him if you work with him is he loves telling stories. And a lot of the things that I would like to do, I used to try to key him up, because I knew the stories, but it would be, like if Mick Jagger comes to town, you say, play the old tunes, I want to hear Give Me Shelter or something like that. I don't want to hear the new stuff. And so I'd try to key him up and tell these stories. And I think that's the way we can preserve it, preserve his essence among us, is to just retell the stories about him and spread it out. Because I've been all over the world and I've been working in science for a long time, but I don't think I've ever met anyone who I would compare to him in any way. And I think that's such a special thing that we should keep it alive. Thank you.
Thank you, Rana. I think we'll edit out the no committee meetings part of that last. We can get rid of that. Okay, so our last speaker is Matt Evans, who's going to be looking, I think, a little bit forward. But again, this is all inspired by Ray. So Matt was got his PhD from Caltech, working with Barry Barish. He went to Virgo, I guess, and spent some time there as a postdoc. Then came to MIT, where he's now a professor of, I think he's the MathWorks professor of physics here, MIT anyway. And Matt's gonna close this wonderful session. So Matt, please come down and take it away.
Wow, those are some impossible acts to follow, with some really amazing storytellers up here in front of you, who have already told almost everything I have in these slides. So I'm gonna just leave it here for a second and tell you a couple of stories. The first was a number of people, Rana, you said that he would always address people so kindly at the observatory. I remember my first encounter with Ray at the Livingston Observatory, where it was time for dinner and everyone was heading out. But I was like, I'll stay here. And he was like, we need people to run the interferometer, keep things going. And I was like, don't worry, Albie. He's your theorist. Oh, okay, I understand. So this is Ray throwing down the gauntlet for me in that moment by calling me a theorist. And I guess over time his appreciation for theorists grew. But I didn't take it as a compliment, so I figured I had some real work to do to prove myself to Ray. And somewhat later in life, we would have, when I started here at MIT, we would have regular arguments about whatever was the most recent problem in LIGO. And one of the ones that stuck was we were arguing about the thermal noise in resistors for the coil drivers. And he had any number of clever ideas, let's say, for how to get rid of this thermal noise. And in after many discussions, I made him a bet. I was like, Ray, I'll bet you $10 that none of this stuff is ever going to work, right? And I didn't hear anything about it then for a few months. And at some point, I show up in my office, and there's a little plaque hanging on my door handle. Right? It's not a plaque, it's a framed $10 bill, right? With the notes from our discussion and the comments saying, Matt slayed this dragon, or something like that, right, at the bottom. But, a lesser person would have just let that slide, right? After he realized, I'd completely forgotten about the whole encounter, right? He could have just been like, oh yeah, I did the math, it didn't work, and no. I mean, framed $10 bill on my doorframe was obviously worth a lot more to me than as a young researcher having this from such a senior person, such a famous person. Of course, I still have this little framed $10 bill there because it was a huge deal for me, and it shows the humanity with which he approached everybody except maybe the theorists. So. So I'm going to talk to you about Cosmic Explorer, which is about the future, and yet I will talk to you a bit about the past. So let me see if I can figure out this device. This is like a test that everybody has put to you, right? I can read, strangely enough, the buttons, so I think I've got it. So this idea for the future of gravitational wave detection in the US, Cosmic Explorer, which was shown on the previous slide, really started almost as if it were some sort of a joke, right? 4 physicists walk into a bar, it's late at night, we're all tired, we're at a conference in Italy on this island, and we were quite certain that none of the stuff we had heard that day was ever going to work. And the only way that we were going to actually make a big leap forward in gravitational wave detection was to just build a bigger observatory, right? We needed to think about, what do we do post-LIGO? And so this is 2013. Of course, we were feeling very cheeky. We were several drinks in, so this thing was called Lungo. There's a backgronym, we had to figure out what it meant. Lungo just means long in Italian, right? So we're in Italy, it's going to be a long detector. You just need to make it longer was the theme of our conversation. Long, uncomplicated, next generation gravitational wave observatory, Lungo. And really the point here was that gravitational wave signal scales with the length of your observatory, and none of the cleverness that we had been talking about for the last decade was likely to pan out. We just needed to make it longer. So in a nutshell, what is this future gravitational wave detector? It's a 40-kilometer long scaled up LIGO. You've heard about this a few times now in terms of the challenges associated with building such a thing. We spent some time thinking about the science case. I don't really want to go over this, but there were a lot of really cool things that we could get out of this, and Ray got pretty excited about it. So this was our first CE gathering. Ray was there along with Nergis and a bunch of others. Mike is here. And this really exciting science case caused Ray to just dive in on Cosmic Explorer. At the time, it didn't have a name. It was just the bigger LIGO or something. So he went back to this question, which drove a lot of the consternation in LIGO, which is the vacuum system, and said, all right, do we really need a vacuum system? As Mike pointed out, there are lots of good reasons why you need a vacuum system. But he went right back to first principles and said, I'm going to consider having multiple beams. They're going to be different wavelengths. I'll use them to cancel out the phase noise. And lengthy conversations about all of the ways in which we might be able to make a giant gravitational wave detector using N different lasers all running simultaneously from various mountaintops to avoid the expense of a vacuum system. Eventually, he wrote all of this up. The introduction starts with this collection of jokers. These are the 4, well, he left out Stefan Ballmer, but these are the 4 physicists who walked into a bar, part of the story. And the exciting part of the science case, and then this very frank, this is going to cost way too much money. What else can we do? And again, off-writing code in Fortran to try to figure out if such a thing was possible. Eventually, he came to the conclusion that it was not. And so he, then dove into the next biggest challenge. Okay, so how do we actually build that? And this is now the largest component of funded work in Cosmic Explorer is how do we build the vacuum system, right? Mike didn't take any of the credit for for this. He's done a tremendous amount of work along with Ray on this. It's turned into this thing called CBEX. It will be the first building dedicated to Cosmic Explorer research. So, Ray was first trying to find a way around it, and then just full bore into how do we get through this challenge of making 80 kilometers worth of ultra-high vacuum system, right? So there was nothing that he found sufficiently daunting to change course, which I think was a feature of Ray throughout. We spent a lot of time at the Pacific. I think some people know exactly what was in there, and this is the usual cup of coffee. And yeah, so these conversations where we would talk about anything and everything that might get in the way, from the smallest detail of the coatings you would put on the baffles that you're going to put in that tube, or what kind of optics you're going to make and how you do the metrology on them, to politics at the international, sort of global level of how do we get this thing moving, how do we get CERN involved, how do we work with our collaborators in Europe. Anything and everything was on the table, and he would engage with those things productively at, in whatever was the next barrier to progress. This would, in the last few years, end up with Ray. He would do sort of a round around the offices where he would come in, and he would come in and go into my office and sit on the couch and say, so, how's it going? How are you doing? As people have said, it usually starts this way. And then we would dive into one of these topics. And the thing that was striking here was that he was, in ways unaware to, that I was unaware of at the time, but engaging with folks you've heard from Vicky, Kalogera, and others, that behind the scenes, he's, pulling the strings and sending email and trying to keep all of the processes moving, while I'm trying to figure out what the technical design of this thing would be. Maybe the thing that struck me about all of this was that many people have spoken to his humanity and the price he put on relationships. I also want to sort of speak to the selflessness with which he did all of this, which is relatively rare in academia. You'll find that people want to hold on to their ideas, and they want credit for the good things they've thought of. And I won't exclude myself from feeling like, gee, I should have been an author on that, or why didn't they put me in the acknowledgements, right? I have that feeling occasionally. And if you ask me, like, do you think Ray ever felt that way? I could categorically say, no, he never worried about that. It was never his concern. If anything, he would say, don't put me in office. I don't want to be associated with that idea. Right? I've had 1,000 ideas better than that one. Please publish whatever you want, right? And this was like an intrinsic assumption underneath all of the conversations, that he had no need for credit for any of those things. It's not even something that I would think about during the conversations, because he just obviously was not interested in furthering his own self in any way in these conversations. And that kind of selflessness, I think, is relatively rare. So while people have spoken to the community that Ray generated, which I really think is the biggest part of the legacy, is this amazing community, and I'm so glad to see so many friends here. This is really wonderful. But that ethos of that community, I think, has really been Ray's greatest gift here, and I hope everybody appreciates it. I think this was an important part of it, was wanting to do science for the sake of getting things done, and being generous with everyone, with his time and his thoughts and his goodwill. So, thank you.
All right. Well, I hope everybody truly enjoyed those presentations. I know I did. And I think I'm going to turn it back to Lisa. We're a little bit behind schedule. I don't know what you want to do.
No, that's perfect. Thank you all so much. I cried 5 times during this, so it was great. Yes, so we are late, but that's okay. It's today's symposium after all. I didn't think would be on schedule. But there is coffee break now, and maybe we do it slightly shorter, so if you can.
Hi, everybody. Welcome back to our next session. So I'd love for everybody to get seated so we could start. Welcome to this session. This is a session that we labeled Ray Stories. And the reason why we labeled them Ray Stories is it was supposed to be something of a kind of an open mic. You know, people just sent us a small blurb on what they would like to say and how much time, and so we have a long lineup. The way it's going to work is I'm not going to do introductions. Every speaker will just say who they are and share their reminiscences of Ray. Before we launch into the session, there is one thing I want to do since I have the mic, and that is I really want to give a big shout out to Lisa Barsotti and Peter Fritschel for organizing today. And then 3 people working very hard behind the scenes were Reshma Rumiel-Rice, Amalia Teglis, and Juliana Di Virgilio. So thank you to them as well. And now, without further ado, we have our first speaker, Rich Isaacson. And Rich, take us away. Thank you.
Thank you. For those of you who don't know me, I was the founding program director of the gravitational physics program at NSF. So I'd like to just give you a short story of an incident that happened after my retirement, which was in 2001. So, some years later, on September 18th of 2015, I visited Bass Harbor in Maine for a prearranged visit with Ray and Rebecca, who were vacationing there with their son Ben and his wife Carla at their summer cottage. So after arriving at my inn, I headed over to their place and joined Peter and Sarah Salson, who were also visiting. Ray and Peter were in the middle of some discussion. I think it involved kayaks or something, but that was interrupted. And they turned toward me, and Ray said to Peter, "You tell him." And as Peter got his laptop, Ray leaned back in his chair and continued, "I want to see his puss while you two talk." So Peter opened a file on his laptop and pushed it over for me to view. And on the screen, there was a very familiar image of a damped oscillation with a little bit of noise mixed in. Kip Thorne had been drawing such things on napkins since the 1970s, and anybody who was interested would find out what it was, the expected intensity of gravitational waves arriving at a detector on the Earth when a black hole was oscillating. So I looked at this laptop and saw this picture and asked Peter one question: is this an injection? Peter said he thought not, but rather he said it was the actual output from a detector. So Ray had then explained that they had requested permission from the LIGO management director to let me in on this historic development just a few days after it happened. But it had to be a secret for some time while they were checking out everything. So this was wonderful for me, a theorist familiar with the mathematical calculations of gravitational radiation and black holes, to actually see a confirmation of this extraordinary tests of the dynamics of gravity under the most extreme conditions in the universe. And I was, of course, conscious that this had required 4 decades of work with, over 1,000 talented scientists from all over the world. But since this observed waveform was exactly the result expected, it seemed inevitable, and therefore it was a completely unsurprising result. And what else could it be? And why did it take so long? However, I was the only civil servant in DC whose job description authorized me to request that the government throw $1 billion at a black hole for 40 years in search of solving cosmic mysteries. So what I felt was not surprise, but mostly relief to learn that this effort had finally produced the results that I had long been promising. So Ray, however, seemed a little bit disappointed at my restraint on learning of this triumph. However, there was an actual enthusiastic celebration that took place that evening, and that's on this slide, next slide. So there was actual dinner with wine and toasts, and there were a cast of characters going around the room clockwise from the right, Ray, Carla, Rebecca, Ben, and Peter, and Sarah, and then myself. So that's a picture that hasn't been shown yet today. Thanks.
Hi, I'm Fred Robb, and I joined LIGO in July of '98. And about after a few days of July 4th weekend, I met Ray for the first time. And we had a big assignment to write a proposal, which people have talked about a bit. When I heard the news that Ray had passed, there were a lot of memories flooding forward, but one of my favorites was this one. What I'm showing you is an actual slide that I use when I talk to college students about careers and whatnot. But what it shows is this tremendous love that Ray had for people who just got their hands dirty and built things. He was himself a craftsman, and he as Mike Zucker said earlier, he both learned and gave learning to fellow craftsmen. So the problem we had here is I had been involved early on in some of the beam tube work. So Mike talked about the tubes that came from Larson after testing out some stuff on the feasibility of doing a beam tube bakeout. Those later became 40-meter tubes. He showed those. I didn't have any photos from the period of time of the actual testing of those tubes. But what I can tell you is it was really hard to follow all the procedures. And the question was, how were you going to do this on a factory-like scale and get the amount of care when it's not being done by professional engineers and physicists, but it's being done by guys who know how to do excellent welding. And how do you motivate these sort of crazy specs we have that we need to have 30 kilometers at each site of welded seam with no leaks, that by the time they deliver it from the factory, it's got to be free of any kind of molecular or chemical contamination or dust. And so the solution was you basically talk to people. And Ray gave this wonderful talk to the craftsmen working on the beam tube. So this is Big Pasco factory. That those big wood beams in the ceiling are part of Russian timber that came back to the US as ballast during the Lend-Lease program and during World War II. And what Ray did for the craftsmen is he connected the welding that they did and the other metal bending and tasks that they were doing, both to the past in terms of Einstein and his edifice of general relativity, but even more importantly, he connected this to the fact that those people had children or grandchildren that would someday learn about their work, what their work produced in their schools. And it was just a wonderful time to watch this. We actually paid for these guys. They were on the job listening to it. And Ray just did a superb job. And I can tell you that they loved it. So that's my memory.
I'm Satya. I'm going to share a couple of things of my experience working with Ray Weiss. I met Ray in 1996, December, at a workshop right here at MIT. It is, that series went on for nearly 20 years. It was called Gravitational Wave Data Analysis Workshop. I was working on those days on theoretical development of waveforms to detect these binary black holes. And at the end of the first initial LIGO, at the end of the observing runs, LIGO lab began to think about whether to shift one of the LIGO Hanford instruments to Australia. And the person who was given the responsibility to write a report, what is the advantage of doing it, whether to do it at all, was Ray Weiss. And he put together a committee, and he conducted the meetings on a weekly basis, but he wouldn't be satisfied with the graphs and arguments that we were bringing until he was really, truly satisfied. The final thing that really helped us to convince him was these figures that you see here. How, if we had the 4 detectors, LIGO Hanford, 2 of them, Livingston and Virgo, these are the ellipses of the uncertainty regions on the sky. But if you move one of them to Australia, the 2-kilometer one, how that would improve the sky localization. This was the selling point for Ray. Unless he was convinced, he was not going to be, write a report. And you can see a similar thing here at the bottom, how, the scales of the figures are very different here. This goes all the way up to pi radians, whereas here it's a very small region of the sky. So this is what really convinced him. And it was a tremendous time working with him because in addition to the committee meetings, he really wrote a lot of emails to me asking very detailed questions about how did you calculate this, and my own back of the envelope doesn't seem to agree with it, and so on and so forth. This was a very difficult thing to convince him how just moving it to Australia will help. And so finally, we did do the job. But I want to spend a little bit of time talking about an inspirational talk that Ray gave, and this is what I call it, Before the Dawn, Ray Weiss's vision on the eve of the discovery. If you want, you can scan that QR code. That will take you to a lecture that he gave in March 2013 at a meeting in LSE, LIGO Scientific and Virgo collaboration meeting in Maryland, I think. And he came at the end of a plenary lecture, and he gave an inspirational talk. I'm not a person who normally records anything at all, but I somehow felt that this was an important thing coming. I'm not going to read through the slide, but except to tell you the main message that he was trying to convey. And he conveyed to us that, look, scientific progress is nonlinear. Even Einstein's discovery itself involved confusion, correction, and interpretation. So don't be worried about making mistakes. On the other hand, just imagine the controversy that this field has generated, both theoretically and also observationally. And so the quest for gravitational waves is as much a story of perseverance as of theory and experiment. So you need to survive through all of these. But his main message was we should make this discovery, if possible, before the turn of the 100th years of gravitational, general relativity. And he gave all the arguments, but this was funny. We don't tell the NSF a word about this, but we keep it to ourselves, have a go. And I was really laughing because Pedro Marinetti was there in the audience. I don't know what he thought about it. And that was a massive inspiration. There was a message, ambitious internal goals can catalyze coordinated progress without external pressure. He didn't want to make a big deal out of it. And he also motivated us by telling us, we have everything, but don't wait to fix things serially, but make parallel improvements. And this was the main message that he gave. And he visited us in Penn State the year after he got the Nobel Prize, and here he is talking about inspirational talk, another inspirational talk to our faculty, students, and so on. But he went to the Swift laboratory. I had taken him just to see the place from where the gamma ray bursts were observed after 1708-17. But instead of spending 20 minutes, he spent 2 hours there. That was what his interest was. He didn't really care about all the show that was going on. His interest was still in the lab. I want to just conclude by saying that we not only were able to accomplish just the discovery, but we have appeared in the title page 4 times so far. But wouldn't it be really wonderful if we can build this to honor Ray? Thank you.
Well, thanks, Nergis, for putting me on the program. I have to figure out a button here. The green button. Okay. I'm David Tanner at the University of Florida. I'll start with a little bit of how I first met Ray and got involved with LIGO. Gano Mitzelmacher came to Gainesville. He had been at Caltech and knew Barry Barish and the others, Gary. And he decided as a high energy experimentalist that he wanted to start also a LIGO group. So he sent an email around. And I came, and Dave Reitze came, and a number of other people. And we said, yes, we should do that. So the outcome of that was that in winter, we went to the Aspen meeting. Dave and I did. And Ray was there. We wanted to learn. And Ray was there chairing a session and giving a talk. I remember having dinner with David, or lunch with David Shoemaker at this time. And then a few weeks later, we went out to Caltech to look at the lab. And we thought we would get involved in some way, maybe evaluate lasers and think about configurations and so forth. But the outcome of that 2 or 3 day meeting there was that there was a chance that we might be able to build the input optics of LIGO. Dave would have been and was the PI on the contract to build them, and I was a co-I, and we built them. Okay, so before this came to pass, of course, Ray and Stan, and I think Mike Zucker also came down to Gainesville for a couple-day visit. It was a reconnaissance in force, in some sense, that they wanted to see what we were doing, how interested we were, did we have what capabilities. We showed them our wonderful machine shop and cryo shop and other things. And then we both spent a little time at Caltech, and by fall we had a contract and an ability to start making the I/O. What I learned in those visits and as I met him was he's a technical genius. There is no experiment that he could not take on and make it work. There are not many people. I have a former student at Brookhaven who's a similar technical genius. Anything, vacuum, electronics, cryogenics. And that's one of the reasons he was so successful, obviously. I already knew about Kobe because my former life, I was an infrared spectroscopist working in the far infrared. I know what the 5 wave numbers means on that graph there. It means 150 gigahertz. And that is the single most beautiful infrared spectrum I have ever seen. The error bars there are multiplied by 400 from the actual error bars so you can see it. The line goes through every point. I mean, I've never done anything that good, that's for sure. He had amazing vision for the future, too. He saw, our colleague Gano Mitzelmacher was similar. He saw the forest, not the trees. And that was a real thing as well. So about 8 years later, one of my birthdays that ends in a 0, we had a little conference in Gainesville where my friends came down to give talks, and Ray came to give a talk about the status of our search for gravitational waves in 2005, and he spent time talking about the initial LIGO detector, sensitivity, all the things that you've seen. It was a really nice talk. Near the end, he said what the role of the University of Florida was. And I can see right here, he knew what was going to happen in the future, I think. So he said we designed, built, and installed the input optics. They were more or less in place and working pretty well by then. Input mode matching telescope, mode cleaner, Faraday isolator, modulators, all that stuff. Development of data analysis techniques, so he knew about that too, and that there was a wavelet burst analysis that Sergei Klemenko was starting. This turned in, of course, to coherent wave burst, and on the 14th of September 2015, it was coherent wave burst alone of all the online data analysis programs that triggered on that detection. And my feeling is that had it not triggered, we'd never have looked at that data. It was an engineering run. So line removal techniques was based on wavelet analysis as well. And then finally, high power optics for advanced LIGO. Guido Mueller was in Gainesville by then, and he took over the input optics when we lost Dave to the lab, and built the input optics for advanced LIGO. So, and then finally, you notice he put this in red. This is the most important thing we ever did, according to him, was to find and nurture Rana, and I agree with that. But it also tells you that his interest was in people, not so much the science. And you know, I saw that when he put together with Stan's help the rules for being an author and also the publication policy that all our papers got circulated, everybody had a chance to comment. That was Ray looking out for the young people who might feel left out in one way or another. And there are hundreds of people that Ray, whose career Ray's nurturing and mentoring meant big things. And I'm glad to say that one of those people is me.
Okay, you can read my talk here. Let me say, I have been at Princeton 2 times, one from 61 to 63, and then from 66 to January 1969 when I arrived to MIT. I am referring to my second stay at Princeton. I am delighted that Kip Thorne is here, and he will certainly be able to make comments and confirm what I say. At that time, in 68, it was the end of my stay at Princeton because Rossi had invited me to come to MIT. At MIT, they were not afraid to do experiments in X-ray astronomy and space physics. Unlike Princeton, Spitzer was quite negative on those things, let me say. And this is how I came. So I was at the Institute for Advanced Studies. And those of you that are about my age or not much younger, remember that there was the physicists that we given a small building with 2 rooms. The physicists were there except Dyson, that was among the mathematicians. On the 2nd floor, we had very few offices, and my office was between that of Rosenbluth, very famous nuclear physicist. He invented the various numerical methods, and so we called it the Pope of plasma physics. And at the other end of the corridor, there was Tullio Regge. Regge at that time had developed an interest in general relativity. And therefore, because of the connection between Regge and Johnny Wheeler, we would welcome his visit. They were rather frequent. And of course, at that time, I got to know Kip Thorne. I was a kind of postdoc, and Kip was a graduate student. You remember Kip? So he can testify this. So very soon, Johnny Wheeler, because he had been in touch with plasma physics in some role that he had before, he thought it was important. And he thought I was a great expert. It was not true. But in any way, so he got me involved in understanding what later were called the black holes. They were not black holes at that time. And the issues connected with them. And one of them, which is still been underestimated, is that black holes do not exist in vacuum. There is matter, like plasmas. So there is all sorts of plasma physics involved with the physics of black holes. But now with the discovery of the binary system, there is even more plasma physics. So, well, then I came to MIT. Johnny Wheeler was very displeased. He came with me on the airplane, could try to convince me to come back. So here, when I came, nobody was into general relativity. Well, the applied mathematician. But then I encountered Ray. He was very interested in gravitational wave. He had been at Princeton before me. So we connected immediately and became friends. And that friendship lasted, well, until he died. And I have a letter that I exchanged last year to confirm that. So he began to invite me to all the gravitational wave meetings he would organize. And I reminded Kip that there was a famous French mathematician, Meyer, who swore that it will never be possible to reveal gravitational wave because the signal-to-noise ratio would be not adequate. Now, I have many, many anecdotes, but there is no time to speak about them. So let me speak only of one. In early 1969, I proposed an experimental program called Alcator, in Latin it means Psi-field torus, whose main objective, counting on the understanding of Ray, was that of producing and investigating the high-density plasmas that were associated with the few X-ray stars. At that time, there were 7 observed at that time. And we knew later they were involving a black hole. Yeah. So the Alcator program turned out to be quite successful. The desired densities, about 10 to the 15, that is those around black holes, particle per cubic centimeter with keV temperature were achieved. And new plasma physics processes were discovered. However, the program became of importance for nuclear fusion research. The astrophysicists did not care anymore about that, and it opened what has become now the most promising line of experiment for the field around the world. There was a small-scale experiment, quite revolutionary, and now the leaders are the combined collaboration of the Russian and the French. Thank you.
Okay, for those who don't know me, I'm Steve Penn. I'm in LIGO. I do mostly mirror coatings research, but I also chair the Collaboration Council. And I don't have slides, so I'm sorry, but I'm going to read this. And I hope my words provide a little bit of both gravity and levity. I was an undergraduate physics major here, and I had a friend and study partner, Michelle Eisgruber, who's now Stevens, seeing her first time since we were undergrads or grads in the back of the room. And she took up a research project with Ray. I, at the time, was doing research in nuclear physics. And I remember Michelle describing her research in which she was focused on what seemed like ridiculously small levels of noise. It was hard for me to believe. Now, Ray had been our junior lab professor, and one day I ran into him in the pass-through beneath Building 26, and I asked him about his research. And I got that 15-minute LIGO in a nutshell talk. I'm sure you all know the one and have heard it many times, but at the time, as a young student, I remember feeling completely spellbound. As he spoke, I was filled with 2 competing perceptions. Oh my God, this will never work. And wow, this is so much more interesting than my own research. But I stayed at MIT for graduate school in nuclear physics. My office was in Building 26, which is next door to Building 20, and I built my thesis particle detectors in Building 20. So I would run into Ray periodically, and we would stop and chat for a while about physics and politics. You see, as a graduate student, I did a lot of activism. And our conversations were always physics first, but then we would talk about the latest political campaigns. And he was always encouraging me and my colleagues to always fight the good fight. It's truly heartwarming to a student activist to have a professor who is so completely comfortable talking politics that he can easily slip into a long and impassioned string of expletives to condemn this or that goddamn fascist. He was never reserved. He let you know how he felt, and he did not mind if you disagreed or argued with him. Indeed, he enjoyed the debate. He cared about global issues, but also campus politics. As you may know, or might imagine, Ray's history with the MIT administration could at times be rocky. I remember when we did an investigation, a story that was later picked up and published in the Globe that kept John Deutsch, the provost and later CIA director, from becoming MIT's president, and Ray reacted with particular gusto. Ha! You got that son of a bitch. As the years passed, our conversations always seemed to come back to that smooth flow and debate between physics and politics. When I eventually joined the LSC, it seemed to me that Ray's political principles had been infused into the collaboration. The LSC had a very welcoming nature and a democratic structure governed by a council of its member groups. I remember Ray arguing for egalitarian policies, like our authorship policy, in which the entire collaboration in alphabetical order would be listed on all of our observation papers, even knowing that his name would be near the end. The message was that in LIGO, we are all in this together. I spent my first sabbatical at MIT working on reducing suspension thermal noise for enhanced LIGO. I have to admit, I always hated that name, enhanced LIGO. Late one night, I was working in the machine shop when Ray came in. I think we were the last two people left in the building. So he sat down and we talked for a very long while. As always, a mix of physics and politics, and in this case, a mutual love of machining. He told me how one year there had been a huge blizzard in Boston. Sound familiar? And he was stranded in the lab for 3 days. He looked off. He seemed quite lost in that memory. Finally, I said, "Wow, that must have been hard." "What?" he said abruptly. "No, it was great. I had so much time to work on whatever I wanted in the shop, in the lab. No, I had a great time." We did track down the excess suspension noise to the wire standoffs, but Ray and I had very different ideas for how to fix it. We presented both our ideas in a sort of dueling presentations at an LSC meeting at Caltech. His design required a switch from silica to sapphire standoffs for the suspension wires. And I wanted music wire ribbons that cradled the optic underneath, but then did a quarter turn to be more compliant in the suspension. My design needed 2 sapphire standoffs to capture the twist, and Ray thought my design was too complicated. It's just possible that he was right. But unfortunately, neither design was ever implemented. Nevertheless, I enjoyed our arguments about the design, and to prove a point, I kept a model of my ribbon design suspended in my lab to see how long it would last. And I thought about Ray a lot and our debates this past December when I finally took down that suspension in order to move my lab to Syracuse. In later years, as my research focused more on coding thermal noise, I tended to see Ray only at our semi-annual meetings. He did not work directly in codings, but when we talked, he was always up to speed on what we were working on. One year, the LVK held a meeting somewhere in the middle of Wisconsin at a former Playboy club Needless to say, it was very weird. For example, if you exited from the wrong door, you were locked out and had to go around to the main entrance to get back in. One afternoon, I got locked out, and while pondering my predicament, Ray walked by. He had also gotten locked out, and I offered to run around and open the door from the inside, but he demurred. "Let's go for a walk," he said. So we strolled around the grounds and talked, and eventually we made our way back to the main auditorium in time for supper. As we entered, there was a group of folks all wanting to take Ray's picture. Of course. This meeting was the first one after Ray had won the Nobel. He was famous now. Realizing the dynamic, I quietly stepped aside, but Ray would have none of it. He pulled me back into the picture. "Come on," he said, "we're all in this together." We're all in this together. To me, that's the greatest legacy that Ray passed down to us. He helped us believe in amazing things we could achieve if we worked together. And now, having made that detection that everyone thought was nearly impossible, our accomplishment has inspired us to visualize and build the next amazing thing together.
Yeah, I'm Valera Frolov. I'm a scientist at LIGO Livingston Observatory since 2002, and I've been LIGO Livingston commissioning lead since 2008. And so it's getting late in the day. I guess somehow my story is superposition of Matt's and Steven's stories. But anyway, its story was involves prisms. So it was around 2010 when we did an upgrade of initial LIGO to advanced, initial LIGO to enhanced LIGO, right between initial and advanced LIGO. It was modest upgrade. We were supposed to get factor of 2 in a range. We didn't quite get it, but came close. And Ray worked on a couple of things. So one of them was prisms, and another one was magnet noise. And at that time, we had excess noise around 100 hertz, which was looked like thermal noise, but it was very stationary. And that's why Ray pursued the suspension noise. And I think he got it right. So although, as Steven said, we never implemented it. And that's where our story sort of begins, because at the same time, Virgo was implementing analytic low-loss suspensions, which kind of we're using in advanced LIGO now, and Virgo is using now. And so after the decision was made, not by me, that we are not implementing the prism, so Ray was visiting the site, came to me and said, "I bet you that $1 that Virgo, when they install the suspensions, they're going to be better at 100 hertz by a factor of 2. I said, okay, well, I mean, maybe Ray can bet against LIGO, but I work for LIGO, so I guess I cannot. So I had to take the bet. So I took the bet, and Ray lost the bet. So, and he framed the dollar, and that's a kind of superposition. And they wrote a concession note. Bet lost to Valera. Virgo to be 2x better than LIGO at 100 hertz in August 2010. Did not want to lose this bet, Rainier Weiss. Yeah, so why did he lose the bet? So we didn't improve our suspensions, and Virgo suspensions was excellent. The problem was that Virgo polishing was bad. So they never reached their design sensitivity. So in a sense, no one won, but I think Ray won the science. Anyway, thank you. That's all I have.
All right, I'm Stefan Ballmer. I joined the LIGO group in 2001, just when Rana headed off to Livingston, getting these machines to work. And the first time I met Ray is actually almost exactly 25 years ago. That was when I was still a prospective student down in Livingston. And I walked into his cubicle because he was curious whether, he wants to take a chance on this young theorist that just got his completely theoretical thesis under his belt. And I guess I used the magic words. I said I wanted to get my hands dirty, and I guess the rest is history. There's so many stories I could tell, but I want to sort of focus on a few that not many might know. So jumping way ahead into 2011, I just started as young assistant professor in Syracuse. Ray calls me up and says I should show up at Cryomech, a little cryogenic company in town, because he's going to be there for a day. Turns out there was just a period where we were considering cryogenic detectors, and Ray just could not find any reliable data on the displacement or the force spectrum of these pulse tube coolers. So what he did is he called up the chief engineer there, called me up. We spent the full day there suspending one of their cryogenic pulse tube heads with Ray's seismometer and a little HP spectrum analyzer that he logged along, and just took the actual data that we needed to see where we can use these in future detectors. That just speaks to how Ray approached the problem when he needed information from people. Again, jumping many years ahead, all this day, this was lunch right after the big announcement. I just happened to be in line behind Ray on the lunch menu, and I can't use the word he used there, but he basically said he was full of this PR stuff. He wanted to switch back and wanted to really get back into how the apparatus was doing, because he had lost track of what was going on because of all the PR stuff. Just speaks to how Ray saw all this stuff. And then finally, the last story I want to share, which was an event that we held in the Explorers Club in New York City. And I don't think it was mentioned a lot today. Ray grew up in New York City, starting year 7 when he was 7 years old. And much of his skills he gained fixing electronics for the rich Upper East Siders in the city, all the analog radios of the time. And apparently he came across stories back then that in that Explorers Club, where only the rich people go, there would be stuffed animals in the ceiling. And he was never there, could never go there, but we happened to hold our event there. Now, of course, that was all valved off with a velvet rope, nobody classed here. That didn't stop Ray. We found the stuffed animals. I'll just leave it at that. This is a quote that I think sort of summarizes the way he led his life, and I certainly think a lot of us are taking that to our heart. Thank you.
Okay, so I'm Vivishek Sudhir. I'm a faculty member here. I think I have the notoriety of being, among the speakers, the person who knew Ray the least amount of time. So I met Ray January of 2017 at Snowbird in Utah. That's a ski town where they have this amazing conference called the Physics of Quantum Electronics, PQE. So of course this was right after the discovery was announced, the paper was published. Ray was a keynote speaker there in a session on quantum optics. And I was one of the speakers who succeeded him after that, in that session after him. And I was giving my thesis talk, as it were. And what we had done in my thesis was to observe quantum radiation pressure short noise, which is one of the fundamental noises that goes in the noise budget of LIGO. And my thesis was one of the first to actually observe this in a nanomechanical oscillator. So I'd given this talk, I could see that, Ray was sitting in the audience. Once in a while, he would nod his head. But most of the talk, he had his eyebrows deeply furrowed. So I was kind of concerned. But anyway, I finished my talk. He never asked a question. Well, of course, in the frenzy of the aftermath of the discovery, I couldn't find Ray to ask him what he thought of the talk. But anyway, the next day, I was getting my coffee, and Ray came over, tapped me on the shoulder, and said, look, he had his characteristic, finger wag. I said, look, I want to talk to you about your talk. I said, sure, ask away. And he proceeded to, I would say, interrogate me for about 4 hours. He bought me lunch in between, so that was good. But he interrogated me for 4 hours, and he wanted to really understand what we had done in the experiment, what the systematics were, what kind of checks and balances we had performed. So after 4 hours of all this, and me profusely sweating through the whole experience, he said, look, here's what you should do. So he pulled out a piece of paper from his pocket, wrote down an email. It was actually Nergis's email. Said, look, you should write to this person and see what happens. So I wrote to Nergis. I was anyway planning to write to Nergis, looking for a job as a postdoc. So that actually ended up being fruitful. I came to MIT as a postdoc, worked with Nergis. And one of my hobbies is photography. So here's Ray doing his characteristic finger wag, definitely disagreeing with me about something. Here's another photo from, I think this was us celebrating Ray's 90th birthday. I like this photo because you can see that this is, of course, Matt, who's looming over Ray in this strange perspective. It's probably a premonition of, what Cosmic Explorer might ultimately do. Let's hope that metaphor actually plays out. Well, here's one. This was probably a few months after I joined as a postdoc. This is, of course, the laser head that's actually downstairs, which you can actually go and look at. This is a dinner at Nergis's house. I think this was the day after the Nobel Prize was announced. So I was kind of hanging in the background. I'd just known some of these people for no more than maybe a couple of months. So I was kind of a fly on the wall, sort of, taking away these photographs, so that was nice. And really this, again, from his 90th birthday celebration, it's kind of an emblematic photo for me because what Ray's actually looking at, if I remember right, and Matt or Lisa can correct me, this is actually a framed photo of Ray teaching Elena to play the piano, correct? Yes. And this was presented as a gift to Ray, and of course it's immediately obvious, sort of the childlike sense of wonder and, playful smile that Ray has on his face. I think that's what I remember about Ray. He always had that, this childlike wonder and playfulness, even when he was doing physics. So at some point, I applied for a job and I was given this faculty job at MIT. So for the first 2 minutes after I got the offer letter, I was extraordinarily elated. And then suddenly there was a sense of doom that settled on me. Because this seemed like an enormous responsibility and a huge shoe to fill into and step up to. So I was extremely despondent. I called up my PhD advisor and said, look, thanks for writing this wonderful letter that got me this job. Really, I can't do this. I'll have to go back to India, go back to my small hometown and teach high school physics, which is all that I ever wanted to do. He had some choice words for me. He was a German. He promptly clicked the phone, and that's the end of that. So I came into the lab on a Saturday, still despondent, not knowing what to do. And Ray was in the office. I went to him and said, "Look, Ray, this does not seem like I really want to do this. I don't think I can step up to this thing." I said, "Well, look, here's the thing. Half a good idea is really good enough when you start out, and you'll spend the rest of your life figuring out the other half. And if half of an idea is good, and you spend the rest of your life finding out the other half, that's probably a good sign that the first half was good in the first place." So that's, I think, what we are still doing here. And in fact, what we are trying to do in our group, and I want to go back to this photograph. What we are trying to do in our group is to actually figure out how we might actually do experiments where we might produce and ultimately observe, perhaps, gravitational entanglement between two test masses. And the idea being that this would be a proof that gravity itself is a quantum entity, which is something that does not yet have an any sort of empirical evidence. So Ray got excited about this problem, and we would periodically meet to talk about it. And as always, Ray would say, "Look, you're completely wrong." He would give me 10 reasons why I was completely wrong, and over a couple of hours, we would talk about it. And it seemed like we would diffuse into a scenario where I would have probably knocked down 8 of those reasons. So 2 months later, he would send me an email again and say, "Look, I thought you convinced me last time, but in fact, you're wrong for these other 10 reasons." Right? So this would go on back and forth. So this was actually a meeting where Ray invited me home. And this was after he had moved to the assisted living facility. So this was, I think, early July last year. So I thought, look, why don't I just take my camera with me this time? I'd never done that. For some reason, I thought, maybe I should do it. So I carried my camera. Ray was blasting away at me for the umpteenth time for, the next 10 reasons why I was wrong. So we had a long conversation about it, and he said, "Look, okay, maybe you've convinced me this time." And he said, "Look, I've had enough of you. Get out of this place. I feel kind of weak. I don't feel so good in my throat. Just leave me alone." As I walked out, he said, "Look, let's actually plan to meet 2 months from now, and I'm sure I'll have another list of reasons that you'll have to shoot down for me." So I think that's the last I met of Ray, and that's the last time I saw him. And then maybe a month and a half later, I had to read, unfortunately, Nergis's email that Ray had actually left us. Well, I think I'm still chewing on that half a good idea, and let's see how far that actually goes.
And I advance like this, all of them. All right, thank you for waiting so long. I'm Salvatore Vitale, I've been here since 2012. I'll be looking a lot at my notes, which is something that normally I would not do, but I have a toddler, so I slept 12 hours in the last 3 days. So sorry, my short-term memory is less than the duration of this talk. All right, so in the period between the announcement that he had won the Nobel Prize and the actual ceremony in Stockholm, Ray used to tell us that MIT was sending him to charm school. Some of you may remember. And what he meant is that they were going to coach him on how to talk to journalists and possibly, royalty, reducing the swearing. And as you have heard today, that probably was a good idea. However, I like to think that the decision was at least partially driven by the following episode. This is a press event here at MIT in Pappalardo Room, a few hours after the announcement, 10 or 11 a.m. the same morning. So the press is there, the Globe, New York Times maybe, all the higher-ups from the president of MIT downward are there. And when a journalist asked Ray, where he was when he got the phone call from Stockholm, he replied that Rebecca and he were quite nude. Okay, that's a literal quote. And so, probably it was a good idea to, coach him a bit. Now, in the weeks and months that followed, those weeks and months highlighted a side of Ray that I think most of us already knew, and that is his absolute humbleness and generosity that we have heard about a lot today. He was never I, but always us, right? As we heard about. In every story I personally heard him saying about, the early days of LIGO, it was never the focus. It was always the others. It was a collective we that made that incredible adventure and achievement possible. And the same was true when he was talking to the press, colleagues, the public. He explained how we detected gravitational waves, and he meant it. The private Ray, as we have heard today, was exactly as the public Ray. And this generosity was there at all levels. More than once, as I was holding office hours in the LIGO building in W22, after the Nobel Prize, undergraduates occasionally asked me if Professor Weiss was around and if they could go and shake his hand. And the answer, when he was around, was always yes, and most often than not, that turned out in 20 minutes of Ray asking them about their life, and so on and so forth. And, in classical gravity and E&M, what happened to you, the energy you gain going from one point to the other, depends only on the starting point and the ending point. The trip doesn't matter. And I really think Ray would not think that this applies to life, right? It would tell those students to enjoy their time at MIT and to enjoy the process of discovering and learning and the people they met here, not to focus solely on the destination, but to savor the trip. The joys, the issues, the surprises, and the people met along the way are what made that meaningful. And this was also, as we have heard, this approach to work. Every single day, an opportunity to do what he liked to do with joy and to enable others and elevate others in doing the same. As we remember the incredible scientist and the warm and generous person, I think we should feel lucky that he has left a clear legacy and an example to follow. He has showed the way and a viable path. It might not be easy to follow, but anyways, what matters is the trip. Thank you.
We didn't know how long to make LIGO to begin with. It was made 4 kilometers because of, well, there was 40 meters. The 4 was because Caltech liked 4.
This time, they're going to make the antenna 40 kilometers long.
No, that's just a little bit of a joke. And we know now that we should have made it longer.
So what do you think of this field? Like in 15 years from now,
you know it as well as I do, but it would be absolutely fascinating to find out how we got these pairs of black holes. That's a challenge that we have now discovered. And that to me is sort of, it's cosmology on near terms. It's not the cosmology of the cosmic background, but it's cosmology that is, how did the universe make progress?
Yeah, because...
And we are 10 to the -6 and 18.
Yeah.
Okay? They think that that's 50 years away, but it's going to be done.
You think?
Oh, it's got to be done. It's one of the most interesting experiments in the world.
Thank you. That's about legacy, and this panel is all about Ray's legacy. Antonius and Nancy, please come here. These were not PhD students with Ray. They interacted with Ray, but Ray left a big legacy with them, and these are the youngest, not the youngest speakers today, but the youngest assistant professors that will be talking today, and we want to hear from them. First, I want to have, since I have the mic, like Nergis, a very short anecdote. Of course, Ray was my mentor here at MIT as a scientist for very short 2.5 years, and then for the 30 years that followed. One thing that we shared that he inspired in me is a love for convertibles. And you saw his one. He bought that one when I was here at MIT, and that's when I said, I want to do that too. And I did. And he drove my car, and he liked it, so that was my dream. Anyway, we have here, like I said, 3 very young assistant professors. Nancy Aggarwal, who got her PhD here. She came from India and did her PhD here, went to Northwestern as a postdoc, and then she's an assistant professor at UC San Diego. UC Davis, sorry. Sylvia Biscoveanu, who is a young assistant professor at Princeton. She comes from Romania. She did her bachelor's at Penn State, her PhD here, her postdoc also at Northwestern, but not everybody goes there. Antonius did his studies in Greece, came here as a postdoc and interacted with Ray, and is now an assistant professor at Bard College. And they all had different experiences, so I want you to all share his legacy with us. Thank you. Nancy, do you want to start? And we won't use slides because we need to finish really fast.
Okay. Yeah, hi everyone. So yeah, I did my PhD with Nergis. So Ray was kind of my academic grandfather. I was studying quantum optomechanics when I did my PhD. And over the course of my PhD, I had a lot of interactions with him, even though I wasn't his PhD student. And what I really actually appreciated was that we have this culture of going for lunch in the LIGO lab, and even after the detection or after the Nobel Prize, nothing changed. Ray was still coming to lunch with us, and that was very meaningful to see as a student that that we were able to still continue deep academic physics discussions at these lunches. At one of these lunches, I remember this was after the detection. He was reminding us that we now have to be kind of quote unquote responsible, that LIGO, we can't just be tinkerers anymore. We have a responsibility to the broader astro community. And that was around the time when I was going to be wrapping up my thesis. And I thought to myself, you know, my physics career is just starting. I do kind of want to tinker around for a while more. So I started thinking about what I wanted to do and branching out. And Nergis was very kind to allow me to just spend months on just reading papers. They were completely unrelated to what I did. I just read papers, and I decided that I wanted to do axion detection. So I was reading these papers. I found this one experiment that actually really reminded me of LIGO in its infancy, in that it looked completely crazy, but plausible, and was sort of going for a very difficult thing, difficult target, very small precision measurement, but a lot of technical and engineering challenges that would need to be solved. But fundamentally, everything looked plausible. So I joined it, and along the way, I started also working on a high-frequency gravitational wave detector, and more broadly, just making the case for expanding the frequency spectrum of gravitational waves into the ultra-high frequency domain. And that's kind of what I'm doing now in my group. So I think one of the things that I remember just from a lot of stories from Ray was just sort of chase the physics. If it ends up requiring building something difficult, then just build it. So that's what I'm trying to do now. Ray really cared about students, and he made time for us. Like I said, we weren't his problems, we weren't his mentees, but he still made time for us. Even actually after I graduated, Ray and I had many lengthy discussions on both of the experiments, so the axion experiment that I was building and a gravitational wave detector that I was building. We went through every single constraint, every single design choice, every single noise source, hours and hours, just like what Vivishek was saying. And I was just amazed that this man who is clearly a busy person was able to take all of that time for me. Because I think it really stemmed for he cared for me. He warned me when I was actually going on this axion path. He warned me that it was going to be a difficult journey, and I think it all came from he just cared, and so he sat down with me and sort of made sure that whatever I was going to do was going to have a decent chance of success. So I like to think that one of the legacies that I would like to take forward would be just to be able to give similar amount of time and attention to the students that come across me, and just sort of help them out in a similar way as much as I can. One other thing that I remember that I don't think has been mentioned today, but at some public event, someone asked Ray how did he get into doing what he ended up doing? And his answer really sort of stuck with me, which was he said that you can like the big physics question all you want, gravitational waves, yeah, blah, blah, very, very nice. But you also have to, at the same time, enjoy what you do every day. And a lot of students come to me, ask me how should they be choosing the next stage in their career. And that's all I have to say, because I think it is completely true that if you don't enjoy soldering, you will probably not enjoy being an experimental physicist. Speaking of soldering, one other anecdote that comes to my mind when I was thinking of what to say here is that we're all physicists. Sometimes we work weekends. It's normal. I was working on a Saturday in the lab, and I ran into Ray, and Ray sees me and says, "What are you doing here? You're too young to be working on a weekend." I was like, "You're retired. You don't have to work at all." And so he completely nonchalantly just started to explain to me that, no, he had to solder this circuit. This was really, really important, and all these problems that he was sort of encountering in whatever he was solving. I think my memory is fainting, but I think it was an early prototype of the ray gun that he was building that day. But it was just purely curiosity and drive that has also stayed with me since then. Another fun anecdote that actually, I think that one people have talked about, how he didn't have any filters. I have another one to offer of him not having filters. We had recently started to implement a new locking technique in which we were using radiation pressure itself to lock the cavity. And Ray was completely amazed by that a laser could hold something so floppy so tightly. So maybe he didn't believe us, or maybe he was curious, but he came down to the lab to see the lock for himself. And he started tinkering with the table, just making very gentle motions, because he thought he would sort of destroy the lock. And the postdoc at the time, Adam, he just started jumping in the lab to really prove to Ray that this lock wouldn't break. And then later on, I overheard Ray talking to someone else about the lock, and he was like, "That lock, it's tighter than a bull's ass." So yeah, really no filters. He just said whatever came to his mind. One of the other stories I really loved hearing. Ray had a lot of early career stories. I cannot blame my child, but I just generally do not have a good memory. So I only remember one of them that sort of stuck with me. And it was of his difficult time when he was doing gravitational wave detection and wasn't being appreciated by RLE and the funding situation and everything, and he was let go. And then eventually he found a home in LNS, and I think eventually LIGO found a home in MKI. And as I've been thinking about his legacy, I was reflecting on that story and I realized that actually there is a lot of parallels with my own personal career trajectory, that I am also pursuing these sort of gray interdisciplinary ideas, high frequency gravitational waves. Are they astrophysics? Are they high energy physics? Primordial black holes? Are they astrophysics? Are they, and the techniques are AMO. So I'm also sort of facing a lot of the same things, the physics silos and the funding landscape, and just thinking about that story has actually, I was feeling pretty jaded, but this last couple of months when I'm thinking about that story has given me a whole new motivation that, this is not a new problem. It has been solved before, and we'll figure out a way to solve this, that physics is just physics. We don't have to sort of create these fake borders, and we'll figure it out. So Ray kept going, and that's just, I want to keep going as well. That's it.
Thank you.
Sylvia. I had some quotes that I'm going to pull up. So I was a PhD student here from 2018 to 2023, working with Salvo Vitale, but I actually joined LIGO in 2015 for a summer undergraduate research project working on detector characterization for the stochastic background. So I was, a first-year grad student. There's this big bookcase in the McNair building that has all of the theses of all the previous students, and I pulled out Nelson Christensen's thesis, and I was, very excited to see that some of the early pioneering work on search strategies for the stochastic background had actually been done in Ray's group in Nelson's thesis from 1990, and it was amazing to see, 25 years later that basically the foundations of how we do the stochastic cross-correlation search were the same, and the role that Ray had played in that. When I came to MIT to do my PhD, my work shifted more towards compact binary coalescences and characterizing them both individually and on the population level. But I was still interested in the stochastic background, and so with some external collaborators, we had written a paper on a new method for how to separate the stochastic background of primordial origin from the stochastic background that comes from all the unresolved astrophysical sources. And I would say that Ray's main impact on me and my development has been just how supportive he was of my work on the stochastic background. This is obviously not as glamorous as the 300-some detections that we have of compact binaries, and so this is more of a long-term concerted investment, which we see as a theme among his work. He's not afraid to put in work on something that might not have an immediate payoff, and that kind of encouragement to pursue these potentially more high-risk, high-reward projects at this early stage in my career was really impactful. And so for those who know, in NW22, we actually have a paper subscription to PRL, and Ray would read the PRLs and sticky note them and annotate them. And so he found my paper and he sent me an email. We were all in lockdown at the time. He wrote, "I have felt that the measurement of a primordial background of gravitational waves, either of the impossible kind, the real inflation, or those from phase transitions later in the universe, is one of the most important things for gravitational wave astronomy." And when I was graduating and getting ready to leave, he said, "Please, I want to say goodbye." So I met with him, and again, he really reiterated how he felt that this work was really important. And we've heard a lot about how even late in his career, he was thinking to the future and thinking about, the next generation and developing the science case for Cosmic Explorer, and, making sure that we have an instrument that can be used to achieve these most ambitious goals of gravitational wave astronomy. And he shared with me one of the papers that he had submitted to Vicky as the lead of the NSF and PSAC Next Gen GW committee, that was basically really highlighting how important it is to think about the primordial stochastic background as a science case, even though it might not have as immediate of a payoff and it might not be as flashy. And so I wanted to share another quote from this document that he sent me, which was, "Even though we are not sure of a detection, the possibility of these primordial gravitational waves is so important for cosmology that searches at each improvement in detector sensitivity is warranted." And so this is a line of research that my group is now continuing at Princeton. And so when I'm working on this with my students and postdocs, I definitely feel Ray's support. So that was Ray's scientific impact on me. The other area where I really felt Ray's impact and legacy is in my musical activities. So My very first individual interaction with Ray was actually facilitated by music. So I'm a violinist and a violist, and I was very involved in the musical community at MIT when I was here. And I walked into the office in NW22 one day. I had my violin with me. I must have been going to a rehearsal later. And this was, at the end of my first year of grad school. And he comes up to me and he's like, "You play violin?" And my first reaction was, Nobel Prize winner is speaking to me. But, he was very insistent to hear about what I was playing. And then he said, "Oh, you have to come to my house and we have to play together." And so he invited me over for dinner. He drew me a physical map of how to get to his house in Newton with little landmarks, go past the fire station, but really I knew I was in the right place once I saw the punch buggy convertible in the driveway. And so I had dinner with him and Rebecca. I heard many of the stories that we've heard today, and then we moved over into the living room and we got ready to sight read some Schubert. So at this point, Ray's eyesight wasn't great, and he had, in true Ray fashion, rigged up a device on his piano that would magnify the sheet music and project it on a large, computer screen. And this is how we read this Schubert together. We made it all the way through, and this was transformative for me because not only was this distinguished scientist, thinking of me in any way, but I was getting to share my passion for music with him. And so, unfortunately, because of COVID and his worsening eyesight, we didn't really get to play together again. But after we met when I was leaving MIT to say goodbye, he sent me an email and he said, "Continue your wonderful violin playing. It will give you and others pleasure for a very long time into the future." And then when I got my job offer at Princeton, he wrote to me a congratulatory email, and he says, "I heard that you have been offered a position at Princeton. Congratulations. It is also worth remembering that Princeton is quite close to New York and the best music in the United States." So forget about the science. The most important thing to him was that I would be able to pursue my musical activities at Princeton. And so this has been my first year on the faculty at Princeton, and needless to say, it's been very busy. I've had less time than I would have liked to continue my musical activities. But when Lisa and Peter asked me if I would play a musical interlude tomorrow, I said, of course, what a wonderful way to honor Ray's legacy. And as I was preparing, I needed to practice more than I have been in the last year or so. It made me realize that even now, preparing for this event, Ray was making sure that I was continuing my musical activities. Thank you.
Hello, everyone. My name is Antonios. I came at MIT in 2014, where I was a postdoc for Nergis. And I had my main experiment, of course, here, a very ambitious experiment in optics. But I also was assigned to work a little bit with Ray on a side project. Ray was very much, at the time at least, upset with the test masses and the fact that the test masses were not conductive, and therefore they were accumulating a lot of charge. So he actually described it to me, at least at the time, I'm not sure if that was really true in general, as the biggest mistake he made in the design for LIGO, that the masses were not conductive. So anyway, so he suspected that the reason for that was light coming from the ion pumps. So he and I worked together for about a year or two to measure the kind of photons, the kind of light that was coming out of the ion pumps. So this was like to me, a detail of an apparatus that is somewhere in the corner of LIGO that may affect the whole apparatus. And I came to realize that this is kind of like a quintessential Ray project in a way, at least the kinds of project that he worked on maybe later in life. And, true enough, we actually measured it and we found that it was actually one of the reasons, and someone else fixed it. But it was kind of what I did with him. Now, my first experience that I remember, and one that I cherish, was when I came to work with him he sat me down and he gave me a back of the envelope calculation, like of the order of magnitude of why our project matters. And he actually sat me down and he went through all the calculations, and I was having an outer body experience, because I feel like no supervisor of mine ever sat to write equations with me, like at any point. And we spent quite a bit of time he spent quite a bit of time convincing me that this was important. In less, let's say, flattering memory, as a less flattering memory, was one time when, as he was doing something similar, he asked me whether I knew how to work this scientific device anyway, and I told him no, and he blurted, "Oh boy." And but then he went on, to spend time and actually educate me, and again with pen and paper, kind of showed me how this thing works, and I really appreciate it. And coming from Ray, did not really affect me negatively, more than I need to know more things, So in general, when I think about Ray's legacy, really I think about all the people that he mentored, and I see the compassion and the kindness that he had, the true compassion, no matter how it came out. I see it with the people that he mentored and people I met at MIT and in general in LIGO collaboration. I think that's evident there. At the time when I was at MIT, my family was actually in Connecticut, so I had to go back and forth 3 hours every weekend, and he was very, very concerned about this. So every time that he would see me, he would ask me, "Is the family together?" When I got my position at my current college, that's the first thing. And then I met him a couple of years later. He would ask me, "Is the family together?" And I was able to tell him yes. He seemed like very happy about that. And in part I owe it to him, and I'm very happy that he was so human-centric, let's say. And I take that along with me. That's all I have to say.
So I hope this shows that, there's a film called, a documentary short film called LIGO Generations that talks about how LIGO has been built through several different generations. I think I would like to call this Ray's generation, because it's not just his students and grand students for people who are students of students, but all the people who mentored and he worked with has left a legacy of how to respect everybody, even when swearing, how to work with everybody, and how to build incredible things that maybe had been called crazy at some point, or difficult, and we all did it as a team, and he would say that. So that's Ray's legacy. Thank you.
Let's see. Can you please put the closing slides? Just very briefly, Nergis already thanked several people. I just want to thank them again, Reshma, Amalia, and the MIT AV team that did a great job and stayed over time to support us. So maybe an applause for them. Thank you. And sorry, this is not a complete list, but there are a lot of people that helped me, Peter, Nergis, putting all of this together. So thank you all very much for being here. Okay, I have one last thing. Can you put the movie on? And now I apologize, there are professionals in the room, and this is a movie that I made when Ray won the Nobel Prize. I knew that the Nobel Prize won't be discussed much because it's not something I was very proud of, to be honest. But I want to show what it meant to us. And so this is the last thing that will happen today. And again, apologies to the professionals for what you're going to see.
Välkomna allesammans till Kungliga Vetenskapsakademin. Det är alltså dags att presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Science. Now, this year's Nobel Prize in Physics. And as usual, we'll go between the languages. I am Göran Hansen, I'm the Secretary General of the Academy. And we...
What? In the quantum world.
Exotic matter in the quantum world. Topological insulators, I bet.
I want my Dunkin' Donuts money back.
This year's prize is about a discovery that shook the world. Årets pris handlar om en upptäckt som skakade världen.
Literally, Mike.
Kungliga Vetenskapsakademin har beslutat att utdela 2017 års Nobelpris i fysik med ena hälften till Rainer Weiss. Med ena hälften till Rainer Weiss. From the US. Dr. Weiss, are you there?
Can you hear me?
Yes, absolutely. Good morning. This is Göran Hansen, the guy who woke you up an hour ago or so. How are you now?
I'm fine. I even have clothing on.